No, it's all good. All right, we're gonna get started here soon. First off, welcome to the CSM session on machine learning. We're really excited to be here, and I think we have a really exciting set of speakers. So just for the speakers, we are going to be giving you a 2-minute warning over here. It'll look like that. And we have a discussion session at the end. So, you know, have your questions prepared and be excited to discuss some points about machine learning and CSM with you. We're going to throw up the code of conduct. We want to make sure that everyone reads that and make sure they internalize it, and we all want to be respectful here. And then lastly, if you're online, please put your questions in the chat and we'll read them aloud. So with that, we're going to launch right into that, and we'll start with Stefan here.
All right, hi everyone, good morning. Today I'm going to talk to you about the progress we've made towards AI-based climate modeling with a model from my team at Google called Neural GCM. This is a new sort of AI-based model of the atmosphere. First, I want to briefly acknowledge the big team that worked on this project from Google and with some collaborators from ECWF and MIT. Okay, so the context here for sort of this work is, I think, really like looking back over the past couple of years, people have sort of started to explore using machine learning for global weather prediction. And when people sort of started, this is actually like an absolute scale here, on sort of skill relative to the ECWF's deterministic weather forecast, which is roughly sort of the state-of-the-art model. Sort of state-of-the-art physics-based forecast, and as recently, like the first models, out like 2019 or so, were like really pretty embarrassingly bad on an absolute scale. So like something like 20–30%, and then a bit of progress, and then suddenly over the past couple of years, we've seen these AI models sort of shoot upward in skill, and suddenly measured on skill, like here's like root mean squared error relative to IFS. In the past, this is basically all in like 2023, there are now a whole bunch of AI weather models that are sort of at parity with ECWF. And I haven't updated this recently, but in the past like 6 months or a year, there's probably like 4 more or 5 more that are up there. So it seems like, and this has gotten the weather community really excited about AI. And so there was a Nature and Science paper. ECWF has their AI-based forecast model. NOAA is also starting to run a bunch of like AI weather forecast models. So the weather community is like really excited about AI, and it seems like, and there are caveats. We'll kind of get into a few of those, but like something really dramatic happened here, because this is like sort of this is really sort of like the crown jewel of numerical weather prediction, sort of the global weather forecast that has on timescales of forecast timescales up to a few weeks ahead is now better with these AI models that are trained on reanalysis data sets. I guess in this talk, I want to sort of explore how hybrid approaches might help us sort of bring these advancements, sort of this AI breakthrough from weather into climate modeling. So here I kind of want to sort of map out kind of a spectrum in terms of different modeling approaches. From the sort of the pure AI approaches that are on the left, these are all based on like deep neural networks, and some of these models like the GraphCast and Pangu are up there. And then on the other side, we have sort of more traditional sort of physics-based models that like numerical weather prediction and climate models. And in between, there's the space of hybrid models. We heard a bit about hybrid models yesterday in like Veronica's talk, but I mean, at a high level, here we're sort of taking some parts of the physics-based models, and we're combining those with AI. And we're sort of typically replacing subcomponents like subgrid parameterizations. And so potentially, I guess the hope is that this can sort of blend together the strengths of both these approaches. So on the one hand, again, on the pure machine learning models, these models are actually very small, like very little code. Like GraphCast is like 5,000 lines of code, which is like absolutely teeny compared to something like CESM, which is, I don't know how big CESM is exactly, but it's million, exactly. There you go. And in principle, CESM is interpretable, but you'd have to read 2 million lines of code first. So there's kind of some question of I think complexity is a little nuanced. On the other hand, these ML models are trained on huge archives of data, and we have that for weather forecasting. We have data sets like ERA5, which are sort of reconstructions of weather over the past handful of decades. Which we don't necessarily have for climate in many cases. And the physics-based models are kind of based on physics. That means that we trust they're going to generalize, even in, say, in a climate change context. In contrast, the weather prediction models are just optimized for forecast accuracy, like to make the best weather forecast. And so for prediction-type problems, the machine learning approaches work incredibly well, and it seems like we're not going back from that. But for cases where you're maybe sort of less prediction-type problems, maybe more sciencey problems, where you want to explore hypotheticals, maybe we want more of the physics-based approaches. I think in reality, if sort of problems we look at in climate modeling often fall in between. And like there are some parts of the problem that we actually have huge amounts of training data. If you're looking for things that like sort of patterns that look more like weather inside of a climate model, we have gazillions of like satellite images or clouds, but we don't have. On the other hand, there are also parts where we don't have it. We don't have that data. So the hybrid models are appealing because they're kind of this in-between path. And that's what we did with neural GCM. So sort of brief recap of sort of hybrid models. So this is not a new thing. People have been sort of exploring this for, again, a handful of years now with deep neural networks. So far, it's been a sort of mixed track record. So sometimes it works, a lot of the times it doesn't. And oftentimes you train these models and they don't make a stable forecast. The model seems like it's great when you're training, and then it just kind of blows up or the climate drifts off. A lot of these have been relatively idealized settings, like sort of really training for example, like on an aquaplanet, or sort of training from idealized models, even just training to match like some sort of a simulation, which may have some at varying degrees of quality. And they haven't been that great in sort of the real world. They haven't been anywhere close to the performance of the pure AI models. So we were kind of hoping to change that. And we think one issue with a lot of hybrid models is they've been optimizing for the wrong thing. They've been doing this thing called offline learning, and I'll kind of walk you through what that is and kind of how we changed that with neural GCM. So in like an offline learning model, you have some physics-based component like a dynamical core. And now you have, but there's some errors in that model that there's maybe some processes you don't resolve quite right, and you want to fix those with a machine learning model, say a neural network. So in the sort of typical formulation, you would say you're going to sort of collect a bunch of input data, you sort of run your dynamical core, collect a bunch of outputs of what the dynamical core produces, and a bunch of examples of what you want. Let's say one time step later, let's say. And typically this has to come from a simulation. Maybe you're predicting fluxes. You can't measure the fluxes, sort of all the fluxes in the atmosphere. So you need like a high-res simulation to do that. Then you just optimize the neural network to estimate that quantity. So it's a pretty straightforward thing. It's actually a pretty easy, relatively sort of machine learning task. It's done all the time. But like sort of any number of machine learning techniques can do this. Unfortunately, when you actually use these, again, you're training over one time step, but when you use it, we run even a weather forecast, where you actually are running out that model hundreds, thousands, tens of thousands, maybe millions of times to sort of run it forward in time. So there's a big gap between what you're doing at inference time versus what you're doing at training time. And in machine learning, and so this means that you optimize it to do a task that's very different from what you want to use it for. And there's actually a lot of like feedback cycles, like these instabilities, for example, that you don't capture with the sort of offline training. And so this makes it hard to get these models to work well. In contrast, what we did with neural GCM is we took the sort of physics-based approach. We rewrote the dynamical core in the AI framework. So in our case, we wrote it in JAX, which is a framework that's used for training many of Google's big AI models. You could also do it in like PyTorch or Julia. And now it's a differentiable. Now the dynamical core is differentiable. And it also incidentally runs on GPUs or TPUs. Because it's differentiable, we can optimize through the dynamical core as well. And so that's really powerful. That means that we can now optimize over, say, we can feed it back in over many time steps and optimize the collective behavior. So there are some other challenges for going out to like optimizing over like climate timescales. Like sometimes the gradients are not always sort of in the right direction, sort of going for long times, but we can certainly optimize over weather timescale. So now at least we can get the feedback cycles over maybe over a few days or weeks. And we can also optimize for other quantities, maybe things that are like things that we observe, as opposed to that's kind of a bad color there. That's all right. We can optimize for things that for observables potentially, as opposed to just like the fluxes in the next step, which we can't measure. So we can use like more real world data. Oh, I'm running fast. Wow. Okay, we're a little ahead of schedule today. Cool. Okay, I'm going to breeze through my results really quickly here. So we have this differentiable hybrid model for the Earth's atmosphere. We wrote it in JAX. We have neural network learned physics. We trained on ERA5. It looks like a general circulation model, except we replaced some parts with a neural net. I think we did start about 5 minutes late, but that's okay. We have great results for weather forecasting. I'm not going to sort of worry that, but we do beat this ensemble weather forecast, which is kind of an achievement that people have not hit before previously. We also have really realistic looking weather forecasts. I guess we don't have time for my quiz, but one of these is sort of ERA5, and the others are forecast models from our stochastic model. They all look pretty similar. You can guess, but if you look really carefully, you can see there's some high-res features we don't get, but it's pretty close. And we can also do basic climate type projections. So with prescribed CESM temperature, we can run our atmospheric model. And we don't sort of do everything fully physically consistently, but we have the sort of the boundary conditions like CESM temperature. So we can run things out over, say, the next year. We have pretty favorable biases compared to a global storm resolving model. This is X-Shield. And which runs at way higher resolution, is also like outrageously expensive. This is like 1 million times cheaper to run. If you compare to a model like CESM, it's more like, I don't know, like 300 times cheaper to run or something like that. So it's still like 10 cents to simulate a year instead of like a TPU is pretty cheap. Like it's like a GPU basically. You can just runs out pretty fast. So that's kind of the exciting potential here. We can do tropical cyclones reasonably. We can even do some sort of like AMIP style climate projections. I have this is over the training data set, so some caveats here, but I have a comparison to CESM, actually, on the AMIP. I mean, this is probably not a fair comparison. I'm sure there are a lot of things we don't do that CESM does, but near surface temperature bias, like it does like sort of like much better actually, which is maybe not surprising. It was like optimized for that, and CESM was tuned for a lot of other things. But neural GCM was also tuned so it's kind of tuned for everything. So this is kind of like a different paradigm that we could explore. Okay, so we have a paper, it's a preprint that's on the archive right now, and we have open source code for this as well. So we have documentation, so please take a look, ask questions. So really briefly, next steps, we're kind of obviously not a complete climate model. There's a lot that needs to be done. I think these are problems for us, but also for like this entire there are a handful of other groups sort of working in this space as well. So if we think about doing climate modeling, we really need to get into sort of coupled modeling. There's probably a lot of new challenges there. The stability, still a challenge. The differentiability helps, but it's not solved. And then there's kind of the elephant in the room for climate projection is that we need ways to generalize into the future climate. I think hybrid modeling is a really effective way to do that because you can build in things like we could write a radiation scheme, just put that in there. Then we don't have to worry about different levels of carbon dioxide, for example. But that is sort of a challenge we need to solve. I'll close by mentioning what would really help us is better for the AI community is sort of a better benchmarks and kind of as much as you can distill down the insight of what it means for like a good climate model. Like the AI community loves benchmarks. If you can give us a score, if you can have like climate score that's like, this is impossible, but like even if you can distill things down into like a digestible versions of things that like, you really have to spell it out, but if you can do that, like that's amazing. And like that's what WeatherBench did. So like WeatherBench sort of distilled out like the criteria for here's what an amazing like weather forecast looks like. And like a bunch of companies, like a bunch of people, even more than like on that list. A bunch of others like tried, but like, did not quite get there. But like there was a huge community in the AI community that started doing this. And like, so like if we can do that for climate, that would be like really incredible. So I encourage you to think a little bit about that. Talk to me. We also have, Google actually has a grant program for faculty where we're giving out some funding for this as well. So we're pretty excited about this. That's it. Okay, cool. That was a very long 2 minutes.
So When they did data assimilation, they had differentiability problem for moisture. That's why precip isn't assimilated. You can't build an adjoint.
Yeah.
So if you bring in moisture, could you still maintain differentiability?
So yes and no, I think. So I think you can't, like, so some of the processes, like especially in traditional parameterizations, are sort of non-continuous processes, so you can't really necessarily differentiate through them. I think, and often in the machine learning community, we use like approximated gradients of different kinds. There's like a whole library of tricks for calculating these things. So I think that I think in principle that should not be impossible, but like there certainly are going to be cases of and they're like when you're kind of beyond the predictability timescales of weather way out, like that then the derivatives are less helpful directly.
Hi, everyone. Okay, so what I'm presenting here, it is a study that is the last chapter of the PhD thesis of Raymond Seleford. So the Greenland ice sheet is currently losing mass at an accelerated rate. This is both due to atmospheric and ocean warming. The average mass loss in the last decade is 0.07 millimeters sea level rise per year. We have a couple of years with more than 1 millimeter of sea level rise contribution, 2012 and 2019. And the largest contribution to the mass loss is coming from surface melt. The standard approach for projections of future melt is using regional climate models that are downscaling the input from a global climate model. However, this approach is very expensive. The regional climate model is run at a 10-kilometer resolution typically. But the alternative is that the global climate models by default don't include a melt calculation for the Greenland ice sheet. But CESM2 does in all of the runs. And it has a very advanced melt calculation that has been thoroughly evaluated. It has a very advanced snow and fairness scheme. So the question here is whether we can use CESM2 to train a neural network so that we can use atmospheric fields from all of the suite of the CMIP6 climate models to obtain melt from them through the neural network, since they don't have a physical explicit melt calculation. Okay, so this is the training data that we had from CESM2. So we have 10 historical runs and 19 scenario runs. So they include prognostic Greenland ice sheet melt output. So this is our neural network. In the input layer, we are going to have annual means of summer maps of near surface temperature, geopotential height at mid-atmosphere, cloud cover, net radiation at the surface, so the sum of solar incoming and long wave incoming, or snowfall. And I say or because we are using these maps independently. We are not combining them. So we have this input layer with maps, one map per year corresponding to the summer. And then we are going to allow a maximum of 4 hidden layers that correspond to 4 patterns that we can activate. And then what we want to predict is melt, integrated all over the ice sheet. So this is in units of mass, so gigatons per year. So this is what we are getting. So here we have the, we use one independent simulation of CESM that we then include in the training. Here for evaluation, so the melt calculated explicitly by CESM is in the black line. Okay, so we have black lines there, and then the blue line is the prediction by the neural network. And then the components of that come from the hidden layers from the patterns of the neural network are in colors orange and then green and red. We activate a maximum of 3 layers, so we never reach the 4 that we allow us maximum. And for one case, that is a snowfall, we only need one pattern. Okay, so we are gonna have a look variable by predictor by predictor. So starting by 2-meter temperature, that is the one that works the best. So the correlation here is 1.00, and between brackets you have the correlation when we did trend the time series. So we have a first pattern that is active from 1950, so from the beginning. So when we have a summer with high warming in the southern half of Greenland, we have high melt. But as time goes by, we are going to have more percentage of melt coming from northern Greenland because the melt takes more time to be activated or more warming to be activated in the north, but it comes eventually. So from 2040, then the weights for southern and northern Greenland are very similar. And what we don't weight are the margins. And this is because the margins are at melt point. And when they are at melt point, then the temperature, the near surface temperature cannot increase as much, okay? Because the surface cannot go over melt point. This is very similar to what happens over Arctic sea ice if we compare warming in the winter and the summer. This is from the interactive atlas of the IPCC. So I'm taking all of the models here and comparing warming over the Arctic in the winter and the summer. So it's much less over the summer. So it's the very same story over the margins that are melting in the ice sheet. So there, the increases in temperature that correspond to high melt are small. Okay, so for geopotential height, we get more melt. For high geopotential height, that correspond to high blocking, high heat advection, and clear skies. Now for the cloud cover, yeah, we have mixed stories for the short wave and the long wave energy. But what we are getting here is that we have more melt when we have clear summer skies in the margins, particularly in the southwest, and cloudier interiors in the ice sheet. And then for the incoming radiation, we get more melt when we have high incoming radiation in the interior. And for the snow, snow is also a very good predictor here when we are within the CESM world. And so if one summer has high precipitation in the interior, give us more melt that summer as well. So it's a warmer summer. But in the margin, we are going to have more amount of rain because we are at low elevation. And then the weight is negative for the snowfall. Okay, so now we go with a comparison, a true evaluation we get out of CESM world, and we are going to compare the neural network with dynamical downscaling with the regional climate model. So we have here a model called MAR that is going to downscale 5 global models. So this corresponds to the black lines. So this is the truth from the dynamical downscaling. And then we have the predictions from the neural networks for each of the variables. So 3 variables, geopotential height, cloud cover, and net radiation, underestimate melt. They don't work well for the prediction. They are not good predictors. And the best fits, we get them for near surface temperature and snowfall. For CESM, all variables are good predictors. So when we are downscaling dynamically or with a neural network, we get very similar results, irrespective of which variable we are choosing. But because some variables don't work for the rest of the models that are our target, we are going to use only near surface temperature snowfall as predictors. So here the dotted lines correspond to the average melt that we get with these 2 predictors. We combine it, and then we compare to the solid lines that correspond to the regional climate model. And the blue line now corresponds to an SSP 1 2.6 scenario that was run for this particular model. Okay, so now we are getting pretty good fits. And we are going to extend the approach now to all of the CMIP archive, anything that we had at that time. So it is more than 100 simulations per SSP. That's fantastic. And okay, so these are the 4 scenarios, 4 lines that correspond to the means. And you have here the global mean temperature change, and also the melt prediction. So mind that 360 gigatons per year would correspond to 1 millimeter of sea level rise, but you would also have to consider refreezing. So here is melt, so the sea level rise is going to be less because a portion of this melt is going to refreeze. Okay, so typically it's 40% for present day. Okay, so this is pretty good. So you have this column with the estimates of melt that come from a physical model in CESM2, but now we can extend and have predictions from any CMIP model. And so now our standard deviations are more, and we can assess uncertainty in a more complete way. Can I go? Can I go to the next slide? No? Thank you. Yeah, no, it's good. Okay, thank you. Okay, so here is the analysis of the sources of uncertainty. So the primary source of the spread in the melt projections comes from the model choice. It is followed by the scenario, and then the choice of the input variable. We have only 2 choices, whether it is 2-meter temperature or it is snowfall as predictor. Okay, and now we are mapping here the melt estimate to the global warming level estimated by each model. So you see a clear relationship between global warming and the melt increase. Okay. Okay, so the conclusions here is that we found a strong correlation with with the physically based melt calculation for all predictors when we stay within the CESM world, the CESM modeling. Now, when we move to other models and we compare with dynamical downscaling from a regional climate model, temperature and snowfall are working well. Other variables are not working so well. So you can imagine that these cloud patterns may not work well when you are going to a different model. we found a large contribution to uncertainty to the model spread in the estimate of melt. And the projections are this. The projections can be provided for the full CMIP6 archive, although these models didn't have an interactive melt calculation, and this is really great. So this is a relatively cheap way to extend the science that we have done within this community to other models and complete our estimates of what is going to happen in the future with Greenland. No, thank you very much.
Unfortunately, we have to move on to the next speaker, but we do have the 15 minutes of the discussion time, so thank you. Our next speaker is Yuan. There you are, perfect, great.
Hi everyone, thanks for joining this presentation. My name is Yang, and today I'm gonna show you a method to emulate work with climate model PPEs and the insights from working with them. We all know that climate model PPEs are very important, so we have some set of parameters, and we have the corresponding model outputs, and we study them so that we know how the parameters affect the climate model output, and we use them to train the emulator so that we could better predict the climate model output at any given any parameter value combinations. So there's a key feature of the PPEs, which is very sparse. So we only normally have a few hundreds of runs, and we have extreme high parameter space, normally several tens. So this is really similar to draw the coastline of a country, given just 3 points. So in the following presentation, I'm going to show you how the method works, evaluate its performance, showing some insights, and I hope to convince you with these insights that analyzing a PPE is different from analyzing emulator-generated data trained based on the PPE. So it's kind of, it's two things for different purposes. So our emulator is actually extremely simple, and it's simplified from additive Gaussian process. So it's additive, and it accounts for a parameter interaction. It works with one variable at a time. Because of our simplification, it doesn't account for uncertainty. So its prediction is literally just the sum of additive terms, and each term is the mean of a Gaussian process with fixed hyperparameters. So this is where the simplification happens. So we fixed hyperparameters, which makes the resultant uncertainty is just not useful. So we allow it to have 1, 2, 3 parameters as input for the Gaussian process. Could be 4 or more, but probably not that necessary. So since it's additive, we're able to kind of monitor how the root mean square error decreases as we add more terms, include more terms as the prediction. So in this case, the little, okay. This green arrow is showing the contribution from one parameter or a parameter group. So this is like a simple scenario of how the method works. So first, it fit a Gaussian process with these fixed hyperparameters for each of the parameter. So the figure here, the x-axis are all the parameters of the climate model. So you have the root mean square error for each of them, and you pick the one with the lowest one. So apparently for this iteration, it's the best. So that's the green point here, and use the corresponding Gaussian process mean as the additive term for this iteration, which is the red line. Which is this line here. Okay. So this point is selected. Apparently, there's lots of residuals, so you pass it to the next iteration. So similar thing is done for parameter pairs. The only difference is the measure, like how we select the parameter groups. So the assumption is that if a parameter group is important, its importance should be a lot more important than the other parameter pairs. So the measure we propose highlight the benefit of emulating a variable using the two parameters or more jointly compared to using them independently. So the color is not so great here, but so the two figures here both correspond to a variable. The x and y axis are the parameters. So you can see on the left, it's a little bit colorful, which make you think it's good, but actually it's not, because there might be too many important parameters, meaning none of them are really that important, given the sparsity of our PPE. Whereas here, it's not very clear, but this point is really standing out, very deep dark red compared to Audi blue. So in this case, it's definitely a significant parameter interaction. So we apply this method with two PPEs, CAM6 PPE and Model E3 from NASA GIS. They have different number of ensemble members, different models, different range of these parameters. So we use 80% of them for training and the rest for testing, compared it with fully connected neural network. The target variables are global averages or model scores, which are the weighted difference between the zonal model output and observations. So, so each point here is basically a variable. You can see that they are mostly kind of on the one-to-one line, which make us think that they have comparable performance. But it's clear, so for the CAM6, our method performs slightly better. So to the left. Okay. Oh, really? With this? Oh. Okay, so here it's anyways. So for the CAM6, it's a little bit to the left. So our method is slightly better. For the Model E, neural network outperforms. So I highlight this point, total ice water pass here, because somehow our method just easily outperform neural network, and I'll show you our explanation later. For both methods, the CAM6 PPE don't perform that well. That is because some of the target variables are model scores. So it's like 0 and -1 and 1 is kind of the same sometimes. So if we just focus on the global averages on the right, you can see both method performance improves, for both methods. So in this case, we're thinking, because our emulator is so simple, so we think maybe it's a little bit provocative, but we want to kind of suggest that the learnable relationship between the parameters and output variables is not that complicated, given that the PPEs are so sparse. So, so this is to test our the assumption simplification. So hyperparameters doesn't matter. So here the horizontal bars are showing the variability when we change the hyperparameters. And the y-axis, so both x and y are from the same method. So the vertical bars are showing the variability from random sampling, as you can see here. And you can see the horizontal bars is very small, so showing that the simplification is justified. Moving down to some insights from working with this method, and most of them are more pronounced for the Model E3 PPE, which is, I think, related to how the PPEs are specified and the model characteristics. So I select 3 variables here and pile the kind of the variability explained by the different parameters and groups, and classify them. So the green, light blue, and gray bars are the contribution from individual parameters, and the warm colored bars are from the parameter pairs. So what's interesting is the light blue bars marked in this dashed line. So they are the sum of individually not so important parameters. So a maximum of these individual parameters only contribute to about 5% of the variability. But when you sum it up together, you can see the width of the light blue bar on the right is pretty long. So it's saying, and the same for the warm color bars, which is for parameter interaction. So it's saying that the cumulative contribution from individually less important parameters and parameter groups should not be neglected. So here is trying to explain to you why our method works well with total ice water pass. So the y-axis are the variables, x-axis are the parameters. So the colors here are showing the variability explained by each parameter. You can see for total ice water pass here, so which is unshaded, it's only strongly explained by, now it works, by two parameters, this one and the orange one here. The yellow one is very important for all other variables, but for this VF mod S, which is related to ice falling speed, snow falling speed, it only helps strongly explain this single variable. So we think that this is why, because the neural network works with all variables all at once. So it's kind of lacking the patience to just focusing on this one optimizing, emulating this one variable. The benefit is too small because it's focusing on other more than 30 variables. The standalone relationship is kind of overlooked by neural network, again, because of the sparsity. So again, analyzing a PPE is different from analyzing the data generated from an emulator. So here it's interesting, and I'm still a little perplexed about it because the number of sample members matters. Again, with the Model E3 PPE, instead of 80%, which is 611 points, we use only 250 points to train the emulator. And the results are presented on the left. You can see it's kind of half-half for the two methods, so comparable performance. And on the right, we trained our emulator again, but we force, during the training and prediction, we force it to select some more parameters and parameter groups. So these added parameters and parameter groups are selected based on training with the 80% of the data. So we're stealing some metadata from training with more data. And you can see, so the x-axis for neural network remains the same. So the performance really improves a lot. So that's interesting and a little confusing. So we only have, so these 250 points have information that could help with the emulation. But this information is difficult to extract the metadata from it by both our method and neural network. And then this is the case with CAM6. So we're focusing on the zonal climatology, selecting two variables. You can see the difficulty apparently varies a lot, especially for the shortwave cloud forcing near the equator. This is very straightforward. And for the long wave cloud forcing, we're focusing on two variables to dive deep into what's going on here. So these two figures are just corresponds to the the variables at the two latitudes, and different lines corresponds to the random test to make sure it's robust. So first we noticed that the top three important parameters are different, which is highlighted here and here. And then we find a little bit of parameter interaction that contributes slightly to the emulator performance. So when we do it, each time we find a very small, but in each case we saw it, the decrease that's from these two parameter pairs that are highlighted here. So we think it's robust and showing that it's probably able to capture some kind of parameter interaction. Whereas at other latitude, even if we force it to have some parameter interaction, the performance still doesn't improve. So this wraps up my presentation, and so this method is very simple, but makes use of the sparsity of the PPE. So it does emulation and do a little bit of analysis. And we want to say that analyzing a PPE could help improve your emulator design, and it is different from the emulator generated data, which serves for different purposes. So thank you.
Okay, we have time for one quick question, if anyone has one.
The Gaussian process is good at picking up on structure in the PPE. Is there a way you think to use the structure you learn using your method to inform the neural network?
Yeah, actually, a big drawback of our method is that it works with one variable at a time. So going back to this figure, so for the case with the model E3 PPE, so when we consider the correlation between the variables, our method could improve just slightly. So which means you shouldn't emulate all at once. Also, you shouldn't emulate one at a time. So that's definitely something. So our method could be viewed as a tool to help you analyze the data and develop better neural networks, I think. Yeah, that's a great question. Thanks.
Okay, great. We're moving on to the next speaker, which is me. Hi. I'm Kirsten. I'll wait till the slides pop up. Great. I'm Kirsten, and this is work that I've done with my collaborator, Will Chapman, who you briefly mentioned as the person who introduced the session. And this is work we did with our SOAR student last summer on exploring the relative importance of the MJO and ENSO to mid-latitude subseasonal predictability. And I have some red colors in here, so I really hope the red sticks throughout the talk. Let's see. The button's not working. Got it. Okay, wonderful. So since this is a machine learning session, I just wanted to briefly do some introductions about what we're going to be talking about today. So I'm specifically focusing on subseasonal timescales, which I'm defining here as 2 weeks to 2 months. This can vary depending on who you're talking to. But what's known across the subseasonal timescale community is that it's often very difficult to predict because neither atmospheric initial conditions that we use for weather or these slower varying boundary conditions that are important for seasonal timescales and longer provide sufficient enough information to make these accurate, usable forecasts on these timescales. But there's this concept or idea of forecasts of opportunity, sometimes referred to as windows of opportunities, where there's specific conditions in the Earth system that are known to provide enhanced skill on these timescales, and we can harness these opportunities for improved subseasonal predictability. And one of these opportunities is the Madden-Julian oscillation, or the MJO. It's this convective dipole oriented east-west that propagates from the Indian Ocean into the Central Pacific, and it propagates over about 20 to 90 days, and it can affect weather in the mid-latitudes on subseasonal timescales. But previous research has shown that when the MJO is active, it can be used to make more accurate forecasts over the Northern Hemisphere in the coming weeks or on these subseasonal timescales. So I just want to briefly mention that the location of the MJO is defined by phases. So you can just equate phase to location, going from a 1 to 8. Another source of opportunity is the El Niño Southern Oscillation, or ENSO. I'm sure most of you know this, but it's an anomalous sea surface temperature pattern in the tropical Pacific. And this can also influence weather, and it's typically thought to influence weather on seasonal timescales. But often, when we think about subseasonal timescales in ENSO, we think about its modulation of the MJO and MJO teleconnections. So that's what this diagram on the right is showing, where we have phase 7 in panel A and B, but the top is for an El Nino background state, and the bottom is for a La Nina background state. And in it is orange. The orangish and greenish color clouds is the MJO, and these blue and red circles are the Rossby waves that propagate from ENSO, or the MJO in this case. And you can see that they're very different propagation of both the MJO and ENSO and MJO teleconnections. So ENSO is often thought in this way to influence subseasonal timescales. But there is also a subseasonal evolution of ENSO teleconnections, where ENSO teleconnections evolve over the boreal winter due to changes in the strength of the background state. And this is a great paper by Will on the monthly modulations of ENSO teleconnections and the implications that it has for predictability over North America. So this led us to the question about the relative importance of the MJO and ENSO for mid-latitude subseasonal predictability. And in particular, we're going to focus on the North Pacific, which is a region of the Pacific North America pattern that both the MJO and ENSO influence. So you can't really read it, but the top says ENSO network and the bottom says MJO network. But to explore the relative importance of these sources of predictability, we use what's referred to as a neural additive model. And this is an architecture that we adapted from Gordon et al. In 2023. And basically what this is you can combine two different artificial neural networks using a linear combination to make a final prediction. So this top network here is our ENSO network. And it's tasked to make a prediction of the sign of the circulation anomaly at 500 hectopascals over this boxed region that we've averaged over. And we use information about ENSO, so specifically we're using the Niño 3.4 index, and then we also provide that day of year information just based on the fact that it's important to know or to understand that background state in terms of it influencing ENSO teleconnections. We also provide information about the evolution of ENSO from 15 days prior. This isn't very important for ENSO, but it is really relevant for the MJO. But we also wanted to give equal information to the ENSO network as we do to the MJO network, which I'll talk about here. We use the RMM index, which is just a way to define the amplitude and the location of the MJO. And we provide RMM1 and RMM2, which can be combined in different ways to define the MJO state. And then 15 days prior for each of those, so we get the evolution of the MJO. And then we also provide that day of year information. And this is making the same prediction of the sign of the circulation anomaly over the North Pacific at a given lead. Then these two predictions are linearly combined in our linear layer, which is the gray shading here, to make our final Z500 prediction. But we also wanted to explore how the evolution of whether ENSO or the MJO is going to be important for a variety of different leads. So we look at leads ranging from 5 to 30 days. And then we also wanted to see the influence of averaging, temporal averaging on the predictand, or our Z500. Often when we're talking about subseasonal timescales, we do weekly averaging or even biweekly averaging. So we wanted to explore whether this also influences the source of our predictability over the North Pacific. So to do that, we look at temporal averaging windows from 2 to 30 days. Okay, but what I haven't mentioned yet is that when we input our Niño 3.4 index and our RMM index into our neural network, I'm giving it just a random day. I'm not saying that it's an El Niño. I'm not saying it's a La Niña. And I'm not saying it's neutral, and the same for the MJO. But what we wanted the neural network to do is to identify these forecasts of opportunities in a data-driven way. And so to do this, we use what is referred to as network confidence, which is nicely shown in the schematic here that I really like. But basically, in more serious terms, network confidence is defined by this softmax activation function here. And all you need to know is that this function converts the last two values of our neural network into values that sum to 1. So in this case, we have a positive and negative circulation anomaly, and the value that's greater than 0.5, since this is binary classification, is the value that the neural network is predicting. So in this case, it'll be the positive circulation anomaly in red. But you can imagine that if the value is really close to 0.5, this suggests that the neural network isn't quite sure whether this is going to be a positive or negative anomaly, and so we're defining this as low confidence in the prediction. On the other hand, if you have a value that's close to 1, this suggests that the network is quite sure in this positive circulation anomaly. And so this concept is drawn in the schematic here, where as confidence increase, does our accuracy also increase? And then if this does, we can use confidence as a metric to identify these forecasts of opportunity or these periods of enhanced predictability. And so that's this diagram that I'm showing here. We have confidence on the x-axis, accuracy on the y-axis. On the left, I'm showing the CSM2 pre-industrial training, which I forgot to mention. We're using the CSM2 pre-industrial runs. And these are 100 years that we use for our testing. And then on the right, we applied ERA 5 reanalysis data to determine the relevance of what our neural network learned to actual reanalysis data, or what we're calling as observations. So on the left-hand side, focusing our attention there, we've just shown two different Z500 averaging windows. We have 2 days and 28 days. 2 days is in the lighter blue and 28 days is in the darker blue. And then the impact of lead on our scale is shown in the shading there. So it's actually not that large, which is interesting, but I'm not going to talk about it right now. But what we do see is, in fact, as confidence increases, our accuracy is increasing, suggesting that we can use these confidence values to identify forecasts of opportunity on these subseasonal timescales. And then we also see very similar results for reanalysis, suggesting that what the neural network is identifying for forecasts of opportunity are also useful in a reanalysis data set. So it's relevant for physical purposes. Okay, so now going back to our question about exploring the relative importance of these sources of predictability, I wanted to focus just on that linear combination layer to orient us on how we could, for example, get a correct positive prediction. So there's a couple ways to do this. Our ENSO and MJO network could both say this is going to be a positive circulation anomaly, which is correct, and so we get a correct prediction. But given that there's a linear combination here, we could also have the ENSO network correctly predicting it's positive, but the MJO network incorrectly predicting it's a negative circulation anomaly. But given the weighting in this layer, the neural network ultimately determines it's a positive circulation anomaly. And then on the other hand, we could have the MJO network correctly predicting a positive circulation anomaly, and so incorrectly predicting it, but MJO winning out for the ultimate final prediction. So you can imagine we can identify the frequency that either the ENSO network alone or the MJO network alone correctly contribute to these predictions. And we can do this for correct predictions overall, but we can also look at these forecasts of opportunities, which we're defining as the 20% most confident predictions. So that's what I'm showing here. The left is for correct predictions, and the right is for confident and correct predictions. In the teal, we have the ENSO network, and that's the frequency of, and we're showing it in percentages here, but it's basically the frequency that the ENSO network alone makes a correct prediction. And then in the pink-purple color is the MJO network correctly making a prediction, where the ENSO network incorrectly makes that prediction. And if we're looking at the left panel here, this is maybe what you expected, and it's what we expected, is that at these lower lead times, or smaller lead times, the MJO network more frequently contributes to correct predictions. And as we move down in time, the MJO becomes a little less relevant for these subseasonal predictions, and the ENSO network becomes more relevant, especially on those monthly timescales. But if we further subset in this to correct and confident predictions, we actually see that the ENSO network overall contributes more frequently to these predictions than the MJO network. We can further subset these predictions into negative and positive predictions. When we're talking about negative circulation anomalies over the North Pacific, this is normally associated with El Niños, or MJO phases 6 and 7, and then positive predictions, La Niña, and MJO phases 3 and 5. But what we see for negative predictions is very similar to what we saw for all predictions, is that the ENSO network contributes more frequently than the MJO network. And on the other hand, for positive predictions, interestingly, the MJO and ENSO networks contribute about equally to these predictions across lead time, but a lot less frequently than our negative predictions, suggesting that our negative predictions were easier to predict for these confident and correct. And then I also forgot to mention that these are for the weekly Z500 averaging, but we get very similar results for a variety of different averaging. We can further explore the direct contribution of the MJO information and the ENSO information to the skill, where before we were just looking at the frequency. So how we did that is using permutation importance, where we basically, for example, take the MJO network and we randomly shuffle its inputs, but leave the ENSO network inputs correct, and then make these predictions, get the accuracy of all of those predictions, and then subtract it from our network where we didn't have this shuffled data. And that's what I'm showing on the left-hand side, which is the change in accuracy, or the contribution of correct MJO information to our final scale of our network. And on the right-hand side is where we shuffle ENSO information and see the change in accuracy. And what we found is that over almost all confidence levels, we see that the MJO contributes about 5% accuracy to the total network, where on the other hand, the ENSO network contributes 10 to even 30% of accuracy if we're looking at the most confident predictions, suggesting that ENSO is, again, very important for these subseasonal predictions over the North Pacific. We also know that ENSO is not always active, so we wanted to explore when ENSO was in neutral conditions. So we did define ENSO neutral in this case, and then what we did is we did a clustering analysis on the MJO input for correct and confident predictions, and then we've separated them here into positive and negative. And what we saw is that the confident and correct predictions relied on MJOs that were anomalously strong, or they were strong and then decayed into neutral, meaning that there was no deconstructive interference from the later phases of the MJO, or very persistent anomalies. So to conclude, we found that ENSO was a greater source for state-dependent subseasonal predictability, but when ENSO is neutral, we found that anomalously strong and or persistent MJO events provided the most mid-latitude subseasonal predictability. Something I didn't mention is we did look at the impact of the day of year value that we gave into our neural network, and noticed that during late boreal winter was the most predictable times. Just to mention that we were predicting the sign of the anomaly, and this could change if we were looking at a regression problem. We'd also like to, these are for CESM, and we'd also like to see if this is a model-dependent result and how this may change in a future climate. And then this is published, so if you're interested, you can find the paper here with our QR code. And that's all. We have time for one quick question.
I feel like I might have asked this the last time I saw you present on this, but I'll ask again because I don't remember the answer. How dependent is the result on the quality of the MGO simulation in the control model? Because we know MGO is kind of like okay at best in CSM2.
Yeah, well, we're finding that the scale is relatively similar between ERA 5 reanalysis and our CSM. So we're assuming that this means that our neural network is identifying physically relevant teleconnections for our reanalysis data set. That's the best answer I have for you at this point. But yeah, it seems like it's the teleconnections are well represented, and we show that in our supplemental information. So the propagation doesn't necessarily seem to be impacting our results. Yeah. Okay, so we'll go on to our next speaker now, which is Jairon. Where is there? Oh, hey.
My name is Jairon. I'm a third-year PhD student at the University of Maryland. And today I'm going to talk about the work we've been doing with Dr. Maria Molina on how to leverage machine learning to understand more about the sources of predictability for North American weather regimes at the S2S scale. So the same scale as Kirsten was referring to. So we have a main research question, which is where does atmospheric predictability come from? And that means what variables contribute the most to that predictability and what processes are associated with those variables. We have an initial hypothesis that the atmosphere is the most important one for the first week of forecasts, then the land contributes the most, and then the ocean becomes more important in terms of predicting at the S2S scale. So the first issue, we had to decide what to predict. So we know we cannot predict small-scale features at the S2S scale, so we went for the large-scale features. And for that, we selected weather regimes as our output for the artificial intelligent methods. These are easier to follow and understand than small-scale features, but they also affect weather at the surface. So they change precipitation and temperature anomalies, and also storm tracks and so forth. So the method to compute these weather regimes is that we take biweekly fields of geopotential height at 500 hectopascals. We extract the region of interest, which is North America, and then we remove the annual cycle and the linear trends in the data. And then we perform principal component analysis to reduce the dimensionality of the data into 12 time series. And then we use k-mean clustering to separate 4 clusters from this time series. And those 4 clusters are equivalent to these 4 weather regimes. And when we project back the data into the original geopotential height anomalies, we extract these 4 weather regimes, which are Alaskan Ridge, Pacific Trough, Greenland height, and Central US height. Apart from the 4 classes, we also add an additional class, which is the no weather regime class. And it's when we have data closer to climatology than to any of the 4 centroids. The next question we had to ask is how to predict. And first, what predictors to use to represent the initial state of the Earth system. For that, we use data from the analysis. We selected 4 variables from the atmosphere, 9 variables from the land, and 10 variables from the ocean. And for all of those variables, we removed the climatology, we removed the trends, and then we also performed a dimensionality reduction with principal components analysis. And now the important or the relevant detail here is that we do not train a model with all the all the variables combined, but we trained a different model with each variable in order to compare the skill of all the models and see which ones are more important depending on the lead time, the season, and the weather regime we're interested on. So the algorithm we use for that is XGBoost, because it's fairly robust and it's also computationally cheaper than deep learning. And we have this framework for each variable. So we have 20 principal components as inputs for that variable, and then 1 of 5 classes as the prediction that we want to get. A reminder that we're not looking for the best performance in general or overall. We're looking for a fair comparison among models to see the importance of each variable. In here we have the first result, which is in the y-axis we have the F1 score for each one of the AI models, and in the x-axis we have the lead time. And each one of the lines presents the performance for the best model from each component. So in purple we have the best models from the atmosphere, in orange we have the best models from land, and in blue we have the best models from the ocean. And then the red line represents the score or the performance of persistence, which would be our benchmark for these results. What we see is that after week 2, the ocean becomes the most variable source of information, and then for the first 2 weeks, as expected, the atmosphere performs better. What we don't see is that peak in land predictability after 7 days. We see that land performs worse in this case than the other 2 components. However, we know that teleconnections, for example, or evaporative processes change with seasons significantly. So if we go and look into the different seasons, we find significant differences among seasons. And for example, we see that in this case, when we look at spring and summer specifically at the late lead times, the soil water content, for example, gets to be more important. Ocean heat content, however, still is the best predictor in most cases, but we see changes depending on the season, and we also see important changes depending on the weather regime we're interested in. So for example, for Alaskan Ridge, we see that land properties contribute the most predictability across several lead times. However, for Pacific Trough and Greenland High, the ocean is still the best predictor. And then for the Central US High, we have kind of competitive behavior between the ocean and the land. But for example, an interesting thing is that for the other weather regimes, we see that ocean heat content is the most important variable. However, when we look at Central US High, we see sea surface high as the best predictor, which speaks about maybe having different sources of predictability from the ocean itself. So we have, for some cases, maybe more tropical relevance, and then for other cases more reliability on extratropical process. So the next part of the analysis, or the next step, was to go ahead and look into the principal components that contributed the most to those variables' skill, right? For the advantage we have is that for these principal components, we have a spatial pattern, which we can relate to a physical process, and we also have a time series. So the question is, what spatial patterns were more relevant for each variable? And for that, we asked 2 questions. The first one is that we require the principal component to be anomalously high or anomalously low, and that changing significantly the distribution of the weather regimes into the future. And then the other requirement for selecting principal components was that the magnitude of the principal component was higher than average when a correct prediction was made. With that, we can highlight some of the principal components. In the y-axis, we have all the variables that we had, and in the x-axis, we have the 20 principal components. The black boxes are the ones that accomplish those 2 requirements, right? And for today, I'm just going to talk about one principal component related to one process that was found in several of the variables. So that talks about the robustness of that relationship or the importance of that process for prediction. And that process is ENSO. So we have in the left, the spatial pattern and the time series and of the principal component, and in the right, we have colors indicating how the likelihood of each one of the weather regimes changes depending on how the distribution of the time series of the principal component change. So in this case, for example, the black boxes show that when we have low values in the principal component, which is equivalent to having an ENSO in this time series, a La Niña event, sorry, we have higher likelihood of Pacific trough occurring and lower likelihood of Greenland high occurring. And we see that not only for ocean heat content at this depth, but also at different depths. We see that at sea surface high and sea surface temperature patterns. Now, when we look at the atmosphere, we see associated spatial patterns to that same ENSO signal, right? So in this case, we see that upper level divergence in the tropics in the Western Pacific is also related to the same change or the same increase in the likelihood of Pacific trough. When we look at the geopotential height over the tropics, when we see an anomalous decrease in that geopotential height, so colder tropics, we also see that increase in the Pacific trough and that reduction in the Greenland high likelihood. An interesting feature that we found when we looked at OLR, which is directly related to the location of convection, is that if the location of the convection changes, for example, from being more central over the Pacific to being more towards the east, we can get significantly different results or significantly different impacts on the weather regime's likelihood. So for example, in this case, we see that in the left, we get an increase in the Greenland high distribution when the time series is higher, but we get the opposite effect in the right, which is a slightly different spatial pattern. We also found, this was just one example, we also found different processes and spatial patterns that were relevant to changes in the distribution of weather regimes. So for example, we found that other processes related to the Arctic ocean distribution of sea surface height were important. The ocean heat content over the North Pacific gyre was important too. We also found that changes in the stratospheric jets, specifically the polar and north subtropical jet were important. And we also found that some specific patterns of soil moisture were also related to changes in the distribution of weather regimes. These results are being summarized in this paper that is in preparation. And finally, I want to thank my research group at UMD and NCAR for the computational resources. I'll leave you here with some of the conclusions, but the main relevant one, or the main one, is that we can use machine learning not only for trying to achieve the best prediction, but also for trying to complement our actual knowledge of the state of the art of the sources of predictability. Thank you so much.
We have time for 1 or 2 questions.
I know you said you weren't focused on predictive skill per se, but how much? I guess I'm curious how much you what fraction of sort of predictive skill you sort of resolve with models like this? How the more sort of explainable approaches? Does that still get you I don't know? Is that 80% of the way there? Is that 50% of the way there? Is that 90% of the way there?
You mean how far can we get combining all the variables and trying to achieve the best?
Yeah, if you were okay with more of a black box approach, for example, if you have a sense of that.
Yeah, we haven't really looked into a combined model that maybe using the same XGBoost algorithm try to leverage all the variables. However, we found something interesting, and is that we also trained 3 models which corresponded to combining all the variables from the land into one model, all the variables from the ocean into one model, and the same from the atmosphere. And what we found is that those models performed better than the individual ones sometimes, but that wasn't the rule. So at least from this framework, we cannot guarantee that just including all the variables and performing a deep hyperparameter search necessarily gets us the best skill possible. And the results are really in the same order of magnitude, and they are really competitive across lead times. So we didn't really see how far can we get, or if we can get too far with combining all the variables. Yeah.
Okay, our next speaker is Dan.
Good morning, everyone. My name is Dan Amrein. I'm a scientist at NCAR in the ocean and data assimilation sections. Excellent. And the title of my talk today is Improving Forecasts by Learning Optimal Transforms Between Dynamical Systems and Imperfect Models. And I'd like to acknowledge my collaborators. Niraj Agarwal was a postdoc at the time he did this project and is now at NOAA Series, and Ian Grooms is at CU Boulder. So an outline of this talk, I'm first going to introduce the problem of forecasting with flawed models and try to distinguish between what we'll call fidelity and mapping paradigms. I'll then introduce a data-driven approach to optimizing pre- and post-processing operations on forecasting. And then I'll demonstrate this to the Lorenz 96 model and also to CESM SMILE initialized predictions. So first introducing these and contrasting notions of fidelity and mapping in prediction. So here is a schematic of how prediction often works in the context of a reference system on top. This is this XR, which is maybe advancing in time. So you can think of this as the model truth, or sorry, the actual truth, the true system. And often we are interested in taking some estimate of an initial state and using it to initialize a model. This is the X sub m. And just as the true system is going to advance, this thing's a little inebriated, the model also has an operation that's going to advance it through time. And we think a lot about how these models behave, right, and how well they're doing their physics within the model. I think sometimes we tend to think less about this step of how we get from some estimate of the initial conditions to this model. And so I'm going to denote this here as being these two transforms, this TRM, which is taking you from the reference to the model, and then the TMR, which is taking you back from the model to the reference. And this can be non-trivial, right? Because we know that models and dynamical systems often live on different attractors, right? So they, if you initialize a model with observations, sometimes it's going to drift or have an initial shock as it goes back to its attractor. Also, sometimes we know that these, well, almost always, these things have very different state spaces, right? And so we're having to do some interpolation or parameterization in how these things are represented. So this, I really like this description from this paper in 2006. It says, the fidelity paradigm assumes that nature and the forecast model are the same, and therefore starts the model with a state as close to the state of nature as possible. By contrast, the mapping paradigm recognizes that numerical models of any system in nature are only imperfect images and searches for a mapping that connects the states observed with the corresponding states in the model. This is also connected to the idea of shadow filtering in data assimilation, which is this nice idea that your observations, your true system attractor, kind of live on a particular manifold, and then they cast a shadow, which is the shadow of the projection onto your model manifold. So the question for this work is, well, can we come up with a kind of generalizable and objective way of deriving how we initialize models from a reference state? And so I'm going to outline one way of doing this. And the starting point is this kind of deceptively, once you look at it for a few weeks, but deceptively simple loss function, right? And this is basically saying, well, here's the true forecast, and then this is kind of the life cycle of a model forecast, right? We start with this reference state at the initial conditions. We do this operation TRM on it. Then we're going to do the model forecast, and then we project it back to the reference state. And so we would love to minimize the squared misfit between the true next step and the forecast after it kind of goes through this life cycle. And you can write down the loss function, and that's basically what we're doing here, is to say, well, if we have lots and lots of realizations of the reference system at some initial time and some final time, then we can try to optimize for these two operators, TMR and TRM. And so that's what I'm going to call CATS, cross-attractor transforms. And so this is a pretty general framework that, as I mentioned before, includes models with reduced state spaces and different numbers of component submodels, etc. Okay, so what does this actually look like? So we're going to apply this to the Lorentz 96 two-scale system and specifically asks, can this CATS framework improve skill when forecasting a chaotic higher dimensional system with a deterministic lower dimensional one? So this is the Lorentz 96 setup. Above is me proving I know how to use LaTeX. I'm not actually going to go through these equations, but this is a coupled system of differential equations meant to represent synoptic scale weather patterns around the globe. It has these 8 large-scale variables. I stole this schematic. We actually have for each of them only 4 small-scale variables in there, but it's this 2-scale system. And an important thing is this F, this forcing term. And so if we pick 2 choices of F, we generate qualitatively different attractors. And so I'm plotting the attractors here as just 3 of the large-scale elements in this 3D phase space. And so here's the choice with F equals 10, I think. And then, so this is our reference system. It's chaotic. And then for F equals 3, this is our kind of flawed model, right? And so this is something that is deterministic, and it also does not have any small-scale features. So we're trying to think of an analog to, for instance, ocean modeling, where we might not represent a lot of small-scale features. Okay, so that's fine. And now we have to confront our gnarly loss function. To compute a Jacobian of this thing, if we want to do neural nets and compute gradients, we need the gradient of the forecast model. You can do this pretty trivially for Lorentz 96. Ian is a little fancy, and so he comes up with cool ways of computing emulators using analogs. But I guess this is just to say that this is if we can compute emulators of higher dimensional models, this is also a way of computing the CATS. Okay, and so then what do we do? So we have we have a neural net architecture which consists of hidden layers on either side, corresponding to these 2 operators, TRM and TMR. And in the middle, we have this fixed custom layer that corresponds to this forecast step. And we have its gradient, because we have the Jacobian up here. So we can train this thing. And we train on 8,000 states from a long Lorentz 96 simulation of reference. And we're going to validate on 2,000 of these states. All right, so go, red bulb, go, because this is otherwise very confusing. I mean, there's a lot of lines here, and we did a lot of benchmarking. I think it's worth comparing especially the performance. So this is root mean squared error as a function of lead time, and this is in this model time unit. And so the red line here is the scaled anomaly initialization. It's kind of like a naive initialization of our imperfect model, where we scale the initial conditions by their standard deviation and then add a mean. And so you can see that over longer and longer leads, so this is like nominally 5 days within the Lorentz 96 2-scale. This is gradually going to approach the divergence, which is the climatological error of both reference and model. And down here in the green, you see the results from CATS. And so this is giving us lower root mean squared error across all of these lags. So we saw this, and then we were like, oh my gosh, are we just training an emulator, right? I mean, is the imperfect model actually doing anything? So we also did this other step, so this is in the brown, of just training an emulator using the same neural net architecture, but without the intermediate imperfect model. And so that's the brown, and we're beating that thing. Okay, so, and then also this pink line is if we're only doing the post-processing TMR step, and we'll get to that later. So some results here are that, this CATS approach is beating these other benchmarks. Pure emulation typically requires, and this is shown here, several times more neurons to achieve the same performance. This isn't just a matter of, well, I should just throw a more complicated neural net at my problem. That also means that you have to have more observations to actually constrain those neurons, right? And so what we're hypothesizing is that we're kind of in this hybrid Goldilocks regime where we have adequate data to train these CATs, not enough to train an emulator that is as skillful, and an imperfect model that, while being imperfect, is adequately skilled to kind of regularize this emulation problem. So even though our model has a lot of problems, it's giving us some skill. And so I'm mindful of time, I'll kind of go through this, but you can actually see, again, the life cycle of what these forecasts look like. Here's a trajectory from our reference space. We can map it using, the red is the anomaly initialization, green is CATS. These things give us different trajectories, and when we map them back, we see that CATS are much closer to the true forecasted values. Okay, and so briefly in a couple of minutes, I want to show an application now to CESM SMILE. So the question here is, can we improve skill on a high-dimensional, non-stationary Earth system model? Seasick. Okay. Okay, so this SMILE, the seasonal to multi-year large ensemble experiments, are a set of 2-year-long hindcast simulations initialized quarterly with 20 ensemble members every year from 1970 to 2019. So I'm showing you here a picture of the North Atlantic, and this is anomaly correlation coefficients between SMILE and HAD-SST over this entire period. And the question is, can we improve on this using this CATS approach? Okay, and so I'm making a series of dramatic simplifications here. I'm fixing TRM, so I'm only doing this post-processing thing. I'm assuming it's linear after some offset, and I'm only looking, this is suddenly we're in non-stationary territory, right, where it depends on the month you're initializing. So I'm considering the problem of 2-month predictions initialized in November. And then we can suddenly solve this just using regression, right? This is something that even I can do. Okay, so we're going to try to train this, and then we're going to do this on using contemporaneous HAD-SST as truth. Okay, so as a first cut, if I have my calibration and validation, so I'm basically testing on my training, okay, yeah, fantastic. We have really high correlations everywhere. But it shows that this approach is actually gives us leverage to fit the observations. Okay, so now the harder test, right? So I'm going to calibrate over this 32-year period and validate over this shorter 14-year period. So here again are the original anomaly correlation coefficients from SMILE. You might be like, Dan, that looks very similar, right? But we do get a little bit of increased skill in this particular region, right? And so we can look a little bit, so that this is known as the northwest corner. It's a place where models often have trouble with the path of the Gulf Stream going into the North Atlantic current. So that's interesting, and maybe a place where we're actually able to improve a model bias. So what does this look like? Well, when we actually apply this TMR, here's the original prediction from SMILE, and this is the modified prediction that we get after applying our post-processing, and you can see it's modifying mostly around the northwest corner. Another cool thing is this is a linear solution, so we can understand it completely, right? So this is kind of an explainable AI piece, I guess. If we just take the SVD of TMR, we can see how the structures that are model-like are translated into structures that are more SST-like, right? And so this is kind of under the hood of what this approach is actually doing. Okay, so to conclude, these CATS are optimal in the sense that they're data-constrained pre- and post-processing operations that are trained on forecasts. When they're used with process models, it's a form of hybrid modeling, right, that's inspired by this past literature on mapping paradigm and shadow filters. The cool thing is that we don't touch the model, right? We're leaving the model processes intact. And so, and I've also shown how they might be able to offer ways of diagnosing model bias by showing how conditions need to be transformed from one state space into another to mitigate bias. So we're able to show improved skill in the Lorentz 96 configuration, and I feel like this is kind of first light in a higher dimensional space, looking at the SMILE test, and we think that there's potentially lab applications for this, and so I'd be excited to collaborate with folks. Thanks a lot.
We have time for maybe 2 questions.
Think there would be scope for applying this in line so you can get the impacts on everything else in the atmosphere, or is it easier to just do this for everything?
That's a great question. I mean, people have looked at, with data assimilation, for instance, you'd like to kind of map back and forth between your reference and your model state as you go. Could you incorporate this in the model tendency? I mean, or maybe that's what you're asking. So far we're the model is kind of untouched, right? And so, yeah, it'd be interesting to think about how you might incorporate that into that paradigm. I don't know, yeah. Kevin?
Better results.
Yeah, I think so. I mean, there's always this tension between training data and the skill, right? And so I had to do ridge regression. I had to do some really gory dimensionality reduction of these things. So yes, 100%, I think so. Thank you.
Here as well.
Awesome. So my job got significantly easier over the course of this session because we had introductions from Kirsten about the Mann-Julian oscillation, which I'll talk about, and Stefan and Dan about hybrid modeling. So essentially what we're trying to do here is a hybrid modeling approach where we're combining machine learning and CSM to try to improve predictions. And we're doing that through the lens of trying to learn data assimilation increments. So the title of this talk is a state-dependent model error representation for online climate model bias correction, which is a mouthful, and I'm sorry, but essentially we're just trying to improve CAM with machine learning. So this is work with Judith Berner. She is a scientist here at NCAR. I am also a project scientist here at NCAR. But I want to pay special thanks to Jim and Jack and Jesse, who are all software engineers who were essential in helping get this linking some of the libraries here in CSM to allow some of the machine learning, and they did a lot of great work. I want to say this is in association with the M-Squared Lines project, which is funded by Schmidt Futures, which is a sort of consortium of groups here working to try to improve climate model bias via hybrid machine learning. So let's get going. For some background or context, in dynamic modeling, we typically have these initial conditions that we pass through some sort of dynamic core, and we handle subgrid processes with a physics package, and then it makes some sort of forecast. But we know that there are errors that leak into the system. So we have errors that are coming in through some of these subgrid parameterizations that we're not representing perfectly, and also the numerical approximations we're making just to solve the next model state. So we're trying to ask the question, how can we help address these errors directly with machine learning? And it turns out these errors can be summarized really well with data assimilation systems. So I'll try to explain that here really quickly with a figure from Palmer and Weisheimer from a paper in 2011. And on the top, what we see is a healthy modeling system in which we have the obs in gray here, and then our data assimilation system, which is randomly pulling the increments back towards the observed system. However, on the bottom, we see a biased model. And the indication is that the increments are always being pulled in one direction. You can imagine this like a sea surface temperature in the tropics somewhere that's too cold, that the DA system is constantly saying, hey, warm up. And then once it is warmer, if we could correct that bias, it would potentially give it sort of access to different attractor spaces. We could potentially cause convection that wouldn't have happened before if that SST was a little warmer. And the real idea of trying to correct model bias with this is kind of summarized here. So although the amplification of some forcing on some bias process will occur on the timescale of decades, meaning that you need to look at decades-long simulations to understand biases or see biases in models, likely these processes are happening on the fast physics time step. So it's time step to time step errors that are accumulating that are causing biases that then propagate downstream. So if we can fix the fast physics errors, if we can fix the time step to time step errors, we're hoping that we can fix some downstream biases in the process itself. And Judith and I put out a paper a few months ago saying, okay, we have this beautiful data assimilation product that has been made for CSM, so we have this reanalysis. However, if we change model versions, maybe the DA will have to change and we'd have to rerun it, but it's a really expensive system to run. So we compared nudging, which is just a simple linear relaxation, to the DA increments. We found that they captured a lot of the same processes, and if we reinsert climatological nudging increments and DA increments, we can improve a lot of the model biases. And I'm just showing improvements to model bias in precipitation across different seasons here by using both DA and nudging. So from this point on, we're going to be using the nudging increments, and we're trying to ask, can we do this in a more state-dependent way? So can we take the current state of the model, write some sort of machine learning algorithm that then maps from the model state to the increments, apply these online, and thus improve model representation. So this is my data slide. Essentially what we did is we ran CAM6 for 9 years, linearly reaxing back to the era 5, and then we are nudging only the U and V winds. We found that nudging T and Q had some pretty bad problems for our model CLIMO, so we are opting just to learn U and V here. We then collect these model increments and we form a diurnal cycle and an annual cycle of these increments, and we're going to apply these online, and then we'll use a machine learning algorithm to learn the anomaly on top of that. So we essentially remove the anomaly, we have removed the anomaly from the CLIMO, apply the CLIMO, and then use the ML just to correct the anomaly increment. So we train a convolutional neural network at every model level to then predict this anomaly increment of U and V winds. And you might ask the question, why are we not doing this as traditional parameterization do it in sort of a single column sense? So why aren't we learning spatial representations rather just a very simple or easy spatial or single column representation? And essentially what we found is that by increasing the spatial extent of our filters or giving the CNN access to more large scale spatial information, we could dramatically improve the representation of the increments themselves. So I'm essentially showing how big of an area I'm giving to the CNN and the improvement to the R squared of predicting these DA increments here. We found that increasing the size of the increments, we were able to increase the scale of our model. So we stuck with a larger spatial extent here. The model architecture is fairly simple. It's a very vanilla UNet. So essentially we're abstracting information in this downsweep layer. We then have a bottleneck layer, and then we add the information back here while decoding the latent space, and then reform the full picture of the lat-long area. So we're inserting the latitude and longitude, or the full spatial maps here. It passes through this UNet, and then we want to reconstruct the whole increment space at the end. We went through a pretty large suite of input variables to see what was important to the space. And after doing a bunch of ablation studies and removing variables, we came up with a suite of 16 variables that seem to predict a lot of these nudging increments fairly well. And again, the target are these nudging increments, the U and V winds here. And what we could see is we have pretty good skill, especially in the storm track regions, of predicting these anomaly increments and predicting, especially these surface increments are particularly good. We can see we have skill, if you average across the whole atmosphere, about 0.6, 0.7. So we're able to predict these things fairly well, and we have pretty high confidence that we can take the state variable and then predict the increments themselves. So in order to put these things, this is all happening offline. In order to put it back online into the model, we leverage this toolbox called FTorch, that's written by the group in Cambridge called ICCS, and got help from Jack Atkinson in order to link it back into CSM. And we now have this running. If you want to implement machine learning in CSM, please come talk to me. I can get it all set up for you, and then we can start to move these projects forward together. However, this is only for PyTorch implementations. We can also do this with 4Pi, which is another package. So if you're a Keras user, we can make it work. But stick to PyTorch if you can. That'd be great. So what does this look like in an actual online model run? So what I'm showing on the right is the anomaly plus the climatological correction, and then on the left is just the climatological correction. So this is coming out of the CNN. This is defined through our training data by taking averaging. So you combine these two things together, you put them back into the physics package, and we see if we can't improve the representation of some of the climatological biases. And essentially what we showed is that we can. So I'm showing in orange just the mean correction, and then in blue it's the mean correction plus this CNN. And this is for 2 meter temperatures over land, global precipitation over land, precipitation in the tropics, and sea level pressure. And we see particular improvements in sea level pressure and precipitation in the tropics when you're improving or throwing in this CNN learning on top of it. If we look at all of the prognostic variables here, so U, V, T, and Q winds. Again, showing in orange just the CLIMO correction, and then in blue, the CLIMO plus the CNN. We see particular aspects where and then this is showing RMSE reduction, so anything positive is showing a improvement. So we see that across most of the variables, adding the CNN and then adding the CLIMO production itself will improve your background model state. And these are, I should have said, these are for 30-year climate runs, and we're able to do this stably, and we're not seeing any blowing up or any climate drift, which we're encouraged by. What I am particularly bummed about is we are showing an increase in bias to upper stratospheric specific humidity, which I'm sure my chemistry friends will be not too happy about, but yeah, we're working on figuring out what exactly is going on here. It's not a systematic drying or wetting anything, it's just a increase of bias there. So I was frankly a little disappointed by adding the CNN. We didn't get in as much scale as I thought we were going to, but what we do see is we see improvements to some of the major modes of variability within the model, particularly the representation of the North Atlantic Oscillation, and I'm looking at DJF. So up here I'm showing the control simulation. So essentially what's happening in the control simulation is we have a really stunted NAO. So really what you want to see are these two major dipole patterns here, and essentially in the middle of the control simulation we have this errant representation of the lower limb of the MJO. So by adding just the climatological increments, we can bring these back, but we're adding a little bit too much variability towards the northern limb. However, with the CNN, we're able to improve the space. And essentially what we've done is a stream function decomposition. And again, I liked Dan's explanation that this just proves I can do LaTeX, because I'm not going to explain what that is. But essentially we're showing that we have the interaction between high frequency and low frequency eddies that should be causing the growth and maintenance of this pattern that are now doing that because of the addition of these increments themselves. So Kirsten gave a nice introduction to the Madden-Julian oscillation. We are also examining this field, and what we can see is that by the addition of our machine learning algorithm, we are able to improve the representation of the Madden-Julian oscillation within the CAM system, and I'll show you that here. So this is showing the OLR in observations, and you see in phases 2, 3, 4, and 5, 6, 7, where we have these nice dipoles of OLR on either side of the maritime continent. This is pretty stunted and missing in the control runs. We're not getting the correct convection in the Indian Ocean or the east of the maritime continent, and by adding just the climatological increment, we do see a continued degradation of this space. However, by adding the CNN, we're seeing a really nice representation of the OLR across this region. This is for the wintertime DJF, and we're seeing that it falls nicely within the observational range. So we are representing the OLR better in the different phases, but the thing that's potentially more exciting is we're also getting improved propagation across the maritime continent. So this is what we should be seeing. This is the precipitation signal kind of moving across the maritime continent here. However, in the control run, we don't really see a connection here, and then by just adding the climatological increment, we're also not really getting much of an improvement. However, with the CNN, we're able to propagate the MJO across the maritime continent, and it seems to be doing it potentially a little too fast, but still getting a little propagation there. So really, we're trying to ask the question now, what are the increments doing? Why is this improvement actually helping? So we can potentially feed back into the model parameterizations. So I'll have you just focus on the increments here on the right. These are the V winds across the maritime continent. And essentially what you can see is an increased strength of convergence and divergence in the lower levels, indicating that we're improving or strengthening convection at both the lower atmosphere and then also into the upper atmosphere. And these are fairly fresh results, but I'm pretty confident that this is coming through a sort of improvement of this trio interaction for the MJO propagation. So essentially the CNN is enhancing lower tropospheric heating, which is then to the east of the convection region, which is deepening the Kelvin wave associated with the MJO, throwing in more convergence, which is dragging in more specific humidity. And essentially, you can see that through boundary layer moisture convergence, which the difference between the control run, which is in black, and the CNN run, which is in blue, is shown here. So you can see a dramatic increase to this boundary layer moisture convergence, which will then feed back to improve the dynamic representation of the MJO itself. We're digging more into these processes to potentially say, this is what's being represented by the model increments. Can we figure out either simple ways to represent this with the model, or actually use these online and continue to push this? I'll make the caveat that this is all in the just CAM alone. This is not in a coupled run. And including the coupled run, we do still see some improvements, but we also see some degradation. So we're working on figuring out how to iterate on that process a little bit more. So with that, my conclusions are we learn these state-dependent corrections to CAM via linearly relaxing back to observations and then learning those spaces. I'll say that we're not the first to do these, but we are the first to do it in more spatially, and then to do it for longer runs here. So we've enabled CNNs in CAM and CSM with FTorch. If you'd like to do some machine learning in CSM, please come talk to us. So we show some significant improvements and some degradation to the model climatology, and we evaluate the major modes of coupled and semi-coupled variability, and we show some significant improvements to the model representation of these fields. And we're working on this final question of why, but we think we're getting pretty close. So with that, I'll take questions.
Well, thanks. Your nudging increments are working in a model that has physics of various kinds, right? Your nudging increments are correcting a model that has physics parameterizations working. Yes. Have you thought about turning them all off to see if you can get the same? Yeah. Yeah, just don't do anything but nudge to ERA and.
If we don't have a differentiable model. But there are ways that we can do sort of Will Gregory 2024 did this iterative process of learning and sort of mimicked an online learning scheme that potentially could benefit that. It's interesting, yeah. I didn't know, I haven't done that. The whole floor kind of develops the physics, and if I go, oh, let's take those out, feels mean. Yeah, there you go.
I was curious if you ever had challenges with stability.
Yeah, I didn't, which was, yeah, really beneficial. Well, no, that's not true. So there are tuning parameters within the CNN itself. If I crank that up to like 2 times, I can develop Gibbs frequency waves and just like blow the whole thing up. Yeah, so we do tune that down a little bit. I think it's at like 0.8 right now of the full representation. So I can make it blow up, but that's not so hard. But yeah, it runs fairly stably without too much work, which was nice. Yeah.
A really nice talk. I'm just wondering if you had any sensitivity to the background SSTs. Have you done different CAM experiments with different SSTs?
I mean, we train in one regime and then test in another. So there is representation for different SSTs in that sense. But again, like I said, when we do this coupled runs, things change a little bit. So that's really the true test. So figuring out how to do that is kind of the next step. Yeah. And I think with that, we're sort of in the discussion period now. So if anyone has questions for any of the speakers, yeah, it would be great if we could roll into that section.
I have a question for you. When you showed the NAO in the control, I didn't think CSM had that bad of an NAO. So what was that?
Yeah, so I mean, maybe CSM in the coupled system doesn't have that bad of an NAO, but I keep seeing it over and over again in the just CAM itself, that I'm getting the DJF NAO and it has a stunted pattern. And I see it with Adam Phillips' toolbox. I see it with this. So it could be a particular model tag that I'm using, but I am using 2.1.5. So no, that was the full 35 years, I think. Yeah. So yeah, I'll have to, we can chat about it. Yeah. Yeah, cool.
$3,300. Yeah, I guess, yeah, there is a question of, yeah, is it hard to invert some of these matrices and stuff? And yeah, there's some tricks around that. Yeah, but that's what it was.
I think I've asked this to you every time that I've seen the cats talk, and it's amazing because we have a developer for Neural GCM. So I know in Neural GCM there is a layer that essentially takes an interpolation layer that moves from, you know, I think model space to pressure space, and then you move it forward and then move it back. So I'm trying to understand if that linking function, that TRM, so is Neural GCM a CATS, or is there a difference here, or is it just that brown line emulator? Like, I'm trying to understand, yeah, that sort of.
Yeah, I think it'd be fun to chat about this. I think, I mean, that architecture is the same. I guess one thing that we think is being characteristic is the training on, you know, lots of different forecast step, you know, previous forecasts. Yes, maybe they are the same. I don't know.
Not differentiable, but you're using an analog, so you make it differentiable, which is potentially a way to get around some of this stickiness.
Right, yeah, if we really want to get both of these operators, then we have to have a different model. And then, you know, and adjoints used to be really exotic, and now we have emulators, right? And so in a lot of sense, you can get these things for free. We don't even use a neural net emulator, right? We're doing something with analogs. Yeah, so that, I mean, and that's how we hope this is eventually a path towards a model like CESM that never, I think, hopes to have an adjoint in its full, yeah, embodiment.
Yeah, so I should have pointed out at the beginning that the organizing committee here is Wayne, Linnea, and Kirsten, all of us NCAR and Columbia employees. So we had a couple questions that we kind of gave up the group just to discuss broadly. So the first one was, what role does or should NCAR play in fully data-driven or hybrid ML-based modeling? Or I definitely have an opinion, but I'm wondering if the community thinks that this is more of a tech space, or this is more something that NCAR should have their hands on directly. I'll call out people. Yeah, Dave, go ahead. Go.
For your opinion first, then I'll give you.
Oh, I mean, my opinion is I think we have the computer, we have the capability, and we have the know-how in-house. And I think that we are also really capable of working with these groups, and I think they've been shown that they like working with the scientific community because we're adding our scientific expertise. So I think there's a way that we can both work synergetically, but I don't think that we should export all of the just model development there. Yeah.
I guess it might be dependent on what you mean by hybrid modeling, but you know, what Veronica posed yesterday, this sort of hybrid physics modeling at the parameterization level, I think clearly we should be involved in that, and that I think it plays to our strengths, right? We have a lot of experience in parameterization development and understanding of models, and so if we push towards, you know, replacing some of our most uncertain parameterizations with something we're, you know, learning based on you know, high fidelity models or better observations, I think that makes a lot of sense. It's a little less clear to me whether, you know, the approach that the Neural GCM group is taking, you know, and building an essentially emulator of the entire model, is whether or not we should be pursuing that kind of activity, or if that's left to somebody else. So I think that's maybe open, and I know Dan has been talking about this. He thinks that we have potential there too. So to me, it's a little bit less clear on that aspect. But for the first part, I think it's almost our responsibility to see if we can make a really epochal change in the quality of our models you know, with a hybrid physics model. That's my opinion. And I think we have the potential to do it.
Maybe I guess I'll represent all of big tech. I guess I think there's a lot of people in the tech industry who are excited to work on these problems, but like honestly, you know, like we have like a small fraction of the expertise, like even in this room, about like climate modeling. So like there's like basically no scalable way for us to sort of like do it all, and that's not something we want to do. So we are excited to help, you know, help, you know, everyone in the whole community figure out how to do this. But like, I mean, maybe weather forecasting is a little different. I mean, people disagree about that, but like certainly for climate modeling, like there's sort of no way to, I think, to export all that.
I'll give my opinion too. Still NCAR employee, but on the more AI side of things. I think we shouldn't limit ourselves to one pathway, because there seems to be a lot of I guess advantages and trade-offs to going the full AI model replacement, the hybrid approaches, the sticking one little piece in. I mean, I think they all have value in their own ways, but I think each run into barriers at different points in the process. So doing the full AI model run is it's I think the ceiling's a lot higher on potential performance you can get out of it, and then you can couple at the model level instead of having to dig into the deep innards of the 2.5 million lines of compute code, which I think Wayne can attest to how challenging this is to learn this process. That said, there's also, it does take a lot more compute and a lot more spin up to get something going, and you need some giant data sets to train off of, at least for now. So, but I think there's a lot of stuff we haven't even scratched the surface of in terms of what some of these models can do. But then there's also a lot. It's a big space to search through, and a lot of parts of it aren't all that fruitful. So I think NCAR should be doing some development, but we should also help the community search that space and help guide where there might be more fruitful places to search, and where you shouldn't be probably isn't worth your time to go digging, and to make sure that we're just evaluating things correctly. So I'll leave with that.
Comment, and the first talk today, there was a request for a climate bench, and I'm not sure we have that for 30 years or 100 years from now, but we may have something for MJO or ENSO. And doing whole model ML only works if there is such a thing, and we're premature to do whole model prediction beyond interannual at this point. And I'm not sure we'll ever agree what is the best climate model using a skill score, but for ENSO and MJO, there is a hope. And since we can't have a whole model score, what Dave mentioned, doing it apart may be better for longer time scales.
Yeah. And I'll also mention that we've seen a few times in talks that there are these scorecards that have been developed, and that is a suite of metrics that can be optimized on for different climate models. So I would.
Score, that's a starting point. We want prediction, not seasonal cycle of the mean state. That cannot be the ultimate goal.
Yeah.
Yeah, I agree. But and a lot of these metrics packages are moving beyond just mean, right? So they have more things to them. But that's one obvious thing. ESM Val tool, ILAM. There's a whole suite of them now, and honestly, it's complicated for us even to figure out how to manage that. I have 2 points. One is, compared to what DJ said, I agree that we shouldn't knock ourselves into one corner. I also think we should maybe keep the framework that, especially for the CSM, is that we're building a research tool. So we're not building a climate projection tool, right? We're building a research tool. So I'm not smart enough to figure out whether we're going to put ourselves in a situation where we have a perfect climate prediction tool that doesn't allow us to do research, but we need to keep that in mind that we don't get ourselves in that position. So we just need to have aware of that. And the other, I just want to do an advertisement real quick, 2 advertisements. One is that I'm surprised that you didn't advertise your machine learning working group that we have at NCAR. So I just want to advertise that Kirsten is, and others are organizing, mainly Kirsten, organizing a bi-weekly meeting where we're just talking about all sorts of machine learning applications, and I'm hoping it's open to everybody. I think it is, and it's been really great for me to just sit and learn about all the different ways we can apply machine learning within the CSM context. The second advertisement is, so there's a group called the U.S. Climate Modeling Summit, and it's a group of all the models get together once a year. All the modeling centers get together once a year, and we talk about big challenges around Earth system modeling. This year, as in many years in the recent years, we've talked about ML. And one thing that's happening on June 27th is we're having a online forum, panel forum to discuss, the potential for, basically climate emulators, climate model emulators coming down the pipe, and how are we going to validate whether or not these are good tools to be used to understand the climate change problem. So we feel like it's coming really fast, and we're not quite ready to answer whether or not these should be used in a climate, informatics kind of way, climate information. And so there's going to be a panel. I'm going to be on the panel. Chris Brotherton, Pierre Gentine. I have no idea what I'm going to say, but it's coming, and I don't even know how it's going to be advertised. But it is. I'm pretty certain it's going to be public. So just something to keep your eyes out. If I'm allowed, I'll send it out to the CSM community. So.
Cool. With that, I think we can wrap the session and thank the speakers, and thanks for the discussion.
tell everyone.
Okay. Why don't we start a few minutes late, but we have some time at the end for the discussion that is fine for overview. So I will present a little bit of the sort of current state of the WACCM working group and kind of where things stand in terms of release or getting ready for release of WACCM 7. So first, as just summary of within the last year since the last CESM workshop, including winter meeting, roughly the main development and update. So I broke into kind of WACCM and then WACCM X. So for WACCM, the main thing was we transitioned to using the CAM development physics in the most, not quite the most recent development tag, but that had some implications, as we'll talk about in some of the next slides. One of the main things really was Peter Luritzen helped us a lot with getting the model more stable so that we could get significantly better model throughput, and this required some updates to the dynamical core, and then we added in HB diffusion, and then just recently added a modification so this would only act on the unstable profiles, and this really improved the model throughput so we could do much better for tuning. We've performed a number of sort of baseline simulations, so we have some sense of where the model is currently and that we're using for evaluation and the future tuning. And then Doug Kinnison has worked on this initial implementation of TUVX in WACCM, and I won't present that here, but he had a presentation on that in the winter working group meeting, and I think that is maybe his summer project, he said. So he will be continue working on that implementation. And then we have been doing a lot of, the focus has been on the QBO tuning in WACCM, mostly with the 2-degree dynamical core, and that is one of the sort of main topic I will present here, since that's been our focus recently on the development side. And for WACCM X, we put in preliminary tests with the spectral element dicore and a 189 level model. And this is a model that basically the level structure follows CAM and WACCM, and then we have 189 level. So we can run this stably and successfully. There's some issues with using the latest version, which is related to this chemistry update that I'll discuss. And then also we have been doing some work related to nudging of the high resolution simulations, and I will discuss that as well. So first thing is related to this QBO tuning for WACCM 7, which has been significant work among the group, mostly Mejong, Sasha, and Rolando. And really the goal is to have a good QBO in WACCM 7 for both 1 degree and a 2 degree resolution. And once we transition to the CAM development physics and we added the HB diffusion, the QBO that we used to have that was reasonably good in the earlier version of model really kind of went away. And so there's been a lot of focus in the last few months on understanding why it has degraded and then trying to get a better QBO in the model, since this is something we'd really like to have in WACCM 7 when it's released. And so the slides I will show are really focused on a few different factors and trying to understand why the QBO degraded, and it shows kind of the current state of where things are. So first is to look at the effect of adding the HB diffusion for model stability. then this sort of conversion factor for the gravity waves, and then also adding the CAM development physics. So first looking at the result for the HB diffusion and adding that. So the next several slides are all the same in terms of the format, but show different set of results. So I'll explain what is shown. So the left is essentially the frequency spectrum, so looking at the period of the QBO, and then the right plots show the amplitude. And all of them, the black line will be a sort of reference from ERA interim, so that is the reanalysis as we kind of target. And then it will show a few different experiments with different, the colored lines, hopefully they show up okay. And the different colored lines show different experiments that we have been running to try to understand the effects. So here, these experiments show the kind of baseline simulation, and this one has the HB diffusion in it. And then we ran a few additional experiments where we turned off the HB diffusion at different levels towards the top of the model, so it wasn't active in the troposphere, stratosphere. And you can see here that when we add the HB diffusion, it really degrades the amplitude of the QBO compared to these ones where we turned it off. I don't show here on this slide, but when we include a Richardson number trigger into the to trigger the HB diffusion, so it's only acting when the model is unstable, then that actually gives us something like this. So that is a way to add it, only act on unstable and keep the model stable and not negatively impact the QBO. So here is looking at this gravity wave conversion factor. Again, the same sort of set of the figures. And again, here on the right show the different experiments where we've kind of changed this parameter in the red line and the sort of light blue. And you can see we can use this as a way for tuning the QBO. But in the current state here, with this one, we can't only use this factor to tune some of these deficiencies in the QBO. And then the last one I want to show is this effect of using the CAM development physics. And again, here on the right, similar plot where black is the ERA, and then the different colored lines. So red here is if we use the old CAM 6 physics, and then all of these other lines are the other using CAM development physics, and with different versions of the HB diffusion modification. And the main thing you can see here is in the red line, one, the amplitude is too weak, but if you look at the frequency spectrum here, the period is much longer when we revert to CAM 6 physics. So the combination of this sort of longer period but weaker amplitude, we should be able to basically tune that with changes to the conversion factor or the Berry's gravity wave efficiency. And so it would be possible to get a realistic, better QBO in this case with the CAM 6 physics. But with this sort of CAM development physics, we can't, or we've had trouble, I would say, tuning that QBO. So that's essentially where things stand for QBO, and what we've concluded so far is that introducing both the HB diffusion and the CAM development physics, that has impacted the QBO. And the HB diffusion we can mitigate by just applying this condition where it only triggers when it's unstable, and then we can apply throughout the domain and the model stays stable. The bigger issue at the moment is this transition to the CAM development physics and the degradation of the QBO. And we really don't understand why this has been a negative impact on the QBO. And so the focus in this sort of near term is trying to understand why using the CAM development physics has made the QBO problematic, and see if we can understand what was changed that led to this degradation, because obviously we don't want to run the model with CAM 6 physics just to get a good QBO. So that's our focus for the kind of near term in terms of the WACCM development, and then I'll talk a bit about WACCM. And so when we were running the more recent versions of WACCM, there was a issue with the thermospheric temperature that it became much larger. It was about 50 Kelvin larger than the CESM2 when we ran with the latest development version. And after some sort of examination of what was going on, we tracked it down to an update in the reaction rate for N+O2. And then this was really the sort of root of this issue. And changing this reaction rate generates different amounts of nitric oxide, and this in the thermosphere acts as a radiative cooler. So it's very sensitive, the thermosphere temperature, to this. And here on the right is shown the different values that were used for this reaction rate. So in the blue curve here is an updated reaction rate from JPL 19, which was what was implemented in a newer version of CAM. And then the CESM2 used a JPL 19, which is this black line. And then the red dots are basically observation, laboratory observation of this reaction rate from an older paper from Fernandez. And then the red curve here is what was a fit to those data that we've implemented with the help of June, Doug, and John Orlando. They came up with this fit, and that's what we've put into the new version, this 3-parameter fit, which is better fit to the observation. And I'll show some of the result of implementing this new reaction rate. So here on the left is showing the global mean nitric oxide in the WACCM model for different reaction rates for this N+O2, and these are all for the solar medium condition. So the orange or sort of yellowish line here is when we use this new JPL 19 reaction rate. And here you can see black was the CESM2 and this very large reduction in NO that I mentioned. And that creates this large kind of temperature bias in the model relative to the older version that we had in CESM2. And when we implement this sort of new rate in green, we get a nitric oxide that matches a little bit closer to the previous CESM2 value, and then the temperature is also closer. So we think going forward we will use this updated reaction rate since it really better fits the available laboratory observation. And then the last part I will discuss is development of nudging or observationally constrained simulation for high resolution WACCM simulation. So one of the things that we want to be able to do with high resolution simulation is generate realistic day-to-day variability of the model in the thermosphere and ionosphere, especially the smaller scale wave. So here on the right is kind of what we are hoping to be able to capture in terms of day-to-day variability. This is from free running model, but here you see these sort of striping. This is radiance of the atmosphere related to plasma density. This sort of striping is related to instabilities in the ionosphere that are driven by smaller scale wave. And here is observation showing a similar sort of characteristic, but without being able to observationally constrain the model, we can't create the day-to-day variation of the smaller scale gravity wave. So what we want to do is develop a way to nudge a high resolution spectral element dynamical core so that we can get the large scale variability but not sort of destroy the smaller scale waves. And so what we did is we've been looking at the NE120, which is about a 1/4 degree resolution of WACCM. And after some experimentation, we came up with a vertical profile that looks like this in terms of the nudging function. So it really drops off quite a bit in the sort of stratosphere in terms of the amount that we're nudging the model. And this is to sort of not excessively damp smaller scale waves. And we use a relatively weak nudging factor so far of 0.3 in the model to try to sort of just constrain loosely the larger scale waves and let the small scale waves sort of do their own thing so we can still get better small scale variability. And here is a result showing, so here is SD WACCM-X with the high resolution NE120. So this is snapshot for 1 day of basically altitude versus latitude, zonal mean, zonal wind. So this is from the high resolution model. Here is a Mira 2 that we're nudging towards. Here as reference is the 2-degree finite volume model. And then here is a free run of the high resolution. And you can see with this nudging approach that we've added for the high resolution, it matched quite well with the Mira in terms of the, what we would expect. And actually, if you compare to the 2-degree finite volume, some features are better reproduced in the high resolution compared to the previous nudging. This is kind of standard specified dynamics. And if we just look at the time series, we've only run this for a handful of days because the model is quite expensive. But here is now altitude versus day at 60 degrees north. And you can see the high resolution model capture many of the feature in the sort of reanalysis in the stratosphere. And that is also seen in the 2-degree version. One thing you do see here in the high resolution is the wind stay eastward, kind of higher into the mesosphere, which addresses one of the biases that we had always in the 2-degree version. So it seems like we can get better representation of the large-scale dynamics. And we did look at the power spectra. This is just an average over 5 days, showing the nudged run in black, and then red is a free run as reference at different latitude. And you can see that we can basically don't damp the sort of smaller scale waves with this nudging. So it seems like we have an approach that can be used to nudge the high resolution simulations to some sort of reanalysis for either WACCM or WACCM-X. And so then to conclude this sort of near-term development focus, we will continue to focus on the QBO tuning for WACCM 7 and try to understand why implementation of the new physics has had significant impact on QBO. And then we've developed a list of metrics for kind of evaluating the long-term simulations as listed here. Some we haven't looked at in too much detail, like the SSW frequency and distribution and the MLT temperature and winds. We do know that the seasonal cycle, there's a significant cold pole bias still, which would impact the stratosphere ozone. There's slightly wrong sort of water vapor taper quarter seasonality, and we haven't really looked yet at the sort of aerosols as much detail. And we'll have another presentation at the end later today. And there will be continued implementation of TUVX in CSM, both for WACCM and I think also for CAM-CHEM. And then we're working on the continued development of MPAS with WACCM and also WACCM-X. And then lastly, for WACCM-X, we want to verify this sort of updated reaction rate against some new observation and sort of evaluate the longer term simulation with the updated dynamical core and also physics. So I will stop there and can take any question or comment anyone may have. Thank you.
I just have clarification. So when you're running CAM6 physics, you're using that same 189 level vertical grid?
So those are for the WACCM, but it's 135 level vertical grid, and yes, it's the same.
That's the CAM7-ish grid.
Yeah.
So we developed CAM-Dev because CAM6 physics doesn't work with the new vertical grids. And so if you're going to do a proper CAM6 evaluation, I would try to revert the boundary layer resolution back to CAM6, because our ZM deep convection scheme doesn't act like a deep convection scheme with the boundary layer resolution in the 135 level. So
it's good to.
Yeah, so I don't, if that's your reasoning for saying that CAM-Dev impacted the QBO, I would do that additional experiment to be certain that that statement's correct.
Noted.
Thanks, Tink. I guess as part of the discussion, I also find it useful to see, for instance, what is the QBO doing in the mid-top version, and are there any efforts being pursued to sort of check how the two compare?
I don't know if, personally, I'm not sure, Simone, I think you have.
It was a question for you, but.
I mean, at this point, I'm sure that, I don't know if Julio is here. We do look at the QBO and the mid-top model too. So, but at the moment, that wasn't the priority. Right now, we thought that WACCM QBO has to be tuned properly, and then we can go over to the mid-top. But the QBO and the mid-top is about the same degraded than it is in WACCM, if you ask Rolando.
Yeah, I think it also depends partly what you consider good, right? Any other question or comment? If not, then I think we move on to next talk. So next talk is given by Dai Koshin, and he will be, I forget the title exactly, but he will be talking about inter-hemisphere coupling in WACCM. This one advanced, and this is the pointer.
Thank you, Nick. I'm Dai Koshin, and today I will talk about the analysis of the interface coupling in the austral winter and also its seasonal variation using WACCM 6. So first of all, I will show about the inter-hemisphere coupling. In the stratosphere, in the stratosphere, there is a large circulation from the equatorial region to the winter polar region. And in addition, there are another large circulation from the summer pole to the winter polar region. After the warming in the winter polar stratosphere, the summer polar upper hemisphere also becomes warmer in this region. The right panel shows the observational evidence of inter-hemisphere coupling. The black and gray curve shows zonal wind in the northern polar region and PMC frequency, which is a proxy of temperature in the summer polar mesosphere. So they are in good correlation. So it indicates the observational evidence of IHC. In addition, the PMC frequency in this figure is shifted 7 days backward, so there is a time lag. So the time lag of the response is also explained by the mechanism of IHC. However, there are several mechanisms with different time lags. One of the mechanism of the IHC is a gravity wave modulation. This schematic diagram shows the mechanism of IHC. In the winter hemisphere, the polar night jet is weakened in association with SSW. After that, more eastward gravity can propagate into the mesosphere, and it weakens the westward gravity forcing. And also, it weakens the poleward circulation. It induces the warming in the equatorial region. After that, the equatorial warming modulates the zonal wind in the summer hemisphere, which lowers the gravity wave forcing and also weakens the equatorial circulation. It makes the warming in this region. The another mechanism of IHC is the in-situ wave generation. The first and the second part of in the winter hemisphere is similar to that. But in the summer hemisphere, the vertical shear of zonal wind is enhanced. After that, gravity waves are generated by shear instability and also deposit westward momentum. In addition, quasi-2-day waves are also generated by barotropic and balconic instability and deposit westward momentum. This westward momentum induces the poleward circulation anomaly. It makes the warming in the summer polar region. So for now, most previous studies have been analyzed for the IHC during the boreal winter because SSW often occurs in the northern hemisphere and rarely occurs in the summer hemisphere. On the other hand, even in the austral winter, a cold equatorial stratosphere event associated with the stratospheric warming occurs once every 2 years. In addition, the IHC in austral winter was similar to that in the boreal winter. These figures compare the mechanism of IHC in boreal winter and austral winter. In addition, it was also suggested that the characteristics are largely influenced by the seasonal variation. So, in the summer hemisphere, the response is obvious only in early season, but not obvious in late season. However, the number of events used in the previous study is not so large. So, in this study, I used a WACCM 6 simulation for about 200 years to examine the IHT. I used the WACCM 6 data. The horizontal resolution is about 1 degree, and the vertical resolution is about 2 kilometers. The time period is 65 years, and the ensemble number of ensembles is 3. So I can use about 195 years data in total. And I extracted a cold equatorial stratosphere events following the previous study, which associated with the SSW. The criteria is temperature anomaly, which is lower than 2 times of the standard deviation, and the definition of the anomaly is difference from the background. And the definition of the background is long-term trend and seasonal variation, and the region of equatorial stratosphere is defined as shown here. And the onset date of CS events is the day with the minimum temperature. Using this criteria, I extracted about 100 CS events in July and August and September, which is much larger than the previous studies. So I will show the result. This figure shows the latitude and height section of temperature anomaly after the onset, 5 days average from the onset of the CS events. The left panel shows the result for July, and the middle panel shows the August. The right panel shows the September. And the star indicates the region I used to extract these events, CS, cold equatorial stratosphere events. From these figures, we can see a warming in the northern polar region in all months. So it corresponds to the response of the IHC. In addition, the pattern in the southern hemisphere and the equatorial region is similar. So there is a cooling and warming, and cooling, warming is observed. So in the following, I will examine the mechanism of IHC, and after that, I will compare the seasonal difference of the IHC. First, this figure is same as before, so this is a temperature anomaly, and this figure shows the anomaly of stream function of residual mean circulation. So we can see the distribution of temperature anomalies can be explained by the change of the residual mean circulation. And we are now focusing on the warming in this region. So there is a positive anomaly is observed. So it corresponds to the weakening of the poleward circulation. In addition, I compare the wave field. So this figure is the anomaly of EP flux divergence, and this is the anomaly of gravity wave forcing expressed by the parameterization. So this anomaly of stream function seems to be induced by negative planetary wave forcing and negative gravity wave forcing anomalies. In addition, I checked the cuba y. Cuba y is a meridional gradient of quasi-geostrophic potential vorticity, which is related to the instability. And the result shows that in this region, so cuba y becomes more frequent in the northern mesosphere. This region is a climatologically unstable region. So this result is consistent with the previous study that it indicates that it suggested the enhancement of barotropic and baroclinic instability and enhancement of QTDW. So in both planetary wave and gravity wave forcing, the modulations are related to the change of zonal wind. So the next question is where the change of zonal wind came from. So I compare the temperature and zonal wind variation. This figure shows the temperature anomaly and zonal wind anomaly. And this figure shows the vertical profile of zonal wind. The black curve shows the result for each year, so it is climatology. And the red curve shows the result for CS event. So we can see enhancement of eastward westward wind in this region and enhancement of westward wind in this height region. So I compared the meridional temperature gradient and vertical tonal wind gradient. The upper panel compares the DTD phi and DUDZ in the mesosphere in this region, and the lower panel shows the DTD phi and DUDZ in stratosphere. So first of all, DTD phi and DUDZ are almost in thermal wind balance. In addition, in the upper mesosphere, they are enhanced during IHC, so enhancement is observed. In the upper stratosphere, they are also enhanced in most cases. However, you can see there is a large deviation due to the internal variability. So they are not enhanced for some cases. So the second is the seasonal variation. This is a temperature and zonal wind anomaly for July and August and September. And the right panel shows the temperature and zonal wind. It is a climatology for July and August and September. So the overall structure of temperature and zonal wind anomalies is similar, but the background field is very different among the months. For example, the temperature minimum in this region is not observed in September, and the zonal wind in the northern high latitude eastward, although they are westward in July and August. So the question is, are the roles of the waves are different between these months? So I repeated the similar analysis again for each month. This is the anomaly of stream function, and these are the anomaly for epiflux divergence and anomaly for gravity wave forcing. So in the northern hemisphere region we are focusing on, the modulation of the meridional circulation is consistent with the response of temperature. So the altitude, the circulation anomaly of positive circulation is high in July and August, but it is a little lower in September. It corresponds to the height of the temperature anomaly, which is high in July and August, but it is a little lower in September. In addition, there is a negative circulation which is large in August and September, which is not obvious in July. It corresponds to a cooling in this region. In addition, these differences of the circulation seem to be related to the different planetary wave forcing. So the height of the negative anomaly is higher in July, but it is a little lower in September. And there is a positive anomaly in September, which is not obvious in July. And for the gravity wave forcing, they are similar in the northern mid latitude, but there are some differences in higher latitude. It may be likely related to the tonal wind, but I need to note that the internal variability is also large in this region. So the question is where the large internal variability came from. So this figure shows the position of temperature maximum in the northern polar region, which corresponds to the response of the IHC in the polar region. And this figure, the x-axis is the time and the vertical axis is the height. So we can see the IHC response is sometimes high and sometimes low. So what determines the altitude? So in the previous study, Maffei et al. 2012 calculated the correlation between the meridional wind in the southern polar mesosphere and the temperature in northern polar stratosphere. The result is shown here. So there was a positive correlation during the QBO eastward. It corresponds to the response of the IHC. On the other hand, the correlation was negative during the QBO westward. So this is opposite to our expectation of the IHC. So my hypothesis is there any another correlation at another altitude? So if it is true, this difference between QBO eastward and westward can explain the difference of the altitude, difference of the altitude. So I checked the dependence to the QBO. These colors show the zonal wind in the equatorial stratosphere, but unfortunately, significant relation to the QBO have not yet been obtained. So this is a still open question, but there may be another mechanism to determine the height of the IHC response. So this is a summary. So the IHC during the austral winter is examined. So both the modulation of planetary waves and gravity waves are observed. And the variation of zonal wind can be explained by the modulation of temperature and its meridional gradient. And the seasonal variation of the IHC characteristics is consistent with difference in wave activities and background field. However, the internal variation is large, so I will investigate the cause of the internal variety in future. Thank you.
Gravity wave parameterization for WACCM.
Yep. Okay, yeah, thank you. So yes, I'm Damien Murphy. I'm going to describe to you in something of a change from the nature of the previous talks, a quasi-monochromatic gravity wave parameterization scheme that I've been working on with my colleague Anne for some time. I've come at this from an observational point of view, so a bit of a different perspective, but one that's, that, as you'll see through the talk, strongly influences the nature of the parameterization that I'll describe. WACCM is actually a really good place to take on this challenge because it's got some really advanced elements associated with its gravity wave scheme that have been brought in over the years. But I think there's still some candidates for improvement, and it's worth sort of noting those. One of the key things is that the model source tuning can't really be aided by comparison with observations very well. So I think this is an end product of the fact that it uses fixed spectrum sources and relies on an intermittency that is constantly varying in the atmosphere, and you can never fully determine observationally because you just don't really have the capability of making that measurement. So, so that's a difficulty. There's also some recent observational insights that haven't been fully engendered into the gravity wave scheme in WACCM. And then from an observational point of view, the model doesn't really provide a set of extensive gravity wave information that can then be given back to the observational people to compare with the observations that they make, and that's something that also could be addressed. So my attempts to resolve these problems have resulted in the developments that I'll show you in the following slides. So in those slides, what I'll do is I'll talk about the current WACCM gravity wave parameterization, just sort of to bring you up to speed on that a little bit. Mention why a quasi-monochromatic scheme may be indicated. Describe that scheme and some of its advantages, and then describe some trials we're doing comparing that scheme to standard WACCM. I'll then talk briefly about secondary gravity waves and then finish off. So this is the frontal scheme, which is very much the focus of the work that I've been doing in the parameterization. It's based on some of Jager Richter's work in 2010. It calculates a frontogenesis parameter, and that's used to identify potential sources where waves are launched, and a spectrum of momentum flux versus phase speed with constant peak amplitude is launched from those sites. So let's see if we can get this thing to work. There we go. So this panel here, that's from Jager's paper. and it shows for January the different places where the frontogenesis parameter is triggering gravity wave generation. But on the right, what I've shown is the velocity field around a front in WACCM. And so the orange contours are where are of the frontogenesis parameter. You can see that they represent a small area sort of within the field. It may well be that the jet activity around the front is also a candidate for a gravity wave source. I'm just noting that here. It's not something we're working on at present, but it's just sort of worth noting for the future. And then if you look at the bottom two panels, you can see from Yaga's paper that this frontal scheme provides a lot of forcing at high latitudes, and given my background is in the polar atmosphere, that's consistent with the approach, with my interest in this. The gravity wave parameterization scheme, how does that work? So the propagation and deposition of gravity waves in WACCM is based on McFarlane 87. There's a spectrum of waves, a phase speed spectrum of waves, but each phase speed in that spectrum is treated as an independent entity. A critical level where the projection of the background wind equals the phase speed of the wave will remove that wave from the spectrum. Or you can get saturation according to the criteria described in Linzen 81 that will attenuate the momentum flux and lead to a gradient. So this figure shows some gravity wave information we dragged out of the model, and you can see that. So the colour contours are describing the momentum flux, and the horizontal axis is the phase speed, and you can see in that sort of blue indicated area there there we go, in that situation the momentum flux has reached its saturation value and is starting to decrease in amplitude, which equates to a forcing. In this region, the momentum flux is being taken away because the background wind is equaling, which is the white line, is equaling the phase speed of the wave. A key observation that sort of needs to be noted, I think, was made by Herzog et al. In 2012 using superpressure balloon measurements. And these balloons can measure the gravity wave momentum flux. They do these measured it at 19 kilometres in altitude, and they do it very well. And the observations are such that one can be quite confident in all of the measurements they make. And they showed that the gravity waves have a log normal distribution. So and what that says is that. So the log normal distribution is showing that there's a whole bunch of waves with really large momentum fluxes out here that aren't noise. They're actual waves, and what that tells us is that most or much of the momentum flux is carried by a small number of waves, a small number of large waves. The top plot shows that that's true at superpressure balloon heights. One of my colleagues, Peter Love, ran some experiments at Davis in Antarctica using a radar, and once again carefully analysed the momentum fluxes and found a similar log normal distribution in the mesosphere. So this distribution is occurring at different heights, and so is well supported observationally. And that idea sort of alludes to the concept of representing the waves as quasi-monochromatic gravity waves, which is the sort of idea that I've been pursuing here. So what we've been doing is connecting those waves to known source mechanisms. That brings some advantages. So we can observe the wave characteristics and then directly use those observations to contribute to the parameterization settings. We can also consider the influences of those on those waves as they propagate through the atmosphere, with fewer assumptions because we know more about the waves. And finally, because we've now got wave information in the model, that information can be stored and output for our observational colleagues to compare with. So there's a few advantages there that are worth pursuing, I think. So how does this scheme work? So the waves are fully specified through intrinsic frequency, horizontal wavelength, propagation direction, and spatial and temporal extent, as well as the momentum flux. We use a full dispersion relationship to relate the wave parameters, which includes calculating the vertical wave number. The wave momentum flux can be amplitude can be variable, so we can actually put in a log normal distribution if we wish to. The gravity wave saturation scheme that we use is now based on some work by Warner and McIntyre in 1996. Now that's some theory that they then use to create a parameterization. This is not their parameterization; it's just using the theory that they started with. But it can be applied over the whole intrinsic frequency and vertical wave number range. Pardon me. At this stage, we're only applying these ideas to the frontal source and not to the convective or the orographic, although the ideas are completely compatible with those other schemes that operate within WACCM. And as for the frontal source, they're triggered by the frontogenesis parameter, and they have a propagation direction that's aligned with the background wind at the source, which is essentially in the plane of that black arrow in the bottom figure there. So the parameters that we can put in, so we put in horizontal wavelength or wave number, intrinsic frequency or period, both of which are eminently measurable. From those, we can calculate the vertical wavelength or wave number and also the intrinsic horizontal phase speed. And with the background wind, we can convert the intrinsic horizontal phase speed to the ground-based phase speed. We can give the wave a propagation direction. We can give it a momentum flux, and we also give it a horizontal extent. So how many wavelengths is the wave packet made up of? How many wave cycles does the wave exist for? We need those for spectral width aspects of the saturation equation that we use from the Warner-McIntyre theory. But the key thing here is that we now have a way of making measurements of gravity waves at their sources and using those measurements to directly influence the parameterization scheme. The saturation amplitude for the waves using the Warner-McIntyre scheme is described on this slide. I won't go into it in too much detail, other than to say that the theory spans the full range of intrinsic frequency and vertical wave number, so we don't have to make mid-frequency assumptions. The key thing is that this sort of this long expression here contains a normalisation factor. So we'll just consider how that behaves. So that normalisation constant, it's chosen in the scheme such that if at a reference period, which is 1 hour, which is a sort of a mid-frequency gravity wave period, the current WACCM parameterization and the quasi-monochromatic version that I'm describing here would agree. So we kind of have a point where the two schemes are brought into alignment, and that's shown in the plot on the right-hand side. So the horizontal axis is the saturation level for the Linsen scheme, which is in WACCM, in standard WACCM, and on the vertical axis we've got the Warner-McIntyre 96 saturation level. The three lines are three different combinations of horizontal wavelength and phase speed for a whole bunch of different background wind values, and that gives you the range of saturation values. And you can see the three dots. That's where the where the methods are sort of tied together. So that's where they agree. That's where they fall on the y equals x line. You can see that for much of the range, the Warner-McIntyre scheme has a larger saturation value, but for some of the range, the Linsen scheme has a really much higher saturation value. To sort of speed up the process of considering how the two schemes work relative to each other, we've got an offline simulation thing going where we can define a set of source gravity waves, propagate those waves up through a set of WACCM wind fields, which are just output wind fields, so that it's not active in the model, and then calculate the momentum flux and the dynamical forcing that they would generate. And some examples of that are given here. So the body forces we have here are not directly comparable to the model body forces because in these simulations we assume that there's a source at every grid point. So there's some aspects of it that are going to limit the comparison, but certainly for internal comparisons, which is what we're doing here, they're fine. So these results are for the southern hemisphere for 4 different phase speeds. So there's a -36, a -6, a +6 and a +36 intrinsic phase speed, so phase speed relative to the background wind at the source. For July in 2020 in the sort of southern mid-latitudes for a 10 millipascal source and about 120 kilometre horizontal wavelength. And you can see that the two schemes, the red for the current WACCM and the black for the new quasi-monochromatic scheme, they agree pretty well for the small phase speeds in the centre, but the current WACCM gives a much larger forcing at the larger phase speeds, we can compare the response of the model to different source amplitudes as well. So here we have northern and southern hemisphere in the 2 rows, and a 25, a 5, a 5 and a 25 for different positive and negative large phase speeds. And you can see that the forcing once again is largest for standard WACCM. It tends to be highest when U bar is furthest from C. So when the local wind conditions make the U bar minus C value as large as the largest. And interestingly, the larger, interesting but not unexpectedly, the larger larger momentum fluxes break at lower altitudes or apply the forcing at lower altitudes than compared to the weaker forcing. One of the other aspects of this scheme is that we can introduce secondary gravity waves. Now, secondary gravity waves are becoming more and more observed in the last sort of 5 or 10 years, but are not currently included in the WACCM parameterization. We've added a secondary gravity wave capability into the WACCM scheme. We're just in the process of tuning it a bit. And it operates when a critical level is approached or when we get really large amplitudes. That creates a breaking level, and that breaking level then generates new gravity waves, which can then propagate away from the breaking level and go higher up into the atmosphere and influence the atmosphere further up. But the interesting thing is that the secondary gravity wave characteristics are dependent on the primary gravity wave characteristics, and in this scheme we know those primary gravity wave characteristics really well. So trials are still underway. The secondary gravity wave breaking tends to produce 2 upward propagating waves, but one of them doesn't tend to last, and the local shear environment defines which one is going to last. We use that to select the phase speed of the secondary gravity wave as well. All right, that's it. So in conclusion, we're developing and trialling a quasi-monochromatic gravity wave parameterization scheme. It has some advantages, particularly in the area of being able to bring observations into the model, but also being able to provide observations, gravity wave information to our observational colleagues. It enhances the realism of the parameterization, I think, and that's good. I suspect that it will make tuning easier, although one never knows, but talk to anybody who's tuned the gravity waves and it's the last thing that they want to do. So if it was to make the gravity wave parameterization less of a bane in people's existence, that would be a good thing as well. But we also have the capability to include secondary gravity waves. into the scheme, and that has some advantages in that they're conceivably an important factor in the whole gravity wave propagation story that needs to be considered going forward. Thank you.
Very nice talk. So in tuning the model, we always seem to be missing momentum deposition in the southern hemisphere. Does this approach help us in any way besides just making it simpler to tune, or
My guess is that the missing momentum flux in the southern hemisphere is probably coming from jets, and it's not inconceivable that those jets are in the stratosphere as well. So in a sense, it helps because the incorporation of those mechanisms is made easier because once they're identified, there's a clear path for including them. But I think, as I alluded to in that early slide, I think there's activity going on around the fronts that at present aren't being used to launch gravity waves, and I wonder whether that isn't a shortcoming. And if you look at the gravity wave activity around a belt around Antarctica, you can see there's an area where there's clearly very, very strong activity, but it's very in the pictures that are generated from satellite observations. It's very it's not a clear hotspot, but the thing is the sources are rapidly moving. So the fronts and the weather systems associated with them are rapidly moving along around Antarctica and the Southern Ocean, and as a result, the satellites, are always looking at a moving target. So they don't, like around the Andes, they see that as a really clear hotspot because they're always seeing it in largely the same spot, whereas the things that are going on in the Southern Ocean are always moving. So I think they are the key to the providing the momentum flux that's missing at those latitudes, but there's still missing information as to what's actually generating those gravity waves.
how does that affect just momentum deposition? Is it mostly in the mesosphere, or?
But there's some aspects of the WACCM scheme that I didn't really discuss here, where if you look at the amplitude of a wave with a momentum flux as it's put into the WACCM scheme at the surface, the waves are extremely small. If you look at that same momentum flux in the mesosphere, the waves are extremely large, and we have quite good observational capability in the mesosphere, and yet we don't largely see waves of that magnitude. So there seems to be a disconnect. And then if you do the same thing at the superpressure balloon heights, so the superpressure balloons are seeing, gravity wave momentum fluxes, as was in that plot, of 30, 40, millipascals or more, and they're way bigger than we're putting into WACCM. So if WACCM had available a step where a larger wave propagated some of the way, was turned into a new wave with a smaller amplitude, which could then propagate further into the atmosphere, I think that through that secondary generation mechanism, there's a way to sort of bring together the sort of slight sort of disconnect between the amplitudes of the waves as put into the model and as observed. So it's something that still needs to be tested, and we're still in the process of working out which primary gravity waves and which forcing characteristics are going to yield secondary gravity waves that will then propagate up to the mesosphere and have some influence there. So that's something that we're just currently working on with our offline system, but I think it's just something that makes a lot of sense. And when we're seeing extensive observations, of secondary gravity waves, you know, it's kind of indicated as well. Thank you.
Yeah, sure.
I think everything you show is like the offline calculation, right? How close are you to running something sort of interactive?
Times, but it's like raising your children. As soon as you get something that you know what to do, everything changes. And WACCM seems to be, you know, so but we sort of get it going, but then the underlying WACCM changes, you know, so we have to sort of rewrite it for the next version of WACCM. So, but yeah, look, the code is, Anne's been doing a great job recently too of tidying up my, you know, I send her Fortran errors and she fixes them. She's been doing a great job of dealing with that. But yeah, so we've run it before, and I think are, you know, close to being able to run it now. So that one of the key challenges is working out what parameters, how we convert the primary gravity waves into secondary gravity waves to get that part of the scheme working. And yeah, because that creates a path for the gravity waves to propagate through parts of the phase speed spectrum that are sort of not way out on the wings. And I think there's physical realism advantages in doing that. So we're getting there, yeah, and hopefully through my visit over the next few days we can make some advances and you know, the strategy for moving forward. Good idea, thanks.
So the last talk will be given online. It's Marcin Kupelis, and it's on a regionally refined WACCM simulation. You can hear us okay? Do you want to share your screen?
Can you see that okay? I couldn't hear if that was a yes or a no.
Yes, we can hear you.
Can you see and hear me okay?
We can also see the slides and hear you fine.
Okay, I guess I'll get started. So, yeah, thank you for coming to my online talk. We've had some really great talks in person. It would be nice to come along and be there in person someday as well. So today I'll be giving an overview of some of the work that we've been doing as part of the WACCM project here at Leeds, which has involved working with WACCM in general, with a large part of the project, now employing WACCM with regional refinement. And I will just jump into what motivates our work and then talk about some of the preliminary results that we have found by running simulations of WACCM RR. So it is possible that vertical transport in the MLT is too slow in GCMs that employ a standard eddy diffusivity gravity wave drag scheme, as can be seen from various evidence, such as, for example, in the whole atmosphere community climate model, species such as O and ozone have been shown at various points to be underestimated in the MLT, potentially due to an insufficient transport of these species down from the thermosphere. Similarly, temperature and minor constituents such as sodium and iron have been shown to be overestimated in standard WACCM runs in the MLT when compared to observations, potentially due to an insufficient vertical transport of these fields away from the mesosphere. So as we all know, that gravity waves form due to various atmospheric disturbances, and the important small-scale waves are usually parameterized as their effects are unresolved. And some previous work in our group on the Wave Chasm project involved tweaking the gravity wave drag scheme, as can be seen in Guarino et al., where Vittoria worked with Chester Gardner to include the effects of propagating, non-dissipating waves in the gravity wave drag scheme. Another way to study this problem would be to use higher resolution WACCM simulations. However, to resolve WACCM globally, it's obviously too computationally expensive. However, now with WACCM RR, we can resolve local regions whilst maintaining global coupling. So this is the experimental setup that we used. So effectively, we studied 2 model runs. The first being model run using standard spectral element WACCM, which I'll refer to as non-RR. This simulation employed globally 1 degree horizontal resolution and a vertical resolution in the MLT of around 2.5 to 3 kilometers. And this was compared to a model run that was run alongside non-RR, which was performed by WACCM RR, which I'll refer to now as RR. And this employed the widely used CONUS grid, which involves an 1/8 of a degree resolution over the contiguous US, a nested grid structure outside of that, and then outside of this nested grid structure is a 1 degree global resolution, where again the vertical resolution matches that of the non-RR run. The time steps have been adjusted in the RR run to satisfy the CFL condition. So whilst in non-RR we use 30 minutes, RR employs a time step of 3 minutes and 45 seconds. And just to get an idea of the theoretical cutoffs for the gravity wave spectrum, you can see them in this table here, which shows the theoretical cutoffs for the horizontal, vertical wavelengths and the minimum wave periods. So the 2 model runs that we studied were ran for the full year of 2010. We employed the free run historical ComSet FWM HIST. And for self-consistency between the models, and in order to avoid double counting on parameterized gravity waves and resolved waves in the RR run, the gravity wave drag scheme has been turned off over the extended CONUS domain in both models, which is shown here. And it's essentially, it covers all of the 8 degree resolution region and a portion of the nested grid structure. So just to show some of the things that we have been seeing. So here you're looking at temperature, time lapses over a 2-day period from the 1st and 2nd of June 2010. These are instantaneous hourly snapshots that have been just looped to show the time evolution. You're looking at 4 slices of the atmosphere, effectively from the troposphere to stratosphere, mesosphere and lower thermosphere, and the top are showing non-RR and bottom RR. And the first thing that strikingly jumps out is that there is clearly a very large spectrum of gravity waves resolved in RR that is not seen in non-RR. These waves appear very clearly concentric to be originating within the CONUS domain and are propagating outwards away from the domain with an apparent global background flow that is affecting the wave field in one direction. Some other features that can be seen, it's less clear in the temperature plots, but will become clearer in some future plots. But there are actually individual high temperature spots which seem to appear within the domain, and on close inspection they do appear to be linked to source regions in the higher levels of the atmosphere. So it's possible that there is some driving mechanism that is being picked up in the temperature, which is then being reflected in the spectrum of waves seen at the higher altitudes. In general as well, it's worth mentioning that the presence of these waves in the higher resolution model produces a hotter atmosphere as you go up to higher altitudes. So taking a look at vertical velocity, again, these are the same times over the same slices. And again, you can see that there is a very distinct and clear spectrum of concentric gravity waves seen in the stratosphere and mesosphere. And now it is much clearer than in the temperature plots that there are individual spots that seem to appear randomly at various points over the continent. And these points are locations of very large upward vertical velocities of up to 4, 5, even 6 meters per second. So clearly there are some activity in the troposphere which is causing convection, large updrafts into the higher layers of the atmosphere. And again, upon close inspection, it can be seen that where those spots are appearing are also regions where the concentric waves appear to have their source. Taking a look at nitric oxide, where here you're looking at the log of the mixing ratio. It is quite clear now, or at least the connection is quite strong, that the locations of high upward vertical velocities are associated with these spontaneously appearing high mixing ratios of NO, most likely driven by the lightning NOx parameterization of WACCM. So it appears that what we have done is been able to capture the generation of lightning due to storm activity, which is then causing large updrafts and large vertical velocities in the lower atmosphere, which is driving gravity wave activity at the layers above. So just to have a better idea of how things look as they change with height, here you're looking at odd oxygen mixing ratios between altitudes of approximately 75 and 130 kilometers. These are monthly means for the month of June, and the data has also been averaged over the extended CONUS domain, which again has been shown here. On the x-axis, you can see the mixing ratio, y-axis is pressure, and the upper x-axis shows the fractional difference between the two models, where the orange line is RR, blue line non-RR. So the first thing to note is that atomic oxygen is seen to increase essentially throughout the entirety of the MLT. Around mesopoles heights, this appears to be roughly around 25 to 30%, and that surplus is seen to decrease as you increase with altitude, and then that difference narrows down as you increase in altitude, where at the altitude shown here, there appears to be the beginning of some deficit of atomic oxygen. Taking a look at ozone, so this was averaged over nighttime, again for the month of June, and once more you can see that RR model is showing a surplus of ozone throughout the almost entirety of the MLT, where around the peak of the secondary maximum there appears to be an almost doubling, more than a doubling of nighttime ozone at this altitude, where again, just like for atomic oxygen, this surplus appears to decrease. There's a minor deficit, and then again there appears to be a surplus of nighttime ozone as you go even further up into the atmosphere. Some results for CO2 and CO, again same heights and averaging parameters considered, where however this time the black dashed line is showing the absolute differences between RR and non-RR. And what can be seen is that approximately below 90 kilometers, if we take a look at CO2 first, below 90 kilometers, the difference is almost negligible. However, above these altitudes, there is an increase in CO2 where around mesopause heights this appears to be around 20 to 30 parts per million, and this keeps on increasing as you go higher into the atmosphere, with a much more rapid increase seen in the lower thermosphere. Taking a look at CO, an opposite effect is seen in CO, where again below approximately 90 to 95 kilometers, the differences between the models are relatively negligible. However, above these heights, you see a decrease in CO, where around mesopause heights it ranges from 3 to a deficit of 3 to 5 parts per million, with the deficit growing as you then increase in altitude. And just returning back to NO and temperature to get a clearer look at this, where now the black dashed line for NO is the fractional difference, and for temperature it's the absolute difference. You can see again that NO has doubled in the mesosphere around mesopause heights, and generally has increased throughout most of the MLT, with the deficit also being seen as you go higher into the lower thermosphere. And for the temperature, there is surplus throughout, again, most of the mesosphere, with an increase of about between 10 and 15 Kelvin around mesopause heights, and then you see a very sharp temperature decrease as you go into the lower thermosphere, which gets greater as you go to higher altitudes. So just to conclude and summarize, so as we've talked about today as well, we know that unresolved gravity waves are usually parameterized. There is ongoing work to try and improve the parameterizations, and recent work in our group has shown an example where this was successful, where propagating non-dissipating waves were included as part of the gravity wave drag scheme. We now also have the capability to model gravity waves using WACCM RR, which can resolve smaller scale waves down to as far as 10-kilometer horizontal wavelengths, 6-kilometer vertical wavelengths, and 8-minute periods. To test WACCM RR and the effects of higher resolution, we simulated 2 models. This was the WACCM standard spectral element WACCM with 1 degree resolution globally, and WACCM RR with 8 degree resolution over the contiguous US, 1 degree everywhere else. And we saw a significant amount of wave activity resolved in RR, and this can be very clearly observed in various fields such as temperature, vertical velocity, and NO, and very strong connection can be made between say the effects of the lightning knocks, parameterization scheme, locations of high updrafts in vertical velocity, and then concentric expanding gravity wave activity at higher altitudes. So there is a clear link between small-scale variability, especially down in the lower atmosphere, and gravity wave activity in the upper layers. And we can see some of the more persistent global effects, such as an increase in oxygen and ozone, an increase in CO2, and a decrease in CO in the lower thermosphere. So going forward, so far we just have these preliminary results, which have raised a lot of questions, probably more questions than answers. So we would very much like to specifically quantify exactly what the vertical transport fluxes due to gravity waves, resolved gravity waves are, and to quantify the extent that these fluxes are causing the differences we have seen, and then also to be able to quantify in detail the spectral characteristics of the gravity wave field that we have seen, and connect this to the dynamics. So yeah, I would just like to also acknowledge some of the other project partners that have been involved, especially Nicholas Davis, who actually performed those heroic runs, working with Dan Marsh whilst he was still at NCAR, and other project partners that have been involved in gathering observational data. So I'll stop here and I'll take any questions.
Very interesting talk. Thank you very much. Just a quick question: is this is probably the version 2.2 of WACCM, and is it the 70-layer vertical? Is that correct?
It was 110 vertical layers that we used, and
110 vertical layers is what you used. Okay, that makes sense. Yeah.
the specific tag we used to run was CAM62011. So I don't know off the top of my head what version of CSM that is, but that was the tag that we used to perform these runs. I believe there are a lot more modern tags that can be used these runs now, but that's what was done at the time.
More about the source of these gravity waves. I think you identified that they're sort of associated with individual convective elements. You know, what kind of storms are these?
Close to the mic, sorry.
Okay. I was wondering if you can comment a little more on the source of these gravity waves. You had mentioned that they were due to, you've identified that there's sort of individual convective elements. And so what type of storms are these? Have you looked into that?
So we have looked in detail at the types of storms that are forming. The only thing that we can say with confidence at this point is that there appears to be a clear link between regions of high NOx production, likely due to the lightning NOx parameterization scheme, and then convection arising from that. So that is still something on the agenda to look in detail at the sources of these waves and then characterize the spectra at different altitudes. Specifically, which I didn't mention, is because that we do have reasons to believe we have managed to capture a secondary gravity wave driving, because at much higher altitudes in the lower thermosphere, we're also seeing very distinct and narrow concentric rings forming, similarly to the ones that form in the stratosphere above the convective regions. So it's interesting that such small wavelength concentric rings are spotted at higher altitudes in the lower thermosphere. So it is, yeah, it's on the agenda to characterize in detail what the sources are doing in the troposphere, but also potentially in the MLT.
Very nice talk. We've always underestimated the ozone abundance in the secondary maximum. And from this work, is that coming from bringing OATM down in some way? Or do you know why that happened?
There is a lot of atomic oxygen that is being transported down from the thermosphere. But the exact reason why ozone is seen to increase by up to factors of 3, we don't have a definite answer for that, exactly what's driving those changes. But yes, we can say with confidence that a lot of atomic oxygen is being brought down from the thermosphere.
Yeah, well, very nice result. Thank you.
Thank you.
Thank you again, especially for staying up, I think, a bit late to give the talk in the evening in the UK. So we have 2 minutes left for discussion, so I think we will conclude this session here, and we have lunch break for 1 hour, and then the second half of the whole atmosphere working group session will be begin at 1:30 this afternoon.
Mic test.
There's, I think, zero control here. There's none. Okay, why don't we restart the whole atmosphere session for the afternoon. So first talk is by Doug Kinnison on the updated solar forcing for CMIP7 and the impacts on WACCM simulation. Could you please bring up the slides?
Thank you and good afternoon. Today I want to talk about the new CMIP7 solar forcing. And does that work? Yeah, okay. And I want to first acknowledge my co-authors, Dan Marsh, who's at the University of Leeds, used to be an ex-CGDer, and then Simone Tilms, who's probably in the audience, who's done a lot of help with me getting the model set up. And also I want to acknowledge Sean Honemichael and Jun Zhang for some figures in this talk. Okay, so today's talk, I'm going to talk about the solar forcing input, and this is it's basically a new solar spectrum, and I'll show an example of that has been given to CMIP and will be used in the assessment, and it goes from the UV into the IR. In fact, it goes much beyond that. And we'll show differences between two simulations with WACCM, and I'll describe those. One with the new CMIP7 forcing, and also one with the CMIP6. And these, or version of WACCM, these will be two 60-year simulations. I'm going to examine some stratospheric chemistry, will be one point I'll make, and I'll also show one example of a tropospheric impact from changing the solar forcing. And then some conclusions, and that'll be it. So I think everybody knows that the sun has a solar cycle, 11-year solar cycle, and it varies depending on, the year. In fact, in 1850s, the cycles tends to be a little bit bigger than it is the last two periods here. The pre-industrial control, just as a note here, will use these two cycle 10 and 11, and the mean of these, the average and the mean of these for the pre-industrial control. And so as the sunspot number changes, this changes the sun's magnetic field, and you end up getting different amounts of UV invisible radiation that comes in. And this is an example over here of the change over the cycle. So this is a ratio. And so 1 is no change, but you can see in the UV here from 100 to about 250 nanometers for this one cycle, cycle 24. You can get anywhere from 20 to 30% change at 100 nanometers versus no change when you get into the visible. If you're interested in learning a little bit more about the role of the sun on the middle atmosphere chemistry and dynamics, I highly recommend you take a look at this paper by Ward et al. It's really a nice paper, great review paper. Okay, so this is some data here. The top is the TSI. This is change in TSI for the last two cycles, cycle 23 and 24. That's maybe peak-to-peak changes are on the order of 10% difference in the TSI between these two cycles. But this bottom one is actually for one wavelength. It's the Lyman alpha line. So this can vary as much as 50%, 30 to 50% going from one cycle to the other. And that's again shown in this figure over here, how variability it really depends on wavelength. But that's not what I'm going to talk about today. I just wanted to get that out of the way because a lot of times people are thinking I'm talking about the change in the solar cycle, but I'm not. I'm talking about this one point right here in December 2020 where we have a reference spectrum that was measured in the atmosphere with very high accuracy and precision. I'll talk about that next. But this spectrum basically is a little bit different than what was in CMIP6. The structure is different and there's more energy now in the visible than in the infrared. And that can affect both the chemistry and the climate. In fact, this spectrum is called the Total Spectral Solar Irradiance Sensor. It's an instrument that was on the International Space Station, and you can read about this in the paper by Coddington et al. 2023. What I'm going to be showing again is the quiet sun component of it. Oops, wrong way. There we go. And so it's just a solar min case in December 2020. And the same period in December 2020 for this new CMIP7 spectrum will also be derived from what we had in CMIP6. And so we're going to run two simulations. The only thing we're changing is the solar input, and we're going to see what impact it has on the chemistry and climate. The model we use is a very fast version of CSM2 WACCM 6. This is a version that Mike Mills put together for the last CMIP 6 assessment. It's a 2-degree model, 70 levels, goes to surface 140 kilometers. It has interactive middle atmosphere chemistry. It doesn't have detailed tropospheric chemistry, but it also has an interactive ocean, deep ocean. And we're just repeating year 2000 conditions for greenhouse gases and equivalent effective stratospheric chlorine. So the chlorine-bromine loading is essentially the same for 2000. It doesn't change. And we ran the model for each different solar input 60 years, and we created climatologies for the last 50. So what are the differences we see in the solar spectrum? So see if I can get pointed. This is wavelength down here. It goes from 100 nanometers to 400 right here. And this is the difference in percent between the CMIP7 minus CMIP6. And what you see in this region here in the UV, you see anywhere between 5 and 10% changes here. Now, I've also put on here important bands for O2 photolysis and ozone photolysis. And for the Hartley band, that'll be really important for ozone, and I'll discuss that, so you should remember that. And then for the Schumann-Runge band and Hertzberg continuum, that's important for O2. So again, what we're doing is we're moving energy, the shape of the spectrum changed, so we're moving energy that used to be in the near IR, and now it's in the visible, and there's consequences for that. If you look at where the heating rates are in the atmosphere, this is just a classic figure from Brasseur and Solomon, and that ozone is the most important heating rate species in this region of the atmosphere, so from 20 to 80 kilometers. And in that region, ozone has absorption in the Hartley band, which is this big band right here that we're seeing this increase in 5 to 10% by just shifting the reference spectrum. So what does that cause? Well, you can see that on the left here, it's the shortwave heating rates in Kelvin per day. So this is the difference between CMIP7 and CMIP6, and it's on the order of about 0.3 K per day. So you say, so what? Well, this is about 2 to 3% of the total heating rate in this region, so it's not insignificant. If you look at what impact this has on temperature, of course, if you increase your heating rates, you're going to get warmer. It's about a 1 K difference in temperature between the two climatologies, with CMIP7 being, again, warmer than CMIP6. This difference in temperature you can put in perspective. It's like going from solar max to solar min in the change in temperature. So again, it's not insignificant in the kind of science studies that we do. So what impact does this have on chemistry? Well, on your left here you can see a difference between the CMIP6 excuse me, just the CMIP6 ozone abundance here, so this is in parts per million, goes from 100 hectopascals to 0.01. And you see the classic shape of ozone in the stratosphere. You got 10 parts per million at 10 hectopascals, and decreasing as you get into the upper stratosphere and mesosphere. If you look at the difference between the two simulations, the two climatologies here, you can see that you have regions where it increased by 3%, you have regions where it decreased by 1%, and then you have regions where it increased by about 1.5% and 2%. So the question is, first, why is it decreasing? And that's pretty straightforward. What we noticed is that, remember, the Hartley band is being enhanced, and so you're getting more photolysis of ozone here. I can get my cursor down here, yeah. And so ozone forms more O singlet D. O singlet D reacts with water in the upper stratosphere, lower mesosphere, and it produces OH. And this OH enhances the catalytic cycle that depletes ozone. So OH plus ozone goes to HO2, HO2 plus O goes back to OH. This cycle can go 100,000 times before it falls apart. And you really get a little bit of depletion, 1%. It's interesting, and again, this is probably the same kind of difference you're going to get going from solar max to solar min. But this, again, is just an offset. This is just the two reference spectrums are different between CMIP7 and CMIP6. So what's the other increases? The other increases, again, have to do with O2 photolysis now and heating. You have enhanced O2 production of O atom in the Hertzberg continuum, and you'll have enhanced production of O atom from the Shimoga bands. And the combination of these give you these positive increases in ozone above and below the stratopause. So that's kind of standard chemistry, and we figured that out pretty quick. Let's now move a little bit to the near infrared, and this is a change in the near infrared. Remember, I've been telling you that spectrum had a different shape, and if you look at the difference between CMIP7 and CMIP6, in the near infrared, it's about 2.5% lower than in CMIP7 than it is in CMIP6. And this is over a pretty broad wavelength range. This goes from 800 nanometers out to several thousand. And this difference then is going to have impacts by moving this energy into the visible, has impacts on climate. So a really nice paper that came out in 2021 was from Jing et al., Journal of Climate. And one of the things that they talked about in this paper was the surface albedo sensitivity. And if you look at this here, there's three different surfaces that they looked at for this figure: the barren desert, fresh snow, sea ice, and ocean water. For this study, I'm only going to talk about the blue line here, which is sea ice. And notice that in the near infrared, there's very little reflectance of energy from the surface upward. In the visible, there can be quite a bit of reflection. And so if you're moving energy from the near infrared into the visible, you're actually removing energy from the near surface conditions, and you can actually cool the surface by this just changing the reference spectrum. And this is what they found in their model runs too. Now, one thing about this simulation, we're kind of doing a check on it because their simulation was a low-top model without chemistry with a slab ocean, but it was CSM2. So and they did essentially the same experiment we're doing, a little bit different the way they set up their ensembles. But the question is, do we get the same effect on sea ice? And that's the question here. So in their figure here, you have surface temperature. This is a reference for the annual average zonal mean. This is the reference for the sea ice fraction in that model. So they have more sea ice fraction in the northern hemisphere than the southern hemisphere. The difference in their simulations showed about a 0.5 degree cooling in the southern hemisphere between the CMIP7 and CMIP6, and about 0.4 K cooling in the northern hemisphere. The consequence of this, due to that albedo effect, is that there was about 2.5% more sea ice extent in the southern hemisphere and about 0.75% in the northern hemisphere. Now, this is a zonal, annual average zonal mean, And so maybe that's not the whole picture. But if you go to what we did, same thing, same reference temperature and sea ice, same kind of conditions. But in this case, we get a little bit less cooling in the southern hemisphere. I don't know if that has to do with that we're using an interactive ocean, deep ocean, versus our slab ocean and how that couples to the sea ice model or not, or something different about the way they did their ensembles versus our simulations. The northern hemisphere looks about the same. It was about a 0.4 K cooling. But the difference between what they got is and what we got is we get less of an impact now because of less of a temperature effect in the southern hemisphere for sea ice fractional increase versus the 1.5%. So if I can go back, so again, they got a bigger effect. We got a smaller effect in the southern hemisphere. If you want to look at this from a pure polar projection point of view, this is also helpful. So here you have sea ice fraction on the top row, temperature on the bottom, southern hemisphere on the right, northern hemisphere on the left, and the hash marks are statistically significant differences between the two simulations. And if you go to the southern hemisphere first, you can see where, I think I lost my pointer. In the southern hemisphere, where it's statistically warmer, you have less sea ice expansion, and when it's colder, you have more. And that makes sense, of course. In the northern hemisphere, mostly what you see is it's typically increases in sea ice fraction everywhere. You have temperatures on the order of 0.75 maximum. But what's really interesting, you know, in the Labrador Sea area here in this region, there is some enhancement. And I know CSM2 has had trouble, and maybe CSM3 will too, with freezing of the Labrador Sea. And so I think this is one of the concerns when you switch in this new solar forcing, and it might kind of be a tipping point in a sense to push the model into a regime you don't want. You have to do some more tuning. So this will be important to get this solar file and get it into the development tuning branches of CSM3. So that's really all I had. So in summary, the shortwave heating and temperature increases through the middle atmosphere, mainly from ozone photolysis. Ozone increases in the middle atmosphere, middle mesosphere and lower stratosphere from O2 photolysis increases, and both in the Schumann-Runge band and Hertzberg continuum. You see ozone decreases near the stratopods, which is due to ozone Hartley band photolysis of ozone forming O singlet D, reacting with water forming OH, and then getting more catalytic ozone loss. And we also get a sea ice albedo effect, same as Jing et al. It's a little bit different. I don't know who's right or wrong, or we'd have to really dive into this if we want to know the differences. But when you move the energy from the infrared into the visible from the spectrum, you can scatter more of that energy out because of the albedo effect, and you get a cooling and you get more sea ice extent. So I found this as kind of a really interesting study, just something like just changing the reference spectrum for CMIP7 relative to what was used in CMIP6 would have this kind of effect. And this effect is really at the same magnitude as what you see going from solar max to solar min for temperature and ozone change. So finally, it's time to start thinking about getting the solar data. It's now available on the Solar HEPAS webpage here. We can get the PI control and probably make it available next week. We'll have to figure out how to create the file again. We had some turnover with people in WACCM, and so the folks like Mike Mills, who used to do this, is retired, so we'll have to do that now. But we're ready to do that. The TSI, according to Dan Marsh, is not that much different than what was in CMIP6 for the pre-industrial control, and it was 1371. And basically, that's all I have. And so we'll follow up on this with CGD and try to get this moving forward with the new solar file. So if you have any questions, open.
So yeah, this is really interesting and clearly has an implication for our tuning of our pre-industrial control runs, which we're all actively doing. So I was just wondering, is this feeding into the kind of CMIP task team in terms of other models being aware of the implications of this for the pre-industrial in particular? Obviously, we're all kind of waiting for the new forcing data sets to come online, but I'm thinking that stuff that impacts the PI is of, high importance for us at the moment.
Groups that are part of the solar task team that are modelers in Europe and in the U.S. So I think they already know that this could be a potential problem. I gave this talk at EGU also, and we'll continue to, promote this and let people know that there has been a shift in the spectrum, so they don't get surprised. Okay. Yes.
Very nice talk. I just have a question. Every few years there's like an additional solar spectrum measurement that comes up. When I was doing my PhD, most of the measurement came from the UCAR measurement. That was the small solar cycle. Then the source measurement came in, and everyone's like, "Oh, this is so much bigger." And that was an extra experiment. So do people have a consensus which one of the measurements is actually right?
TSIS data is, I think the instrument that was on the ISS is, got really good precision and accuracy. And so I think it's kind of the state of the art now. And I doubt it will change, but you never know. But they've been measuring this stuff for a while, like you say, and they keep changing it. But this is the best they have available for CMIP7, so they're going to go with it. Yeah.
Should be, or what the spectrum should be, which measure, which instrument is the most trustworthy.
ACP, they go into a lot of detail about that, and I think that'll give you kind of some insight on where we came from and where we're going. But yeah, I would check there. Yeah.
Online question. I'm just going to read it from the chat. Shouldn't the TSI be 1361W over M2? Say that again? Shouldn't the, I think I'm pronouncing this right. Shouldn't the TSI be 1361W over M2? This is from Alan Robach online.
It's just a number right now, so we haven't, yeah. And in fact, I almost didn't want to put that up there because I hadn't validated that number. Dan Marsh sent it to me, so we can blame him. But yeah, I would maybe not worry too much about that number right now.
Is by Jun Zhang, and she presents on the Hunga Tonga eruption and impacts on the stratosphere ozone. So this, do you know how to work?
I think so.
That's advanced, and that is the pointer.
That's a pointer?
Yeah.
Oh, okay. Hi, everyone. I'm Jun Zhang. I'm a project scientist at ACOM. Today, I'll be presenting the stratospheric anomalies after the unprecedented water-rich Hunga Tonga eruption. So I'm very interested in how the chemical composition changes after the Hunga Tonga eruption. So originally, I put together a very chemistry-focused talk on how the Hunga Tonga changed the ozone chemistry and chlorine chemistry. But then I realized, given the mixed interest of people here, I also added some results on how the Hunga Tonga changed the radiation, temperature, circulation after the eruption. And those part of study are done by Xingyue and Bill. And I also would like to acknowledge the help from Doug and Yunqian and Simone in general. And so Hunga Tonga, Hunga Hapa volcano erupted in January 14th, 2022. In a island country called Tonga near, in the southern hemisphere near Australia. So this is one of the most explosive volcano in the 21st century, and extends volcanic material all the way up to 58 kilometers in the mesosphere, and has attracted a lot of global attentions. And one of the very special, Hunga Tonga is very special because it's an underwater volcano which brings about 150 teragram water into the stratosphere, and this accounts for about 13% of total global stratospheric water mass. So this large water and SO2 injection and in a dynamical perspective can change the radiation and the temperature and the circulation in the stratosphere. And in a chemistry perspective, this additional large source of water can increase the hydroxyl radical and enhance the Hawkes ozone loss cycle. And in addition to that, the SO2 injection forms sulfate aerosol and enhance the aerosol surface area density and facilitate heterogeneous chemistry. And all of the above can influence stratospheric ozone. So here I'm showing you the 2022 ozone anomaly relative to climatology from satellite Aura MLS microwave limb sounders. And it shows the 2022 ozone minus climatology from 2007 to 2019, 13-year climatology mean. And here the hatched region indicates where the 2022 anomalies are outside the range of all variability during the past years, means it's something we have never seen before. It's higher or lower than all the past years. There's two highlights. One is in the Southern Hemisphere summer, June, July, August, there's record low ozone near the middle latitudes. And in the fall, there's also a large anomaly over the polar region. And the question we wanted to answer is, what is causing this ozone anomaly? What is the role of chemistry versus dynamics here? To answer this question, I conducted simulation used WACCM 6, 110 level with horizontal resolution of 1 degree and the vertical resolution of 500 meters in the upper troposphere and lower stratosphere, and includes full interactive troposphere and stratospheric chemistry. And the simulation here are notched the temperature U and V winds towards Mera-2 reanalysis fields. And the simulation started from 2007, goes all the way till the end of 2022. And starting from January 2022, two simulations are conducted. One is the volcanic case, where I include all the water vapor and SO2 injection from Hunga Tonga emissions. And there is also a control case where we consider no Hunga Tonga emissions. So by doing this experiment, it allows us to do two things. First, I can use the volcano case in 2022, which mimics the realistic situation, to minus the climatology from all the past years. This allows us to have a direct apple-to-apple comparison with satellite data. And second, I can also take a difference from volcano case and control case. Since those two cases are notched to the same dynamics, the difference we derived here, we can consider it as chemistry only influence. Here we're looking at the water vapor and aerosol plume evolution in 2022. The red shading, contour shading is water vapor plume, and the red contour lines aerosols. On the left is observation, right is from WACCM simulation. You can see that the water plume propagates from Southern Hemisphere subtropics, where the eruption happened, to the high latitudes in 2022. And we also see a clear separation of water vapor and aerosol plumes over time. In general, they are co-located near the subtropics, but as the water ascends and aerosol descends, and there is a clear separation. And WACCM captures both the magnitudes and the propagations, and also the separation of the plumes very well. So now I'm showing this MOS ozone anomaly again. I showed it earlier, but this time I have the WACCM results on the right for comparison. And you can see that WACCM shows very good agreement with MOS across the whole year. And it captures the main features that in the winter, June, July, August, there is a May record low ozone and also the large ozone anomaly over the polar region in winter, in the fall. There's another way to look at this ozone anomaly, and the left figure here shows the ozone at 30 hectopascal over the subtropics and the mid latitudes. The gray lines here are all the past years ozone mixing ratio from MOS, and the black line is the mean from all the past years. And the red and the blue lines are from MOS and WACCM 2022. You can see there's a large spread in the winter due to QBO variation, but you can see that in 2022, the ozone level here is completely outside of the variability here, showing a record low ozone. So in the polar region, in 2022, the ozone is relatively low compared to climatology, but it's not the record low. Now I'm trying to quantify the chemistry contribution to the ozone changes here. This shows the same ozone anomaly I showed earlier with the movie. Left is MOS and right is WACCM, but I took out August and October for illustration for the two features over mid latitudes and the polar region. So we call this ozone anomaly full impact because we derive it using the 2022 minus climatology from the past years. And when we do that, the anomaly here is from the combination of the 2022 QBO and the Hunga Tonga force changes, because the climatology means smooths out all the past year QBO. So left out the influence from 2022 QBO and also the force change from Hunga Tonga. This force change includes both the dynamic change and the chemistry changes, and all of them can influence the ozone. And on the right here, I'm showing the results from the two notched cases. The difference here is showing mostly from chemistry because the two cases are notched to the same dynamics. So it's mostly this part, the chemistry due to the Hunga force changes. And those plots have different scales. So the changes, the four changes are, the chemistry changes are only account for about 30% of the four changes in the mid latitudes and the polar region, and the remaining of the ozone changes due to the Hunga Tonga induced dynamics and also the 2022 QBO effects. And now I'm going to show some WACCM free running results that Xingyue has done, and almost all the results are showing in her paper. So 10 ensemble volcano case and control case were done for 10 years to look at the impact of Hunga Tonga. And so she looked at the radiation impact from water, SO2 plus water vapor and water vapor only and SO2 only. And you can see that the water vapor up there cools the stratosphere while the aerosol warms the stratosphere. And those changes are mostly from long wave radiation. And those change in radiation pattern would further change the temperature in the stratosphere. So here the spaghetti plots, the gray ones showing all the past years, and the black line is the mean. And the 2022 is the red one. You can see 2022 is completely fall out of the past year variability, but it slowly goes back to the mean level in early 2023. And here it shows the zonal mean temperature change in August from MLS. You see there's a large cooling in the middle latitudes. But again, this is the 2022 anomaly, which is the combined the effects from the QBO in 2022 and also the forced Hunga Tonga. The question is how much this anomaly here we see is actually due to Hunga Tonga. And here I'm showing the model results. It's showing the difference from the volcano case minus the control case from all the ensemble simulations. So you can see clearly there's a similar patterns in the temperature here, cooling over, a strong cooling over here due to Hunga Tonga. And this shows a clear fingerprint of the forced response due to Hunga Tonga eruption. Okay, the temperature change also caused the circulation change in the stratosphere. And here I show the era 2 August U wind anomaly. Here you can see a large negative U wind anomaly over here and positive over here. It indicates that the equatorward shift of the Antarctic polar vortex. And in addition to that, we also see the Brewer-Dobson circulation is weakening, which can be partially contribute to the low ozone in the middle latitudes here, because usually the Brewer-Dobson circulation, this branch, brings ozone-rich air all the way to the upper latitudes. But the slowdown of this branch brings less ozone-rich air here, so resulting in a low ozone level at this latitudes. So the last movie I want to show is the Hunga Tonga water plume evolution from the eruption year all the way to 2025. So as for now, 2024 June, the water are well dispersed in the stratosphere and the mesosphere. And by the end of this year, the enhanced water would be less than 1 ppMv, and it will be slowly phased out in the next few years. And the majority removal process is through the dehydration in the polar region. Okay, in summary, Hunga Tonga eruption in January 2022 caused persistent stratospheric water and aerosol plumes and caused a large impact on temperature, circulation, and ozone. And there's a large-scale southern hemisphere stratospheric cooling and eastward shift of Antarctic polar vortex, and also slowing of the Brewer-Dobson circulation. We also see persistent ozone reduction in the southern hemisphere winter middle latitudes, and also large spring Antarctic ozone loss in 2022. And WACCM 6 simulation accurately captures evolution of the volcanic plume and also the record low ozone level at the middle latitudes from the eruption. And the majority of ozone depletion can be attributed to the internal variability from QBO and also dynamic changes induced by the eruption. Okay, so lastly, I wanted to mention that as this spark activity going on, basically it's an intermodal comparison efforts. And right now we are about here. We're almost, WACCM is part of this, of course. So right now we are here. We finished all the simulations and I'm in the process of analysis those results. And there's a report on the Hunga Tonga assessment will be out in June next year. And this efforts will be mostly focusing on the following science theme: plume evolution, dispersion, and large-scale transport, and also the impact on stratospheric aerosol and ozone layer, and also radiative forcing from the eruption and surface climate impacts. Okay, that's all. Thank you.
Thank you. It's very cool to see that the ozone changes are captured so well. So is this with fully coupled WACCM?
It was coupled ocean.
Dessler that came out, I think 2 weeks ago, where they claimed that in GIS, they actually see a small cooling after Hunga Tonga rather than a slight warming, as you would expect. So I'm curious if you've looked at that.
But I remember Xingyue and Bill, they looked at it, and I think that agrees with what you said. They actually see cooling instead of originally we think there will be a warming because of the water vapor up there. So I find it's very interesting. Thank you for the question.
So next talk is given by Eva Bednars, and it's on the stratosphere aerosol injection and the impact on the AMOC.
Okay, hi everyone. So I'm Eva, I'm a research scientist at NOAA CSL, and yes, I'll talk about something slightly different, so stratospheric aerosol injection and Atlantic meridional overturning circulation. How do I make the... okay, yep, I worked it out. So stratospheric aerosol injection is a form of geoengineering done through the injection of sulfate aerosol precursors, usually SO2, into the stratosphere, lower stratosphere, and all of that in order to reflect a portion of the incoming solar radiation and thus cool the surface. And this effect is thus parallel to the impacts of large explosive volcanic eruptions like the Pinatubo eruption, not Hunga Tonga eruption, but like the older classical Pinatubo eruption. And okay, so I'm gonna talk about Atlantic meridional overturning circulation. I realized this is the whole atmosphere session and my results will mostly be focused on the surface, so I'll try my best to explain everything as much as I can. So Atlantic meridional overturning circulation is a crucial part of the ocean circulation, what we call the ocean thermohaline circulation. It consists, is there a pointer? Oh, yeah. It consists of warm tropical waters being carried near the surface to the North Atlantic high latitudes, where they become colder and denser. And those dense cold water then sink near Greenland to the lower parts of the ocean. And once they are in the lower parts of the ocean, then continue moving southward and resurface somewhere near in the southern parts of the North Atlantic, of the Atlantic. And as such, AMOC is important as it redistributes heat, it redistributes carbon and nutrients around the Atlantic region. And so it plays a very important part of the climate system in general. Now, however, models, as we've seen before in the session this morning, if you were there, models generally project AMOC is going to substantially decline over the 21st century under raising greenhouse gas levels. And this is shown on the plot here. We have a collection of different CMIP6 models under different emission scenarios. And this might be slightly difficult to see, but the different emission scenarios are given by the different thickness of each line. And don't worry about the details. The main point I'm trying to make is that in general, all models show decline in AMOC strength throughout the 21st century, although there are clearly some important differences in terms of both the climatological AMOC strength and also how much decline the individual models project to happen over the next few decades. Now, coming back to SAI, various studies look at whether SAI can actually help prevent AMOC decline or not. And in particular, there are 2 large ensembles of SAI simulations that NCAR produced with CSM over the last few years, well, 5-10 years, which you might have come across, and Peter Lawrence talked about them a little bit, mentioned them earlier in his talk this morning. So the first one is called GLANCE, and it was run with CSM1. And the second one is called ARISE 1.5 or ARISE SAI 1.5, and it was run with CSM2. Both use WACCM and a very similar SAI setup in which SO2 is injected at 4 latitudes with the aim of minimizing changes in global mean surface temperature and its large-scale gradients. Now, even though those 2 simulations, well, those 2 experiments have very similar SAI setup, they differ. First, in terms of the model version that was used, the CSM model version that was used, and also the underlying greenhouse gas scenario. So GLANCE used the high-end RCP 8.5 scenario, and ARISE used the more middle-of-the-road SSP2 scenario. And because of that, the 2 ensembles used different amounts of SO2 injections. They had different amounts of cooling. They used different amount of SO2 injection. They also partitioned the SO2 injections differently across the 4 latitudes. And this is shown the plot on the left-hand side. This is the SO2 injection rates at each of the 4 latitudes. Don't worry, I just want to alert you to this point now that there are differences in the SO2 injection distribution. Don't worry about the details, I'll come back to this later. What is important for now is that here are the simulated AMOC changes in those simulations. So first, under climate change alone, the gray line, well, which is the line, this is the gray line. I know my colors are not very helpful, but this is the gray line. This is the RCP 8.5 simulation with CSM1. And the black line below it is the SSP2 simulation with CSM2. And we see that there are clear differences in the climatological AMOC strength between CSM1 and CSM2. What I mean by that, if you look at 2020s and 2030s, AMOC, so in the near present day kind of period, AMOC is actually stronger under RCP 8.5 than under SSP2. And this is contrary to what I've just told you, that we expect AMOC to be actually weaker under higher greenhouse gas levels. And hence this difference in basically the black and gray lines, so the climatological AMOC strength is very likely due to ocean model differences between CSM1 and CSM2. Now, despite those differences in ocean model physics, both greenhouse gas simulations generally show AMOC decline from at least 2030s onwards. Now, the interesting thing is what happens under SAI. So in GLANCE, which is the yellow line, SAI results in a very clear recovery of AMOC, with AMOC strength consistently strengthening throughout the length of the simulations. And in contrast, in ARISE, so this is the green line, SAI doesn't really do much to AMOC, other than maybe slightly slow down the rate of its greenhouse gas-induced decline. Now, in a paper from NCAR colleagues from last year, it was argued that this is the differences in ocean model physics and ocean climatological states between CSM1 and CSM2 that are the dominant drivers of the different AMOC response to SAI between GLANCE and ARISE 1.5. And what I want to do in the remainder of my talk is to argue that while detail of ocean model physics and climatology are definitely important, I'm not going to disapprove that. However, whether or not SAI can actually restore AMOC or just barely slow down its greenhouse gas-induced collapse depends strongly on the details of SAI realization. So I'll do that using a set of idealized SAI sensitivity experiments. So these are not meant to represent plausible SAI scenarios, but instead help our understanding of processes and mechanisms. And these were run with CSM2, with WACCM in its middle atmosphere chemistry configuration that Doug was using before in his solar spectrum talk. And in particular, there are 7 simulations which with constant rate of SAI for 35-year long, with SO2 being injected in the lowest stratosphere only at a single latitude. And we are talking either 45 degrees north and south, 30 degrees north and south, 15 degrees north or south, or the equator. Now, the plot here shows the simulated distribution of sulfate aerosols in the stratosphere. So in the injections in the northern hemisphere at the top, injection in the southern hemisphere at the bottom, and the equatorial injection is on the right-hand side. So we see, first of all, that in general, the aerosol clouds tends to maximize in the stratosphere near the location of the injection. This is especially the case for the tropical injection, so the equatorial injection and the 15 north and south injection. And this is in that cases, the aerosols are locked inside the tropical pipe. And the other important point I'm trying to make is that if you inject aerosols only in one hemisphere, the aerosols tend to stay in the hemisphere of injection with little crossover to the other hemisphere. Now, this is the plot that combines all of that information. This is the simulated Northern Hemisphere extratropical aerosol optical depth in those simulations as a function of time. And what I mean by extratropical in this case, I mean anything poleward from 45 degrees north onward. So consistently with the previous plot, we find that injections farther north in the Northern Hemisphere lead to the largest Northern Hemisphere extratropical AOD, so that the AOD is generally highest for the injection at 45 degrees north, followed by 30 degrees north, and so on. And you can also see that in general, the injections in the Southern Hemisphere do not impact Northern Hemisphere AOD much. And maybe the exception is the injection at 50 degrees south, which is the light blue one. You get a small-ish in this context, AOD changes of like less than 0.1 that are still important. Okay, so here is the simulated AMOC evolution in those simulations. So in black is the control SSP2 simulation. We see this long-term decrease in AMOC strength under rising greenhouse gas levels. And under SAI, first, if you inject in the Southern Hemisphere only, and this is different blue lines, we see that SAI causes only a small slowdown of the AMOC decline that is projected from the greenhouse gas case only. And this is the case for the injection at 50 degrees south, so this is the light blue line. You could argue that if you look at the 45 degrees south injection case, the dark blue line, the AMOC doesn't really do anything to SAI. In this case. Now, if you do SAI at the equator, so this is the yellow line, AMOC actually no longer declines, but stabilizes at roughly constant levels. And if you do SAI in the Northern Hemisphere, so this is the different red and orange lines, AMOC actually starts to increase very noticeably throughout the simulation length. And the other thing you can notice is that in case for the Northern Hemisphere injections, all of the Northern Hemisphere injections actually restore AMOC to roughly the same level. And this was surprising to us. We are still working on understanding because this is despite the clear differences in the AOD in those simulations that I've shown you on the previous slide. Okay, now, coming back to our large SAI ensembles that NCAR produced. So on the right-hand side, I've got the simulated distribution of aerosol cloud in glands and arise. So in glands, which is shown on the top, there are lots of aerosols everywhere in the lower stratosphere, but there's more aerosols in general in the Northern Hemisphere than the Southern Hemisphere. And if you recall in that simulation, AMOC was actually strengthening with time. And this behavior thus agrees with our idealized simulations with ejections in the Northern Hemisphere. So this is the red lines on the plot on the left-hand side. Now in the rise, we see that most of the aerosols are found in the Southern Hemisphere, and this is because most of the injection was actually occurring only at 15 degrees south. And in that simulation, SAI was only slightly slowing down the rate of the AMOC decline, and this is very much consistent with what we see in our idealized simulations where the injections only occur in the Southern Hemisphere. And so the point I'm trying to make is that you can use those idealized simulations to explain the different AMOC behavior in those simulations, in those more complex SAI simulations, and demonstrate that the location of SAI really matters for AMOC response within the same model. Now, that was the main part of my talk, but since I do have some more time, I do want to follow up a bit with some mechanisms behind the SAI response. And so here is the simulated evolution of North Atlantic surface density. So without SAI, so in the SSP2 simulation, which is shown in black, North Atlantic surface density decreases with time. And this is because global warming makes the ocean warmer, and there's also less sea ice formation, which otherwise tends to increase salinity in the leftover water. And so if you have a less density in the North Atlantic, there's less downwelling in the high latitude, and that means weaker AMOC strength. Now, in SAI cases, in general, SAI acts to increase surface density in the North Atlantic, and this promotes downwelling in the high latitudes, and therefore this enhances AMOC strength. And consistently, which I've shown you before, the largest impact is under the Northern Hemisphere injections shown in red. The important thing I want to try to make your point across is that we actually do see an impact over the soon after the start of SAI, and by soon, I mean within the few years from the start of SAI. Now, changes in ocean density can be driven by either or both changes in salinity and changes in heat fluxes. So salinity is shown on the left. So we do see increase that the salinity tends to increase under SAI in those simulations. However, you can notice that the response really doesn't appear until at least like 10 years at least 10 years into the simulation, and therefore the response in salinity lacks what's happening to the ocean density, and it lacks what's happening to the AMOC strength, and therefore it's very likely the result rather than the driver of the AMOC changes. And what I mean by being the result of the AMOC changes is basically if your AMOC strengthen, you basically you have more salty tropical surface water being pushed to the high latitude, and that increases density. Now, on the right-hand side, I got the surface heat flux in the North Atlantic. So this is surface heat flux into the ocean. So the value is negative climatologically, meaning that the ocean is losing energy. By that, it becomes colder and denser. And without going into details, the response is a bit noisy, but basically you can see that SAI lead to changes in surface heat flux already a few years after the start of simulation, and therefore we think this is the result of the, main driver of the AMOC changes in those simulations. Okay, to conclude, I talk about some idealized stratospheric aerosol injection sensitivity experiments done with CSM to WACCM, which use fixed 35-year-long injections at a single latitude in the lowest stratosphere, and these are meant to be useful for understanding physical mechanisms. And I hope I managed to convince you that while details of model ocean physics and climatology are definitely important, whether or not SAI can actually restore AMOC or just barely slow down its greenhouse gas-induced collapse depends strongly on the details of SAI realization, and in this case, the location, the latitude of SAI injection, or SO2 injection. And I talk about the mechanism a bit, and we found that SAI impacts AMOC via changes in surface ocean density, and these are driven predominantly via changes in surface heat fluxes and not salinity. And I didn't go into details, but those changes in surface heat fluxes are driven by SAI impacts on incoming solar radiation, SAI impacts on sensible heat flux, and SAI impacts on Arctic sea ice. And with that, I want to thank you for your attention. I'm happy to take any questions if you have any.
Very interesting. I have a question. So for Glenn's and Arise, the approach was to keep temperature not from changing. I mean, to not change the temperature, the surface temperature with gradients. So north-south temperature would not change, right? But in your injection experiments, you would get a change in temperature because you inject in one hemisphere, so there wouldn't be a equal change in temperature. So you get a cooling, obviously. So I wonder if that impacts the results in some way. So maybe did you plot lens and Arise on top of these surface heat fluxes or ocean density as well to see if that actually matches, or if that is more impacted maybe by the temperature gradient?
I haven't done that. I mean, that paper from NCAR that showed that there are large differences in the climatology, but I get what you say. Like, I think the problem is that our the feedback controller that controls SAI aims to minimize the surface temperature gradient, but any change in AMOC actually contributes to this gradient. So if you speed up AMOC, you actually end up with cooling in the high latitude, but if your AMOC collapses, you end up, if you speed up AMOC, you end up with warming in the high latitude, but if your AMOC collapses, you actually end up with cooling in the high latitude, this sort of warming hole. So I think like there is an extra layer of complexity on top of that. But like, no, I haven't looked at the changes in the surface heat fluxes in Glens and Arise, and I guess I should have. Thanks.
So we move on to the final presentation in the session, which will be given by Daniele. And it will be on developing a simple set of metrics for high-top models.
Yep, thank you. Okay, so first of all, big thanks and acknowledgement to Ilaria, a postdoc, who's now moving here to Anchor. You're very lucky to have her. Treat her well. She's amazing, and she did a lot of the heavy lifting for this. This has also been something we've sort of done in kind of the last month, but I think we got some actually very interesting results, so I was really looking forward to the discussion. So why is it a simple set of metrics? Well, I think it's useful to have something that at a glance helps you determine the relative scale of different models or different generations of one model, which is of great interest, and can integrate observations as well. But the main reason was that we had a few discussions at the CSM co-chair meetings, and Dave Lawrence asked for some set of metrics to be integrated in the Cupid framework. And when he said a simple set of metrics, he actually intended a number, right? That's what he said at one of the meetings. Like, well, okay, you gave me stuff, but what about a number? And so I kind of asked myself a bit, and we researched a bit how we could maybe do something like this. CMIP6 has plenty of examples. There's plenty of examples in the literature for surface climate metrics. This is, well, not the clearest picture ever, but I think, again, it's useful at a glance to have what you see here are different, I never know how these work, okay, different variables here for different distribution of different extremes and different surface climate stuff. And these are the skills of the different CMIP6 models compared to reanalysis. So it's useful if you are a model developer, you're testing out a new version, to maybe add your new version and kind of figure out how well is your model doing. Again, super complicated. I don't want to do something that complicated, but it's a good place to start. And what they normally, these metrics, what they normally do is that they just calculate the root mean square error of the reanalysis compared to the model results, normally in a way that is this simple, and then they try to normalize somehow between the best and the worst model. Again, multiple examples in the literature, and so my question was, can we do something like this? Is there a way to do this the same for like some form of stratospheric quantities? And can we learn something from it? There are a lot of issues though. What do we pick when we want to do this evaluation? And that in a way will depend on the purpose of the evaluation. Do we want to look at stratospheric dynamics? We've seen a lot of talks today. Stratospheric aerosols, which is what I'm going to focus, or even higher up, right? If we're thinking about the whole atmosphere, maybe we want to also see things higher up. But the metrics that we pick is going to, again, depend on what do we want our model to be good at. It will also depend on the availability of measurements or how good the reanalyses are. But I do think that there are things that we can do to lead to sort of add to the diagnostic package in this sense. So sort of the place to start, we had this paper that we published late last year with Nick Davis and a lot of other people where we sort of compared the 3 different versions of CSM WACCM, the middle atmosphere version in 1 and 2 degrees that you've heard today in a few talks, and the full chemistry version. And I think it was great to have 3 slightly different versions to discuss a lot of the differences. I'm not going to go through all of them, but just as an example, this is the way we sort of depicted all of the changes, right? We have, for instance, for this one, we have Mera and Sabre, and we see, okay, this is the difference with sort of the best model version, which is TSMLT. This is what happens when we don't have tropospheric chemistry. This is what happens when we have 2 degrees. So this was good, but again, evaluating how well the model is doing, it's sort of, you have to qualitatively look at it and look at the differences. Nick did this for southern stratospheric warming. Here's the distribution per month, WACCM compared to Mera, and looking at different versions. We did it for ozone a little bit. This was just the stratospheric ozone evolution compared to SBUV. So, you know, and you can say, well, the model is doing okay. A lot of the main problem to me in all of these is that they never include what the uncertainty is over things like reanalysis in many cases. So it's hard to tell whether, well, how much is this the model being wrong, how much is this the uncertainty over the observation. So what we did, what we tried to do is the thing we're sort of familiar with, and we took, also trying to compare with other models, we took the Pinatubo case and tried to develop a set of simple metrics for this case. So we took this, so there's this paper that Ilaria published in 2023, where this was ISAMIP, so Interactive Stratospheric Aerosol Model Intercomparison Project, where the models are with fixed SSTs, but also they were trying to inject different amount of SO2 and figure out which ones of these experiments fitted Pinatubo better. So we used those. CSM did not participate in these for the Pinatubo experiments, but yes, this is what we did at the time for all of these models. Again, we have the observations here at the bottom, and we have all of the various stratospheric AOD. Very complicated figures, very hard to tell anything. One thing that we tried to do at the time was sort of have some Taylor diagrams where we could look at both standard deviation and correlation and make some discussion. But again, even these, it feels like it's pretty hard to tell which model is doing better or it's closer to observation just by looking at all of these numbers. So we took a lot of the information from there, and we added a lot of CSM 1 and 2 simulation, and also a UKSM simulation with interactive aerosols that has never been published, and sort of tried to, again, come up with this set of metrics. So we took, first of all, the trick is if you only take one thing, if you only take AOD, that only gives you some partial information about it. So we took AOD, burden, and effective radius, both over all the tropics and integrated, or depending on the altitude at Laramie and in the tropics. And essentially, our idea was to not just look at how well they match, but also how does it compare to the error that comes with observation. And especially with Pinatubo, those errors are quite large. So the metric that we used is this kind of different way to look at RMSE, which is weighted by the square of the error, right? So if essentially you're asking, well, how does your model fit inside the error bar? And if it's outside of the error bar, then you weight that a lot more. And we tried to do this again for all of these 6 things at the same time so that we could get a better picture. And the important thing is that also we only took the observations that also included some form of error bar, so some form of uncertainty to do this. So what do you find? I think, so this is the final table, and I think there are a lot of, been staring at this a while, and I think that there are a lot of interesting things. So this is color-coded. The blue results are the best, sort of high scale, as in the lowest weighted root mean square error. And the red one is sort of the lowest scales. We only picked, so these experiments are not sort of all consistent in the way some of them have fixed SST, some of them don't, some of them inject in different ways. But I still think that there's a lot that we can learn from something like this. I'll give you a few examples. So first of all, WACCM does pretty good in all of the simulation. But it's interesting that, for instance, CSM1 WACCM, these are the simulations. The third column is simulation that Mike Mills ran in 2016. The fourth column is the simulations that Anja Schmidt ran also in like 2018 with nudged dynamics. And it's interesting to note that CSM1 seems to be doing better than CSM2 for a lot of things. But also, for instance, you can note that nudging doesn't really improve the skill of the model in this case. These are, the injections are exactly the same. You know, this is not a surprise, as Eva was pointing out to me yesterday. We do know that just nudging doesn't really improve large-scale transport that much. It does a bit for a few things, but not as much, so not surprising. But it is kind of interesting, right? Because it also does tell us something about where the main sources of uncertainties may lie. The other interesting thing is also that, and I'm just going to focus on CSM, is also that, you know, now we have these 2 versions for CSM2 WACCM. Again, we can add more simulations later, and Simone has done a lot of different these are simulations that Simone ran. There can be a lot of differences with injection locations, but with these 2 being consistent, there are some very interesting things. So for instance, the fact that MAM4, that is a much more simplified aerosol scheme, actually for most things doesn't do that much worse than Karma, that is much more complicated, except for burden. For some reason, and again, I think it's very interesting, CSM2 MAM4 does the worst possible when it comes to stratospheric sulfate burden. It really, and you can probably see it from here, the point is that then you go look at exactly what happens. So here's the orange one is MAM4. So it's really completely off in a way, but it still does pretty good in all of the other things. So in a way, and there was a talk yesterday about tuning, and this kind of reminded me of this in the sense that you can try to get a better burden by changing your amount of injection, which is what we normally do in CSM. But that means that maybe you degrade the skill over all the other things. So if you consider the injection parameter as sort of a tuning parameter when you're doing historical simulations, you might want to be careful about just reducing the amount of SO2 you're injecting just to get a better match with burden, because then maybe you do, actually MEM4 does the best job of all models when it comes to stratospheric effective radius. And so I feel like, there's clearly something here in terms of determining the fact that, this means that the model is doing good, except for a few things. And why is that? How can we have a good AOD, not perfect, but a good AOD and a good effective radius, but then such a high sulfate burden? There has to be something here, and this kind of visual inspection of this skill could be of use when we go maybe to CSM3. Or maybe if we look at the middle atmosphere, at the mid-top version, I think it would be very useful to add something like this. And I think that these kind of demonstrate the usefulness of these kind of metrics. Again, they're not perfect, and you don't just want to rely on these, but they do tell you something at a first glance, especially when comparing with other things that maybe just an inspection of the profile wouldn't tell you. Can we expand this to all of CMIP6? Pinatubo is just one case. And the answer is, well, that is incredibly hard. CSM is essentially the only model who ran with interactive SO2 emissions for volcanic eruptions. Every other model used the CMIP6 stratospheric AOD. Even UKESM, that has the capabilities to have interactive SO2, the simulation that they send to CMIP6 are with prescribed AOD. And so these ones, the purple line that you see here, I have zoomed for this, the purple line is UKSM. These simulations with interactive aerosols are simulations that they never published, actually, which is find interesting. But this is something that we also had in the Davies et al. Paper. And we probably can, but the fact is that, for instance, and this is the other useful thing, when it comes to CMIP6 output, stratospheric AOD was not one of the outputs that was requested. So it's not on the Earth system grid. There's no way to get effective radius. Like UKSM doesn't output effective radius for stratospheric aerosols at all. So this is also a good excuse to sort of come up with a set of variables that maybe we can start asking CMIP7 to, help CMIP7 and tell them, hey, these are the variables that we need to evaluate models with stratospheric capabilities, or even for the ozone report, for the ozone assessment. So this is all I have for now. So I think we come up, at least for volcanic aerosols, with a set of simple metrics, and I think that just this inspection tells us that there's something. I think this will be great when we have multiple versions with different complexity. This again is sort of the variables and the things that we knew the best, so that what we did, but I think that we can also expand the same framework to other metrics. So if you have any idea, the code for this is in Jupyter Notebooks, so it can be integrated in the Cupid framework pretty easily. I talked to Dave Lawrence about this as well. So if you think that this is a use for you and you have measurements that you want to include, I think we can try to do these and sort of see these through many more metrics. Thank you.
Yeah, very, very interesting. I mean, maybe that's too much to ask, but one important part is, of course, also the aerosol size distribution in those. And some models may not have that if they are bulk aerosol models. But many model aerosol models have different modes that they describe. And that could be really important also because if, or a sectional aerosol model like Karma, if you do have larger sizes, especially after Mount Pinatubo, you already know that, you may get a lower burden because you have a different sedimentation. I don't know how difficult that would be for people, but it may not be that hard to provide some of that as well.
Yeah, I mean, for sure, size distribution would be great. The issue is that, first of all, it's hard to get size distribution even from observation. Right now, there's a couple of campaigns for sure. But really, what I found is that every time that I've asked other CMIP6 models to give me anything at all about the size distribution, has been insanely hard. And really, UKSM in a way is the model that is most easily comparable to CSM in terms of output. And even that CSM in this is great. You have all of the potential variables that you have DG num wet, effective radius, blah, blah. UKSM has none of that. You need to, it's very complicated. So, even getting stratospheric KOD from this, I had to ask Thomas Aubrey had done these simulations. So I feel like, yes, it would be great if we could develop something for size distribution so that we can tell other models, hey, this is what we need, right? This is, this is a good way to communicate what we need in terms of output and maybe what we need in terms of required variable. I'm also in the CMIP7, one of the variable thingies data needs. And so if I can give some more information about, you know, what exactly we could do for this, it would be good. Yeah.
I think this is great. I mean, I already told you that, but two questions, comments, like, well, comments more. One thing, like, I would look into the new CCMI models. You said, like, you can't look into the CMIP6 because most of the models weren't run with, like, interactive volcanic air. I would check the CCMI, the new CCMI Ref D1, whether they might actually have something aerosols, the output in the CCMI, whether they might actually have something aerosols. Anyway, the main thing is, like, you said that there was a great document in 2010, which was the CCM Val report, and it basically has lots of, it was 15 years ago, so none of those models really exist anymore. But like, it had quite a lot of like those kind of simple metrics. I don't think any of them were for the aerosols, but they have some transport, and I would think it would be useful. I don't know if you checked what's in that report, because you said that the IPCC doesn't have stratospheric evaluation, but the CCM Val report was explicitly looking at the stratosphere.
Yeah, I honestly didn't check. I remember the CCM Val report, but I didn't check on that. We also had the same discussion at one of the Hunga Tonga meetings about, Pete Clarkos had something about finding some way to determine what the scale of the models is. You know, an example of this is age of error, right? Even if age of error was one of the things that the CSM2 actually had an issue with age of error, so for these simulations, we wouldn't have that. But you know, sure, yeah, actually it's a great suggestion to go back and look at CCM Val. Should have done that, yeah. But it did, I'm 100% sure they didn't have stratospheric aerosols, and even the new CCM Myrons, I don't remember how many models even had interactive SO2 injections. Yeah, I'll look at that as well. You know, the good thing about this is that once you have the framework in place, just adding some more variables is good. So yeah, that could definitely.
No, I do definitely agree. Like, the thing about the CCM Val report was great. It was 15 years ago, and it's none of that exists, none of those models, and anything like that hasn't been done.
This one exists. It hasn't changed at all. It's the one I did my PhD thesis on, and like still there.
Hopefully,
but
better
yeah, but
now.
it sucks, as
Hopefully
you can see
better
from the
now,
metrics. So it's
We have an online question also from Alan Robach. He said, what did you use for Pinatubo for observations in the tropics? There was a gap from SAGE-2 and no litters.
Yeah, actually, Hilaria has some figures, and I just didn't include them. So you can see here, right? So this is SAGE, and indeed there are a lot. Actually, there are huge. Where is this thing? Okay, there are huge holes in terms of the coverage. Yes. So this one with Laramie is OPC, so this is SONS, and this one it's SAGE, but it has a lot of gaps, actually even more than it's appearing from here. So this is also a comment on the quality of the observations for sure, and maybe Hunga Tonga can do something like this. And then finally, for burden, we use HIRS, and this is GLOSSAC and AVHRR, and all of these have gaps, right? So none of these are perfect, but yeah, these are the same set of measurements that we used in the 2023 paper.
So just a comment. You don't really show surface area density in any of this, right? Because that would get you to chemistry.
Yeah. But was it because maybe we just didn't have the time and like no? But it's or maybe because it didn't have the error bar. There was a reason why we didn't pick these, even though we had a figure like this in the 2023 paper. And I think it was because lacking the error bar, then we cannot sort of have the same framework of these. But yeah, we should go back and check. Yeah, but definitely, sure, yeah. Okay. Thank you.
do have 10 minutes or so for discussion if anyone has comments on any of talk or questions on future directions for WACCM. You look like you're about to.
This is just a comment for Simone, kind of put her on her spot, but do you want to give like a brief update on Karma, where you stand with WACCM Karma?
Oh, no. Well, I mean, we are developing different aerosol schemes for CSM right now. So we have the model, and Daniel showed the Karma model, which is now included in one version of WACCM, which is the CSM. It's around CSM 2.2, and we're also moving. So basically, we're moving more a flexible aerosol interface into the development version that will be usable for CSM throughout WACCM and ChemChem and other versions. But currently, Karma is only available in a development version. So, I mean, in a specific model branch, CSM 2.2. And we run it with WACCM, just the middle atmosphere version, because it gets pretty expensive. But things like Mount Pinatubo and stuff, geoengineering is something we really want to we want to use Karma to reproduce those runs, and we have already done so to compare really with the model and see what advantages we have with the Karma model. Yeah, so there's still a lot to do to get it in the development version and into the trunk, but that's something we're still working on. Francis is working a lot on improving the aerosol and updating those. Yeah, so more in future meetings.
You have another. It's good Doug is here.
So there's also been effort within the WACCM framework to represent wildfire chemistry in the stratosphere, and the Solomon et al. Papers on that. We will propagate that information into available versions of WACCM, so other people can do that kind of research in the future, where organic aerosols increase the solubility of HCl in the stratosphere at much warmer temperatures, and so you get heterogeneous processing going on, similar to what you see in the polar region. And for when you get these big injections of organics from these wildfires, it's really important. It can destroy a lot of ozone. So we want to have that process in the model going forward. So we're working on that.
Going back to your talk, Doug, so in the paper with Nick, we also looked at surface climate and sort of climate sensitivity and that kind of stuff. I feel like, though, with the new addition, definitely the climate sensitivity would change, right? And the warming in the historical period would change as well. And I assume that it would sort of reduce the amount of warming since it increases sea ice, right? So that's sort of, what I'm saying is that it's important that these kind of changes are documented between CMIP 6 and CMIP 7, because otherwise we might end up with a CMIP 7 version of WACCM that has a lower sensitivity, and the reason is through some of the changes in the forcing data set. So I think we really need to be careful with figuring out where all these changes are coming from. So we really need to keep CSM2 alive so that we can keep doing a lot of these, yeah.
No additional comments. Then thanks everyone for joining the session, and I guess hopefully by the winter working group meeting, maybe we'll have the WACCM 7 in a state of close to being ready for use for everyone. So thank you.
Yeah, so welcome to the cross-working group session on high-resolution and ultra-high-resolution modeling. I'm afraid we will flow over here, so if you just come in, see whether you can grab a seat or bring a chair. I think this will be a little bit packed here. So we have 8 talks. I will kind of introduce the first 4 speakers, and then Adam Harrington, who's here, my co-lead, will introduce the next 4 speakers. And it's all about, 25 kilometer and more, as you will see. Let me kind of start with the first speaker. It's Andreas Prine from NCAR, M-Cubed Session, and section, or lab, I should say. And he's giving us an overview of kilometer scale modeling here at NCAR.
Thank you, Christiane, and thank you very much for allowing me to speak today. Welcome, everybody. The type of modeling that I will talk about is regional climate modeling with the weather research and forecasting model that we did in the water research program here at NCAR during the last 10 years. It's a nice animation of the recently completed South American simulations that we did. We have 20 years of current climate and 20 years of future climate. This is 4 kilometer WRF downscaling era 5. So this is short history of the flagship simulations we did in the water system program. Starting over a fairly small region over the Colorado headwaters more than 10 years ago, and based on the success of those simulations, they're all 4 kilometers. This is our go-to grid spacing. It's a sweet spot that we found between efficiency and accuracy. We basically reached out to continental scales, running most of our simulations now over this domain. The most recent simulations, the most ambitious simulations that we completed was the CONUS 404 simulation. 404 stands for 40 years at 4 kilometers with WRF downscaling era 5. And we have also a 40-year future simulation now that's finishing this week. Each simulation takes a year to run. So those are really expensive simulations to do. And you get one realization at 5% of the globe. But there are lots of interesting things you can look at in these simulations. And I will give you a quick overview of some of those. I will only focus on summertime, not on wintertime. If you're interested, I hope these will become available afterwards. You can click on some of these papers that looked at more snowpack, orographic precipitation, things like that, added value in the 4 kilometer WRF simulations there. I will more focus on convective rainfall summertime. Starting with typical biases that we find in closer resolution CMIP style simulations. This is from CMIP 5, summertime. Top is temperature bias and bottom is precipitation bias. And this is the multi-model mean, and you can see stippling shows systematic biases. We have a warm and dry bias over the US, central US, and a wet and cool bias over the western US. And the second one is not very often talked to, but it's very obvious that you see this fairly cool colors and very wet conditions in the west. Next modeling version, these biases are very consistent. We didn't move the needle a lot. They're still there, and I will talk a little bit more about those. I will focus on the western US bias first, the wet and cold bias, and then in the second part, talk a little bit about the central US warm and dry bias. So looking at, these are now again WRF simulations, but much coarser simulations, 36 kilometer downscaling era 5 reanalysis. And we did a large physics ensemble. WRF has many physics options, so you can play around with physics. What you see here is the diurnal cycle of convective precipitation in the western US. These are the stations that we are comparing to. This is the observations down here. So you see a clear afternoon peak of convective activity that you would expect in this region during summertime. And then you see what the WRF modeling system does with different physics options. The main one that really changed the precipitation are the deep convection scheme, which might not be surprising. You see 3 different deep convection schemes here, Kine-Fridge, Tietke, and ANSYS. You can see all of them are fairly wrong. You can change how wrong they are, but they all basically have way too much rainfall. Oh, the colors, sorry. I can point it out. The top one is the Kine-Fridge. It doesn't matter too much anyway. Like you see, all of them are peaking too early. They have way too much rainfall. That's the amount bias is basically a bias of frequency. Like it's almost every day it rains at noon. And then you have a low intensity. There's basically no intensity variation during the day. This is very common in many, many coarse resolution simulations till this day. If you go to high resolution, this is now era 5 downscaling. With WRF to 4 kilometers, you can see that this is a different range here. I wanted to point this out as well. You can see that we eradicate most of these biases almost completely. And even ERA 5 still has similar biases. This is the blue line, the top one. Yeah, this is still blue for you as well. So the 4 kilometer has a much better representation of the amount, intensity, and frequency of precipitation. It also captures extremes very well. So if you're interested in local scale extremes, these are PDFs. And sorry, again, the colors are really awful. But one of those lines is the 4 kilometers. It's the middle one. All of them are very similar. That's the point. So hourly extreme rainfall is very well simulated in these 4 kilometer simulations, independent of which region you look at, if you're in the northeastern US or, for example, in the Great Basin on the left. So moving on to the central US, and that's a little bit of a more complicated bias there. There were 2 major projects, or at least one really big project, the CAUSES project that some of you might have been involved in. In 2017, there was this paper talking about the reasons for these biases, the warm and dry bias. Now, sorry, going back. And they basically concluded that it's the mesoscale extreme rainfall, which is often mesoscale convective systems in this region that are missing. Again, CMIP6, same biases, but I think there's a better understanding what the sources of these biases are now in this new paper. And they talk about land-atmosphere coupling, recycling of moisture, and this is basically similar to what we found in our high-resolution modeling as well. So if you think about the modeling mesoscale convective systems, so mesoscale convective systems are organized complexes of thunderstorms. There are 3 regimes how you can simulate turbulent motions in our models. So on the left side here is the mesoscale limit. This is where you use deep convection parameterizations. Then you get into the gray zone, where some turbulent motions are resolved, but not all of them, and then you can go to LES scales. And what I'm showing you here is stepping you through these different regimes, simulating idealized MCSs with WRF. I initialize convection back here, and then I let it freely develop over 7 hours. And what you see in the 12 kilometers, it doesn't matter which deep convection scheme you use, or if you turn it off, you trigger one updraft, and the updraft is basically blown with mid-level winds. So if you study MCSs, this is really not what you want to see. You're very disappointed. However, if you go to 4 kilometers, you see really regime shifts. So now we have multiple updrafts. You get cold pools developing, a clear convective line here, and even the motion of the system is very different at 4 kilometers compared to 12. And you can go down to higher resolution to 1 kilometer, and you see more small-scale structures. Things get better resolved, but they're more qualitatively similar to the 4 kilometer than the 12 to the 4. So the big step that we found was really from 12 kilometers, where you have to parameterize deep convection, to something like 4 kilometer scale, where you simulate MCSs way better. We even went down to 250 meters, where you see turbulent motions way better resolved. So I also wanted to show you how this looks in real simulations. Now, these are 2 animations. This is low-level winds in ERA 5 and WRF 4 kilometer. We do spectral nudging in WRF 4 kilometers. So what you see here is the low-level wind looks very similar on large scale. So if I pause here, for example, you can see large-scale patterns with strong low-level winds are similar in WRF and ERA 5. Of course, WRF has much more small-scale details. But when I looked at these animations for the first time, and let me see if I can find this, for example, here, you get this very strong outflows from thunderstorms. These are related to mesoscale convective systems, cold pools, and mesovortices that you get in high-resolution simulations. Those are almost completely missing in ERA 5, even with the data simulation. And you see these kind of systems happening almost every day, and they are really causing a lot of issues. For example, there was a big derecho event hitting Houston earlier this year, and these are exactly the kind of systems. So if you're 25 kilometers, you can get clusters of clouds that look similar to MCSs, but the fundamental processes, for example, cold pool dynamics and mesovortices are really hard to resolve at coarser resolution. So what we did when we ran the first Conus scale simulations, we were really excited because we thought we will solve this warm and dry bias in the central US with going to 4 kilometers. And we ran this is a 13-year-long simulation. I used MCS tracking here. This is observed MCSs, and you can see now in summertime, June, July, August, we almost have 1 MCS every day in this region, in the central US. It's very active. They contribute more than 50% of warm season rainfall. So they are really important to capture in our models. So the 4 kilometer, and this is probably not red, but the line that pops up here, the gray line, showed you we are right on track with the MCS counts until June. And then in the late season, we had maybe a third of the MCSs. And this is the biases that we had. And yeah, it should be, it's really awful colors, sorry for that. But you can see we go up to 5-degree warm biases. This is actually worse than if you run a 12-kilometer, 25-kilometer WRF simulation. So the biases got even worse than before. Very disappointing. We tried to fix or see what causes these biases. We started looking at aerosols. They weren't really the primary source here. Shallow convection, we tried different shallow convection schemes, didn't help a lot. Boundary layer schemes didn't help a lot. And then we found out it's the recycling of moisture. It's this groundwater dynamics that we have in the central US. Basically, if you coarse resolution models, the hills that you resolve in your model are very shallow. And because of that, if you have lateral flow activated in your model, you have very little lateral flow. So you get fairly deep groundwater tables in these small-scale valleys that we have in the central US. If you go to higher resolution at kilometer scales, you get much steeper slopes, and then suddenly you get much shallower water level tables in the valleys because the water is accumulating there, and then you get much more evapotranspiration, and that's increasing your precipitation through moisture recycling in the central US and reducing the warm bias. And if we include that in the simulations which we did in the recent simulations, you can see that we can capture the late season MCS counts fairly well. And the biases are largely reduced, even though it's again, with the colors, it's hard to see. And this can have quite large-scale consequences because central US convection can have downstream impacts, and even on very large scale. This is one example. Looking at ERA 5, there was a convective outbreak in the central US. You can see it amplifies the wave train, and then you get anticyclonic wave breaking in Europe. And this was an early April heat wave that actually hit the UK in this year. So again, there are also upscaling impacts by improving local scale, mesoscale convective activity in the central US. So wrapping up, what we see is a step change in the representation of mesoscale processes when we go to kilometer scale grid spacing. Improvements from 4 to 1 kilometers were less clear in our simulations, but 4 or 3 kilometers get a lot of improvement compared to, for example, to 12 or 25. I also want to point out the computational costs are large. If you would run the 4-kilometer global, is approximately 15,000 times more expensive than a 1-degree model. So keep this in mind. The questions that you can ask are very different from these modeling systems. Not everything improves out of the box. Like the central US dry bias is a good example for that. Things got worse, and then we found the physical reason why they got worse, and then we were able to improve those. And now we have a pretty solid simulation, but don't expect miraculously that resolution is fixing everything. And the frontier research topics that I think would be exciting to look at is with the impact of resolving mesoscale processes on a large scale. The human impacts on the system. We are currently running irrigation simulation and crop simulations, which further improve the central US warm season simulation. And of course, change in extreme events. If you're interested in extremes, those are really nice simulations to look at. Thank you very much.
Yeah, okay. I use this microphone, yeah. I know the CONUS for you run, I think, 40 years plus. Have you looked at climate change impacts over that 40-year time period?
We started looking at the historic climate change impact over the 40 years, and like we see very similar patterns than in the observations, and which is understandable because we downscale ERA 5 and use nudging. But now you can really look at very small-scale processes. Like I published a paper last year on straight-line winds, which is a really difficult thing to observe. And now we can look at how straight-line winds change over the last 40 years in this high-resolution simulation. So it's really opening up to look at climate change in mesoscale processes, which is very exciting for me.
He talks about the SCREAM model, which is a high resolution or ultra high resolution model from the Department of Energy.
Oh, you guys get a preview of one of the slides. I guess I'll go back. No, I'm actually, so this computer seems to be on. What's that? Where is the clicker? Ah. Okay. Perfect. Okay. Sorry. Hello, everybody. I'd like to thank the organizers for giving me an opportunity to come here today to talk to you about the work we've been doing on the SCREAM project, which is the Department of Energy's effort to design a global atmospheric model that can run at 3-kilometer resolution and potentially even higher resolution, and use the machines that we have to run at exascale performance. So I'm going to start off with this slide, which is sort of a twofer slide. It's the outline for the talk. I'm going to cover all of these topics, but it also is an opportunity to sort of see a holistic picture of all of the different things that we had to consider when we went on this effort to design this model. So really the main thrust of the work is in this global atmospheric model, this driver, and that's going to be a lot of what I talk about today. But that driver is responsible for a lot of different aspects of the model, communicating with the computers, communicating with the user, handling testing, handling I/O. And so each of these has their own inherent challenges, and I'm going to discuss those challenges with you today and what we did in the SCREAM project to address them. The first point I want to make, though, is sort of a discussion of what the terms mean. So you're going to hear SCREAM often, but you're also going to hear this term EMXX. And EMXX is the driver, and SCREAM is the configuration, as shown here in this slide. So SCREAM stands for the Simple Cloud Resolving E3SM Atmosphere Model, and it's the configuration that's designed to run at convective permitting scales. And so, as you can see from these physics parameterizations put up on the screen, there's a simplified set of parameterizations, including no deep convection. Another thing I'd like to draw your attention to is that in order to kind of set this up for this very simple model that can run at these scales, we decided to use 3 new parameterizations that didn't exist in the E3SM model before we started this effort. EMXX, on the other hand, is the name that we've given to the E3SM atmosphere model, which has been completely rewritten and redesigned in C++ Cocos in order to run the SCREAM configuration. And so they're sort of 2 different terms and very similar meaning. Did it click? Oh. Okay, I'm stuck on this slide. I can just talk about these for a while. Oh, maybe that will work now. No.
You can see a mouse. Mouse isn't even moving.
Oh, there we go. Maybe if I just don't point at the screen, I'll do that. Okay, cool. Well, aside from that delay. So the question is, how did we get here? So we have this configuration, but we also have this whole new infrastructure. And so the SCREAM team came up with this plan where we would develop the SCREAM configuration in tandem with developing this new model so that both could be developed at the same time, and therefore we could utilize our time better. And so the SCREAM configuration was initially developed in the Fortran version of the code, which is fairly similar to the CESM, although the code bases have diverged since the 2 models separated a few years back. But still, very similar in structure, and so we developed these F90 schemes in the F90 code, and that allowed the scientists to validate the models and fix any bugs they might find. And at the same time, the software infrastructure team, the development team, was building the C++ Cocos rewrite, and we were syncing up with that Fortran code along the way to make sure there was bit-for-bit agreement between the different code bases in terms of the physics, so that when it came time to start using the C++ implementation, which is now, as you can see on this timeline, about 6 years later, we were pretty confident that all of the validation that had been done on the Fortran version would apply to the C++ version. And this strategy was very effective. It allowed us to basically develop a whole new atmospheric model in a completely different code base in roughly 4.5 years using 6 full-time employee hours. And now here we are 6 years later, and we're ready to drop support for the Fortran. And I want to make sure that to point out, this is not an E3SM. EMXX is still sort of independent of E3SM. So EMXX, the project, is dropping support for the Fortran, and now all subsequent development and simulations are being done using this new driver. So that leads me to why C+ and Cocos, right? And it really comes down to this part of the mission, which is to run on these machines that the DOE is coming online in the DOE to take advantage of them and their heterogeneous architectures that run with GPUs. That's where most of the performance is. And so we needed to figure out how we were going to design this project in a way that will allow us to take advantage of that. And there are a few options. So this sort of bulleted list here details a few of those. And we had to choose one. And what we ended up going with is this general purpose library approach using something like Cocos or YACL or Raja. There's a few options to choose from. We ended up taking Cocos. There's a lot of reasons for that. One of the primary reasons is that the software development team on Scream was just finishing up having ported the HomeXX die core to C++ Cocos, and so we could leverage that experience that they had in order to basically make this a much simpler process for us. In order to do this transition to using something like Cocos, we also had to have code written in C++, which turned out to actually be a great opportunity which we seized upon. So rewriting everything in C++ allowed us to look at what was existing in the Fortran code and take what we wanted from there and maybe even improve upon it and leave behind a lot of the legacy code which still exists, which may be unused. It also has a few other benefits as well, with regards to vendors, better support from vendors. And I would note that it allows us to take advantage of object-oriented programming, which will factor into the next few slides. And here on the right-hand side, you can see just an example of how that performance is playing out. This is us running on Perlmutter, Summit, and Frontier, all DOE machines. And the crowning achievement here showing off that with all of Frontier, which is a little unrealistic for mainline production runs, we were able to accomplish greater than one simulated day per year, or one simulated year per day. The other way would be horrible. It's one simulated year per day, on a 3-kilometer global domain. So that's pretty amazing. So one of the key aspects of running at such high resolution is memory management. And so that's illustrated here. When we go to 3.25 kilometers, we're looking at 25 million columns. And when you factor in that we have 128 levels in our run, that's 3.22 billion degrees of freedom per 3-dimensional variable. And so that's a massive amount of memory. And of course, when we're running these simulations, we do want to be able to gather as much data as we can so we can do really good science with it. Similarly, we have a lot of on-node data requirements because we do have these massive variables we're trying to account for. And so if we look at the original E3SM atmosphere model, what we encounter when it comes to variable management are these rigid structures. And so some of you will be familiar with these terms: physics states, physics 10, dying state, pbuff. And so these rigid hard-coded structures that allocate a lot of memory, and some of that memory might not actually be needed for the particular simulation you're doing. Similarly, we have a hard-coded set of restart variables. So when we actually write a restart file, we might be writing out more than we need. And when you're talking about these kinds of file sizes, that's actually every variable counts in terms of how much storage you have. And I don't note it here, but also in the original default model, you have these default outputs that can just be written, and you may not want them, and they also can be pretty expensive. And so what you run into is sort of an issue when you hit storage or on-node limits for your memory. And so in order to address this, in the Screen project, we redesigned it in order to have this sort of intelligent memory management. And so we created this class object called the field manager, and it is responsible for all persistent memory that's held throughout the entire simulation. And so we don't have all of these different state structures, but instead we just have this one class object. And in terms of temporary memory, because of course a lot of processes need just to fire up some memory to do some calculations, we also created this atmosphere memory buffer. And so I'll talk about a bit about both of those in the next few slides. And so as I stated, we've consolidated all of these Fortran structures into this single field manager class and these field objects. And so we treat every variable like a field object. And I think this is actually something similar to what CCPP is also doing as well. And so it has there's a lot of analogies or a lot of similarities between the two. And this is actually very powerful. Not only does it allow us to have better memory management, but it also provides for us a number of tools which we can utilize to improve improve the user interface, the developmental interface, and of course to control our memory management. So for example, one thing we can do is we can construct a directed acyclic graph. And this is done by default by the atmospheric model for every single run and provided to the user. And so with this directed acyclic graph, which I don't expect you to read the very tiny print that you're looking at up there, but what it is essentially the flow of information through the entire atmospheric time step. So at the very top is the beginning of the step, at the very bottom is the end of the step, and what you're looking at is every single process, every single component of the atmosphere, what variables it's using and how it's using those. Are they input, are they output, am I changing them? So what that does for the online, for the driver itself, is it allows it to do things like at runtime determine what is required for a bit-for-bit restart. And so the list of variables that we write for restart are determined at runtime, which is great. So if you change the configuration of the model, you don't have to worry that you're writing redundant restart variables. You're definitely going to write exactly what you need and nothing more. It also allows it to ensure consistency, making sure that if a variable is needed, that it has been created or set by a previous function. It also is helpful for us users because we can actually open this up, blow it up, and look at things and be like, okay, I know what's happening in the temperature, and maybe that's helpful for debugging. Now, I talked about also on-node memory just for local things. And so we have this atmospheric memory buffer, which takes advantage of using pointers. And so what this really just does in a very simple way is every process says, I'm going to need this much memory in order to do all of my local processes. I need this much temporary memory. And the memory buffer consolidates all of that and determines the minimum amount of memory that would be needed to make everyone happy. And then passes that pointer back to the process. And now we don't have to worry that processes are just grabbing memory all over the place and we sort of overburdened our on-node memory. I'm going to go a little quickly because I think I'm getting close to the end of time. But the last thing for output and input and just memory in general is just managing output. As noted, it's pretty big when you do a 3D field. But a lot of the science we want to do doesn't require the full global output. So we've also instituted this ability in Emacs to output data at single points in case you were looking at specific observation stations. Regional output can be done online. And similarly, you can just coarse in your output. So a lot of science doesn't need the 3-kilometer output, but it does need global output. So you can coarse into 25-kilometer output or 100-kilometer output. And so you have that 3-kilometer fidelity, but you don't have the 3-kilometer mesh. And that significantly reduces the size of our files and allows us to really spec out what questions we want to answer. Because these runs are expensive. So we don't want to do them again if we missed an output variable. So very quickly then, I'll talk about how testing has played a major role. So we've inherited a lot of the testing that's already inherent in E3SM, which is fantastic. But again, because we were able to redesign the entire driver, we were able to do it with testing in mind. And so almost every piece of the driver is independent of the other pieces, which allows us to create these very nimble, very fast tests. And so you can see here, this is an example of a dashboard. We have on the order of 470, close to 500 unit tests that can be run very quickly and are run very quickly nightly and every time a PR is issued to GitHub in order to update the code. And so this is just showing our continuous integration checks these tests and reports back pass or fail, which allows us to make sure that bugs don't creep in, bugs that might actually be you might think would be independent from your development, but somehow you've impacted the different part of the code. This is also super helpful for debugging and verification as a developer. These tests are quick. They can be run on a single node. And so when you're doing your development and things aren't quite working, you don't have to worry about building the whole code. You can just build small pieces and run them yourself. And then lastly, for the user interface, C++ doesn't support name lists, which also turned out to be kind of a blessing in disguise, because name lists can be a little bit difficult to parse. And so this is just an example of that. I'm showing how it's very difficult to read that name list. And in this particular example, I've written the same name list variable twice. And it's somebody reading this, they may not even notice that cloud mac mic num steps is equal to 6 in 2 different places or 1 different place. But in reality, the code won't tell you that either. And so we were able to then transition to something like a YAML format, which is a lot more human readable and a lot more computable parsable as well. And by doing this, we also instituted this atmosphere change and atmosphere query, these tools, which are basically the same as the XML functions we should be familiar with from SEAM, but then of course just for atmosphere variables. And so that allows us to do things like enforce consistency. So if you ask to make a variable an integer when it's really supposed to be a string, then you'll actually get told that that's an invalid request. It also stops us from being able to define something more than once, because once you define it, then it will always be redefined the next time you try to update that definition. So just in conclusion, there's a lot more to EMAXX than what I talked about here, but I just want to take this opportunity to say that when you're going to these higher resolution models, kind of like what Andreas was talking about, it doesn't just work out of the box. It's not a matter of just giving it a more refined initial condition. There are a lot more considerations. And my hope is that sort of sharing with you our pathway through these considerations will be helpful in understanding kind of like what choices you would want to make when kind of looking at developing a model that's going to run at these very high resolutions. And then I will finish with this really beautiful picture, which is more beautiful on my screen, apologize, and invite any questions.
Other questions for Aaron?
This may be naive because I'm not a software engineer, but when you refactored the Fortran code to C++ Cocos, were you able to get bit for bit, and was that the sort of litmus test, or is there some other type of round-off level test that you used in order to verify you did the refactor correctly?
That's an excellent question. So there's two answers. When it comes to the physics itself, so just taking the microphysics process itself, that we were able to establish bit for bit because we could have the C++ call the Fortran code through a bridge and call our C++ porting through a code, and then we could just compare those. And so for all of the atmospheric processes, we're pretty confident it's bit for bit. But the driver itself is not bit for bit. It's a completely different driver. It has a different way of managing the memory. And I didn't note it here, but we also have a different process ordering. So we don't have TFIS AC and TFIS BC for all the CESM folks out there. We have just one single physics run through. It starts with dynamics, ends with radiation. And so those nuances mean that we're not actually bit for bit. But we're more confident that we've at least done things correctly on the physics side, and then we just had to rely on our unit tests to make us feel more comfortable with the actual driver itself and that it was behaving the way we would expect it to. And then, of course, the proof of the pudding is to do an actual run for a year and then compare that. And that has been done. There's a paper that will hopefully come out soon that has 4 seasonal simulations with this driver that kind of digs deeper into that. Yeah.
Unfortunately, I think we're out of time. Need to move on. Maybe you can just, yeah, you're sitting next to you. Alrighty. Our next speaker is Christine Shields from NCAR CGD, and she talks about IHASP simulations.
So what do I use? This one? Just the forward? Clicker. Okay. Oh yeah, figure it out as I go. So thank you all for coming, and thanks to the organizers for giving me the opportunity to talk. So I'm going to switch gears a little bit, and we're going to talk more about applications, and I'm going to specifically talk about the 10th degree ocean that's underneath a 1/4 degree atmosphere. I wanted to give a big thank you to Hui Li, who's my collaborator in this work, sitting right there, as well as Fred Kostrucchio, Dan Fu, Cal Nardi, Shui Liu, and Colin Zerzicki, who've all helped in this project. It's been sort of a big project, and I want to make sure everyone is acknowledged. Okay, so to start, this is just a brief IHASP. This is what the IHASP model is that we're using. There's a number of different experiments that are going on with IHASP. So we're looking at the transient climate simulations. And so there are 3 ensemble members available, but 2 were the ones, only 2 had the high frequency data that we actually needed. So those are the ones that are being used. We are using analysis years 1960 to 2005, so a good 45 years, and then 2060 to 2100 for the RCP 8.5 scenario. So these are climate change simulations. We have a regional focus here. So broadly, we're looking at East Pacific atmospheric rivers, but we're going to, let me see if I can use the mouse to find a pointer, maybe not. Okay, that's fine. The blue is the Pacific Northwest. The top button is the pointer. Oh, there we go. A nice green pointer. All right, so we're looking at Pacific Northwest as one region. The green region is sort of hard, is the California region, and the black-looking thing that's supposed to be red is Southern California. So that's how we're dividing up our atmospheric rivers. For this work, I'm using 3 different atmospheric river detection tools, ARDTs, and these are all ARTMIP contributors, and ARTMIP is the Atmospheric River Tracking Method Intercomparison Project. And then the way we're presenting the results is consensus ARs, and this means all 3 algorithms have to agree in order for us to consider it as an AR. And then I have the model reference there for anyone interested in more IHESP details. Okay, so these are I'm going to spend a moment just to talk about the different ARDTs because we're looking at climate change simulations here. And when we look at atmospheric rivers and climate change, one of the things that ARMIP has shown us is that there is a high uncertainty in AR metrics such as frequency and duration and things that how we characterize atmospheric rivers. So it's really important that we use different ways of defining atmospheric rivers in gridded data sets, so we're sort of encompassing all these different possibilities. And this is sort of what ARTMIP is about, but I'm not really going to talk about that. So the 3 different methodologies that we're using, the Shields Q one is very restrictive. It means it just really sort of detects the strongest atmospheric rivers. It is time varying and spatial relative in terms of defining the anomalies. And this means I'm removing Clausius-Clapeyron as a factor in how I'm detecting atmospheric rivers. So for climate change, it shouldn't matter. The Mundik-Nardi one takes a different approach, and this is a lot of the ARDTs that are out there use a temporal relative methodology to define how to identify atmospheric rivers. And this is because these methodologies tend to care about the impacts underneath the ARs, and so they tend to have more atmospheric rivers. Clausius-Clapeyron is baked in, and they are less restrictive, and this is comparable to the ARTMIP mean. And then finally, the third one we're using is removing thresholds altogether and using a threshold-free methodology with the image recognition and IVT plumes, and that's called IPART. And so those are the different ones we're using. Okay, so now I want to just show you an example of what the 10th degree ocean gets you compared to the 1 degree ocean. And these have the exact same atmosphere model on top of it, which is the 25 kilometer CAM. And then underneath it, on the left, is the 10th degree ocean. And then on the right is the 1 degree ocean. And so you really can see that the high resolution captures the eddies from the 10th degree ocean. And the field we're looking at is integrated water vapor. This is an atmospheric field. So that eddy structure underneath is being reflected into that water vapor signal. Okay, so this is the methodology in terms of the results I'm going to present. We're doing composite analysis. We're using consensus agreement for ARDTs, which is what I mentioned previously. And the fingerprint and how we're defining atmospheric rivers, or the signature, is we're taking the 3 days after the onset minus the 3 days before. And so this is how we're actually trying to show this AR signature in the upper ocean response. The different variables we're looking at: mixed layer depth, sea surface height, sea surface temperature, surface heat flux, sensible heat flux, and evaporative heat flux. And it's important to note that these are all anomalies from the long-term climatology, so we're removing the base state for this. So this is really just the atmospheric river signature on the ocean that we're looking at. Okay, so let's start with historical and Southern California. So this panel is the integrated water vapor composite anomaly. And so we put this up there so you can really see the greenish signal where the atmospheric rivers these are the atmospheric rivers that are hitting Southern California, and this is a composite of what that looks like and where it is. And so the upper row, we're looking at more of the mechanical responses. The sea surface temperature composite anomaly is showing a cooling upstream of the atmospheric river. So in response to the atmospheric river, the SSTs are cooling underneath, and this is in part can be explained by the fact that the mixed layer depth is deepening. We're mixing up that cooler water from beneath, and then it's contributing to this cooling of the SST, all upstream of the atmospheric river, and we see a shallowing downstream of or ahead of the composite AR right here. So the sea surface height anomalies also shows that the atmospheric rivers and that those wind vectors that you see are pushing the water coastward. And so this is a very robust signal. We see in all the different regions. See if I can try to trace it. a little light here. I don't know if you can see it at all up there. But the idea, this is important and has implications for coastal communities. So the bottom row is more of our heat fluxes, our thermodynamic responses, and you can see we have this dipole structure, which is a reflection of the AR passage. And so upstream of the AR, we see this cooling or the heat loop being lost from the ocean, and then ahead or downstream of the AR, we see this warming. And so if we separate these out into sensible heat and evaporative heat, we can see that the evaporative heat is actually the stronger contributor to the surface heat flux response. So here is California. Very similar response as to Southern California. Again, here we have where these are the ARs that are composited right here along the integrated water vapor anomaly. And then the sea surface temperature cooling, upstream of the AR, the deepening of the mixed layer depth, and then we actually hopefully see it's a little bit stronger here in terms of the sea surface height along the coast here. And again, the same response in terms of the heat flux anomalies. We see that evaporative heat is a little stronger than the sensible heat. So I'm not going to show you Pacific Northwest here because I think that in the interest of time, but I will show you some Pacific Northwest ones as I have my concluding slides and move through and putting everything together. So I want to switch now to the climate change response. So before we were looking at simply the historical response, in the historical simulations, the response of the atmospheric rivers on the upper ocean. Now we're looking at the change in response between the RCP 8.5 minus historical. Okay, so same sort of format in terms of composites and where things are. And we can see that the sea surface temperatures are, the response is amplified with climate change, so we have further cooling. And the mixed layer depth for the Southern California, we don't really see a significant response upstream, but downstream, we see the significant, what it appears to be a deepening of the mixed layer depth, but this is really a subduing or a shallowing of the shallow response that the mixed layer depth gives just as a base signal. And hopefully this will be clear as I move on through. And then the sea surface height, we see an amplification of the response along the coast. So this is really sort of what I'm just sort of focused on right here. Okay, so for the heat flux anomaly, we see, again, an amplification of the signal. We see this dipole structure with the cooling, further cooling upstream of the AR, composite ARs, and further warming downstream of the ARs. And the significance is, I didn't mention this, is the stippling, and this is a 95% significance test. And when we divide this up in between the evaporative and the sensible heat, we see that the evaporative flux is really the dominant component here. If we look at California, although the signals are the same for the mechanical responses, the heat flux responses are actually quite different from what we see in Southern California. So there's different things going on here. Upstream of the AR, we see, instead of a cooling, we see a warming, and then we divide this up in between the sensible heat and the evaporative heat, and we see contributions of both that are the opposite signal that we see with the Southern California response. And the Pacific Northwest response is similar to the California one. Okay, so I think that it's sort of hard to absorb everything just looking at these quick slides, and I knew there was a lot on there. So I'm going to try to put it all together and hopefully step you through all of the conclusions, and hopefully it'll become a little bit more clear. So first, the ARs and their strong winds cause significant upper ocean responses when we use this high-resolution 10-degree ocean. We see this as a robust response in terms of the mixed layer depth. We see a deepening of it as those winds help to mix the water, the upper ocean water. So this is Southern California. California and Pacific Northwest all have this signal. So when we look at the climate change response, although mixed layers are generally deeper upstream or shallower downstream of the AR passage, and this, as I said, is due to the wind and the heat fluxes, this response is subdued with a climate change response that's a lessening of the shallowing of this downstream response, and that is sort of evident right here. Okay. AR's push water towards the coast is measured by sea surface height, and this will be amplified under climate changes as a robust signal. And then in terms of the surface heat flux, the AR's strong winds impact the heat fluxes, which promote cooling upstream and warming downstream of the AR passage. And when we look at that in terms of climate change, we have a different response in Southern California as we do in latitudes north. And this is in part probably due to, there's a different flavors of atmospheric rivers that are going on here. So there's different types of atmospheric rivers that are contributing to Southern California as opposed to California and Pacific Northwest, which tend to have extratropical cyclones co-located. And then this is my last slide, but I wanted to throw up the sea surface height change response in a different format. Before it was sort of giving you the absolute values, but here we're doing it in relative, in the change relative to the historical to show you the impacts to the coastal communities, which I think is a pretty big result here. So I'll stop there and take questions.
Hi, thanks. Really, really nice talk. I'm curious about the sea surface height composites. It does seem like a really cool result. I'm wondering if you have thought about the integrated effect of multiple ARs causing a more persistent sea surface height response over longer periods of time. If I understood your methods right, this is just over a few days, but...
No, this is over the full 40 years. This is the composite, yeah. Oh, you mean with 3 days before and the cumulative, yeah.
Is there the possibility, does the possibility exist that you could get these AR-driven sea surface height anomalies that persist much longer than these weather timescales?
Dylan, that is a very good question, and we have not looked at it. But yeah, we should put that on our list for sure. Sorry, I don't have an answer for you.
Gave a talk about wanting to do a CESM 3 ensemble for looking at blooms, phytoplankton blooms. And I guess my question is, what do you think is the right resolution for doing that kind of stuff based on the sort of SST fields that you've been looking at?
The right resolution for the blooms?
Yeah, I mean, if you're interested in these blooms, they have a lot to do with the sort of coastal upwelling and things like that. I mean, I would guess from the results that you're presenting that you might want to do those at a relatively high resolution, and then there are some computational sort of implications of that.
Yeah, I would agree with you, but I'm not an expert in the ocean modeling. So Hui and Fred and Dan were my ocean experts. So I would think that we would want to use eddy resolving or high resolution in the ocean for those in particular, because I would think that it might be regional impacts up ocean would matter. But I don't feel like I can really answer that question.
Okay, thanks.
Yeah, sorry.
Yeah, our next speaker is Adam Harrington from NCAR, Climate and Global Dynamics Division, and he talks about high-resolution CSM.
Hi, everyone. As we were envisioning putting this session together a few months ago, I decided I was going to try to make a contribution. And so this is the result of that few months of work. And what I really wanted to understand is what can we do with the spectral element dynamical core that we currently have in CSM? So what can we do now with what we have at ultra high resolution? And I leaned heavily on my contributors, Julio Backmeister and Brian Dobbins. So first, a little motivation. There's been a lot of variable resolution studies using CSM lately that have been resolving weather processes. This is a recent paper led by Rob Wills, where we did regional refinement at 28 kilometers over the North Atlantic and then 14 kilometers or eighth degree over the North Atlantic. And what we're showing here is just snapshots shots of a storm going over an SST anomaly that's in that rectangle. And you can see at 1 degree, it's just kind of one big macro structure that represents the synoptic scale. When you go to 1/4 degree, you start populating your cold fronts and your warm fronts with individual elements. But your grid spacing is so coarse that these elements are pretty big and they just don't really provide a realistic picture of a front. And so once we went to eighth degree, we really started to see that the individual convective elements that are populating these cold fronts and warm fronts are starting to produce realistic structures. And as a result, you actually have more vertical transports at quarter degree of momentum and heat, and that actually does impact your large-scale circulation, response to SST anomalies. And so, this is opening the door to understanding variability a little bit more beyond using our 1 degree model. So this work is going to be not focusing on variable resolution, but global high and ultra high resolution. With the uniform SE grid, we can utilize CSLAM, which is an accelerated tracer transport method. And so these PG3 modifiers are telling you this is the CSLAM variety of SE. So I'm going to be looking at 3 different grid resolutions, NE120 PG3, NE240 PG3, and NE480 PG3, which is 7 kilometers. And once we started, it wasn't until I got to NE480 that I started to experience limitations on basically CSM and derecho. And these are the same issues that are coming up in the earthworks and the SEMA projects, which are dedicated to trying to get global ultra-high resolution empaths working in CSM. And so I certainly benefited from the solutions that they have provided to resolve those issues in order to run NE480. These issues are expected as CSM wasn't developed for this, but if we can work through them, CSM brings complexity to the ultra-high resolution community, whether it's in the form of all the different component models that we offer, such as the ocean and land ice and CLM, or the complexity within the atmosphere itself. For example, we're going to be resolving the stratosphere in all these runs with the 80-kilometer model top. So these are some results of some year-long plus simulations of NE30 1 degree, NE120, and NE240. And these are latitude, height transects of the austral winter polar vortex. And so our y-axis is going all the way to the 80-kilometer top. And this is ERA5 over here. And you can see that ERA5 is quite a bit different from our 1 degree solution, and that has this tilt, and it's not as excessively strong. And we just see these improvements in the structure of this polar vortex as we go to quarter degree, and then we go to eighth degree in terms of the magnitude and the tilt of this polar vortex, which you can start to see here. And so this was promising. And we do also note, though, that we saw some changes in the tropospheric subtropical jet that wasn't so desirable, some weakening. And so, we may want to consider turning off our gravity wave parameterizations to explore if they're providing excessive drag over those jets. The mechanism is basically gravity waves. And so this is the zonal mean flux of zonal momentum in the zonal height space, and this is 1 degree. And you can see, and then you have our NE241 here, and you can see we have all of this drag here being exerted on the polar vortex it's reducing its magnitude and causing it to tilt, that you're not capturing at 1 degree. And in terms of the mechanism, I think it's quite similar to the WACCM RR talk that we saw earlier today. Here's just a snapshot of the NE2040 simulation, and I don't know how well the colors, oh God, the colors are all blue. But the sort of the high frequency or the really detailed structures of the omega field at 44 kilometers, so we're in the stratosphere. And the contours are the sea level pressure. And so a lot of times these gravity waves that are already into the stratosphere by this time are coming from sort of frontal type dynamics. They're associated with fronts. Sometimes they're associated with orography, but nonetheless they are there, and they are helping to improve the the polar vortex. So now I'm going to step into NE480. And so I want to just outline some of the main issues that we had to deal with and we're still dealing with. The SE die core is initializing this big grid NE480 on every single processor. And this is a derecho node over here on the right. It has 128 AMD processors, but all sharing this 256 gigabyte of memory cache. And if you initialize a big NE480 array on each one of these processors, you run out of your 256 gigabytes of memory. And so this needs to be made scalable, and I don't think it would be too difficult after talking with Brian to do that. ESMF calls at CSM initiar non-scalable on high core counts, so they tend to be quadratic in execution time with core count, and so that does actually provide us a limit on using very, very large number of cores. And then the other one was, it sort of mirrors Aaron's talk about how important it is to consider your I.O. and to be not overly excessive, write out stuff you don't need. Well, we have CAM restarts writing out tons of variables, and they haven't been optimized in how they're ordered, and there's quite other issues as well. So right now it takes about 2 hours for me to write a restart file in my NE480 run. So those are the issues, but in terms of like input data sets and boundary conditions, I didn't really have any issues, none that really rise to the level here to talk about. And I also want to point out that the land model has a new surface data set generation toolkit that works very well. I was able to generate NE480 boundary conditions with ease. The throughput that I'm getting on an NE480 run, so I can run on 900 nodes. You can run this on the weekend. Anybody can get a 900 node job through the weekend. So any old person can really take advantage of this machine if you're willing to work those extra hours. But you know, so with this big grid, 12 million grid columns, and we got 93 levels. We needed to undersubscribe the number of processors on the node in order to get around the SE grid init issue. This is just a workaround. But with all that, we ended up with about a 45-minute init time. Not terrible. We can improve on that, and we plan on it, but we can do science with that. And once we're getting to running, we're actually running on 900 nodes about 1 hour per simulated day, 1.5 hours with high I.O. So that means if you have a 12-hour wall time, and say you don't want to write restarts because you don't want to pay for 2 hours to write a restart, you could do a 8-day, 5-day simulation. You can do some science. And so that is what I'm going to kind of show you next here. After I'm going to skip that one. But before we go into science, if my experience publishing 7-kilometer grids is that there are people who don't think you should be able to run a hydrostatic model at 7 kilometers. It's not appropriate. And so I just want to point out the arguments in both, for both cases, for it and against it. So conventionally, the idea is that length scales on the order of 10 kilometers require non-hydrostatic dynamics. And that's primarily based on scale analysis of dispersion relationships. And this 10 kilometers basically comes when your horizontal wave number approaches your vertical wave number. And the largest vertical wavelength you can think of would be the depth of the troposphere. So that's where 10 kilometers comes about. And models don't resolve dx. They resolve 5dx, 4dx, depending on the model. And so the effective resolution of 5dx, you're resolving length scales with a dx of 2 kilometers. So you're well within you're okay according to this argument to run a hydrostatic model at 7 kilometers. There are 2 papers that came out recently, or maybe more, where people switch on. They have a switch on their model that turn on non-hydrostatic dynamics, and they show that you get that these non-hydrostatic dynamics matter as coarse as 25 kilometer resolution. So it sounds like there's still some debate in the community on whether or not the 7 kilometers is appropriate to be running non-hydrostatic dynamics. I have a kinetic energy spectrum from an NE480 run in pink here. What is it? Oh my God, it's blue. So the shallower one with the arrow pointing to it is supposed to be pink. And then the compensated total kinetic energy is in the right. So that's basically scaled such that a horizontal line gives you a negative 5/3 slope. And so you can see that at NE480, We're not even resolving 10 kilometers. We're well in the dissipation range, and that's not an effective resolution. And so our effective resolutions are more like 40 or 80 kilometers. This run I initialized with 0 winds, which is why the entire slope is -5/3. The sort of synoptic scale macro turbulence is not yet developed. It's a 5-day simulation initialized with 0 winds. So my last slide is trying to do a little better than that. So ideally, I want to map an ERI5 data set to the model grid, provide some type of adjustments for the topography, and run it stably, but we did not provide that workflow in time. And so we took advantage of the nudging capabilities in CAM. And so the approach for initializing is, if I want to initialize, I would start the model and I would nudge it to ERI5 for 2 days, and then I would turn off the nudging, and that's the initialized time. And so this is just an animation showing that experiment. So I did this for the March 2022 atmospheric river. And so it's just a 5-day run, nudging for the first 2 days, and then off at the end. And I'm not sure how these colors are turning out. But what's interesting is when you nudge, you've put a sort of headlock around the model, and it can't start developing its own divergent modes. And so the kinetic energy spectrum is very weak in the -5/3 section in the nudging part of the simulation. But as soon as you turn off the nudging, you jump up into these curves up here to start giving you those divergent modes that naturally the model wants to support. And I think that would occur also if you, I'm sure people know this, I'm not a weather guy, but I think that would also occur if you just had an initial condition that you adjusted from reanalysis. As soon as you put it on, as soon as you run it in the model's going to want to kind of go towards its attractor, and it's going to start supporting some divergent modes. Anyhow, this is an approach. I plan to do some science with this. I'd like to study the impact of this atmospheric river on melting of the Antarctic ice sheet and the precipitation. But this is as far as I got in the few months. So that's what we can do with what we have now. And I'll take any questions you have.
Wondering whether you have any issues with the support files like topography generation, land generation, or the files you need to accomplish these high resolution runs. Can you briefly talk about that?
So, the land model will take some time to spin up, and the approach that I did take is I actually nudged the NE120 run for 3 months with ERA5, and at the end of that 3 months, I'm on my initialization date. I take that CLM restart file, and that's my initial condition for CLM. Like I said, the boundary conditions for CLM were so easy to run. The topography data set for CAM works great. It just takes, less than a half hour. We have a lot of coarse input data sets on 1 degree that we are, so the aerosol forcing files are probably not very accurate to be running at any 480, but we are using a lot of 1 degree data sets in these simulations, and that could be improved on. So if there's no other further questions, I'd like to bring in our next speaker, Mary Barth and Brian Dobbins, and they're going to talk about CAM MPAS and SEMA. This just naturally switches over for you.
Yep. So good afternoon. I'll just start talking before the slides show up. We're talking about advancing the high resolution capabilities and the complex chemistry capabilities in CAM. This is work that's being done as part of the System for Integrated Modeling of the Atmosphere, the SEMA project. And I just wanted to start by reminding you of
what the CEMA project is, it aims to enhance the frontier science simulations with one modeling system. So doing Earth system modeling for climate, weather, atmospheric chemistry, geospace, and cross-discipline research as well. So being able to go from the surface to the ionosphere, storm resolving to climate applications. We have two major activities that we're doing. We're developing software infrastructure to make this possible, but we're also demonstrating the science of the new configurations. And so I'm going to talk about some work that we've been doing simulating complex chemistry, work that I've been involved with the Asian summer monsoon. Also talk about a new project looking at extreme weather events. And then Brian will talk about the capability for global storm resolving simulations. So let's get started because it's not very much time. I'm going to begin talking about trying out CAM with the MPAS dynamical core and full chemistry. So this is testing it. Does it even work? And we've done a number of simulations where we are running a grid mesh focused over the Southeast Asia region to look at the effects of the Asian summer monsoon on the composition. And so you can see our regional refined grid in the, on the right there. And then we have a uniform grid at 60 kilometers for comparison. Full chemistry, emissions, and their free running runs. We're just doing a case study for 5 days in August of 2021. And at this point, I apologize for not writing down all the people who contributed to this because it wasn't me. Francis Witt did all the simulations. Bill Scamrock helped get things going. Ren Smith did a ton of work in helping for the analysis. So I really appreciate that. Okay, I think last year I talked about this briefly and showed you results like this. So this is propane in the upper troposphere, 14-kilometer altitude. On the top, I'm showing the regional refined grid results. On the bottom, I'm showing the uniform grid. Left is 32 levels, right is 58 levels. And you can see for this daily average mixing ratio that you have pretty much the same large-scale patterns. Things are looking pretty good, pretty similar among the different models. There are small differences, of course. What I didn't show was NOx. Nitrogen oxides, which is not only affected by transport, but is also affected by lightning chemistry. And again, the same layout. And we see some much larger differences here with high NOx mixing ratios over Africa and southern India in the regionally refined simulation compared to the uniform one. And that's a head scratcher because, wait a second, it's 60-kilometer grid spacing over Africa in both simulations. And so we thought there might be a couple of reasons why. Was it maybe the shorter time step that's being used in the regionally refined simulations? Or is it the lightning NOx production? And so we can look at the time step by just making use of the uniform grid and running it at a shorter time step. And so what I'm showing here are the results for NOx at 14 kilometers with the 22nd MPAS dynamical time step, but the same physics time step. And you can see that looks much more like the uniform grid in the bottom left than on the top left. If we also decrease the physics time step again, you see something much more like the uniform grid. And so it appears that the time step is really not causing this major difference in the NOx simulations. So let's go to lightning NOx production. And so I'm just zooming in on the Africa region here. And on the left is the lightning NOx production rate in parts per trillion per hour, regional refinement on the top, uniform on the bottom. On the right is the flash rate. And so when you look at the lightning NOx production, you do see a major difference. And it actually looks like a fair bit of my colors came through, not all of them. And, but there is much more lightning NOx production than there is in the regional refined compared to the uniform. If you look at the flash rate, you don't see a huge difference. And you can maybe quantify that a little bit. And so I tried that by summing the number of flash rates in this pink box. That's turning blue. And then show the results here, with, of course, different colors than what I'm looking at. But what you find is that there are not huge differences, but there are actually fewer flash rates in the regionally refined simulations than in the uniform. So it's actually opposite of what one might expect. That leaves going to the next step where the lightning knocks actually also depends on not only the flash rate, but is also scaled by the area of the grid box, and I think that's where our issue is showing up. So when you have varying sizes of grid boxes, you have to make sure you actually have the right area that you're working with. And so I'm going to go back to what Aaron said about opportunities to relook at your code and make sure it's working right for your new cutting-edge simulations. Since I had the time steps and cloud top height, the convective cloud top height might be affected by the time step, I also plotted the flash rate, just getting this global flash rate information that's popped out in the log files. And you can see that there is a time step effect on the flash rates. The bottom line, which is also blue, the bottom line is with the 20-second physics time step. So there really couldn't be a factor there. I also want to note that in these simulations, the convective parameterization does not turn off in the 3-kilometer region, and that allows us to have lightning knocks protection in that region. So when we go to scale-aware convective parameterizations, we're going to have to adjust any parameterizations that might be focused on parameterized effects. Okay, I want to move on because I know my time is probably passed already. But I want to advertise this other project. It's looking at extreme weather events using WACCM with the MPAS dynamical core. And Wei Li is leading that. It's this project called Subseasonal Sun to Surface Prediction System. You can see everyone else on the team who's helping out with the science goals of looking at the role of small-scale processes on extreme weather events and determining what's the value of the refined resolution on the events. So again, their configurations is with WACCM, with the MPAS dynamical core, CAM7 physics. This time we're going to go up higher. We're going to use WACCM and try to get all the way to the lower thermosphere. They're looking at 2 extreme events, the cold air outbreak in February 2021 that hit the southern US, and then a heat wave a few months later in June of 2021 that hit the Pacific Northwest, and they'll do 10 members ensemble simulations. The things I really want to point out here is that they're now at the point of having a successful test with it using CAM at the 58 levels configuration and the desired configuration that's shown here on the right, so zooming in over the central US. And then I also wanted to highlight that outcomes will include a streamlined workflow, user repository, and a step-by-step guide of how do you run CAM or WACCM with MPAS dynamical core and get things set up. And so with that, I want to switch over to Brian and leave him a minute to talk over 5 slides. No, just kidding.
Thank you. So I'm going to go pretty quick here. I'm going to give you a technical view of basically the challenges here with the scale of the global high resolution, some of the successes we've had, and some of the challenges we still have. So I like to start with this. If you're looking at a global 3.75 kilometer, it's 32x in the latitude, 32x in the longitude, 2.9 times more vertical levels, 30 times the time step, and about a 10% more expensive physics. This is about 100,000 times more expensive than a standard CESM2 model. That's pretty large. Derecho has 322,000 cores. Imagine if Cheyenne had 3.2. That's sort of the scale that we're doing this on. And on that note, how do I switch? Oh, do I use this? Got it. All right. So Derecho is 3.5 times faster than Cheyenne. So optimistically, we only have 28,600 times to go until we do everything that we're doing now at this new scale. Now, of course, we're not going to do that. There's a lot of good science we can do here. Nobody's going to wait 40 years. Some of you younger people, maybe. That'll be great. But there's a lot of great science, but it's just not going to apply to everything we do. And I think we just need to be clear about that. Okay. Some of our successes. So this is a big problem this is like a moonshot. You're trying to do something really novel. So we started with a bunch of simple cases. So we started up from simple atmosphere models, got a little bit more complex with the physics, tried a land case, then tried to put it all together. When I was putting these slides together on the weekend, we were testing this FLT HIST. This is our target CESM3 case. It wasn't running yet. I don't have a lot of time, but I'll say in addition to cases, we test across a number of processors. The really exciting thing here, we ran out to 164,000 cores on Derecho. It's more than half the system. And we scaled perfectly with the, all right, it was 1% more expensive than what you would get if you extrapolated. I'm fine with that. Because this is the CSM workshop and you get the latest information, last night we actually ran the FLT HIST 58 level successfully. So this is a great milestone. We've got all this going. Now, to get there were a lot of challenges along the way. We had problems, as Adam mentioned, with initialization. We have problems with large writes and I/O. My favorite is this low-res data. This was a really interesting one. When we ran on more than around 55,000 cores, it would crash. Well, why? Well, because we're using these 288 by 192 finite volume input files, which comes out to 55,300 or 296 points, and we couldn't interpolate when we had more processes than ranks. We just never anticipated doing that. And I'm going to point to Aaron here. So we don't have a lot of modular testing that allows you to do things. I bet we could have made this progress 3 times faster if we put in the effort to have that. So this was very slow and difficult. I like to talk about software. It's not magic. People think that, hey, we've got I/O. Why doesn't it work? Well, this is like saying you have a plane. We just want to fly it 40,000 times higher and go to the moon. Well, I think we all know this would not work, right? Same with software. You have to redesign it when you're going beyond your current mission. So this is an important thing to focus on. We also, it's not just software. We identified some interesting system challenges. This first one is really interesting to me. This was, we try to send some data around. To send a 1 byte all-to-all V across 1,280 nodes, it took 13.2 seconds. I could walk the length of derecho faster than I could send a single character to all the cores. And this is not a problem with all systems, because down at Stampede at TAC, or Frontera at TAC, it took 0.4 seconds for the same operation. So we have to think about this. The one on the right, I know I'm running low on time. This is a cool one. We just changed the MPI library of a very simple test, and you see different memory use. Do you know what this application was? It's 4 lines. It's MPI, init, and MPI finalize, and that's it, really. Init main, int main. So really interesting stuff. Another design consideration, because these are such large problems, is the amount of memory we have per node. Adam touched on this too. We should rethink how we design our systems. HPC world talks about capability and capacity systems. This is a capability type of project, and we've often done capacity. NASA's newest system has 8 gigabytes a core to accommodate this. We might need to get more memory per core to help with these. So Dave had a quote by Douglas Adams in his talk the other day. I love that quote. I decided to use a different one. This is SEMA. I like to talk about SEMA the same way. SEMA is big. You wouldn't believe how vastly, hugely, mind-bogglingly big SEMA is. It's trying to do a lot of different things, involves a lot of different people. And there's science and software systems, which aren't really as appreciated much, and support. I'll specifically say Domi Colgrove and Jordan Powers and Mary have done a great job keeping this massive task on point. And I will say, this is my thesis, that ultra high resolution, it's a really easy thing to say. It's a milestone for SEMA. But if we're going to do this well, it's a really big co-design issue for the entire community. We got to think how we do this better. We have the capability now, but how do we make it more robust? And I'll turn it back to you for your last few slides. I think you have a few here. Oh, yeah. All right. Oh. I thought you had a few more. Questions for Mary or I? Oh, great. Everyone's happy. Everyone's going to run high res. All right. All right. Yeah. On the weekend. Sure. Right. Yeah. You're giving away the secret there. Yeah. That's how I've gotten work done. Yeah.
Thanks. The next talk is Dave Randall. He's going to give a progress update on Earthworks.
This thing?
Yeah, that thing. And the big one puts the slides over, and the top one is pointer.
Okay.
If you have the patience for it.
Yeah. Okay, thank you very much. Many of you have heard about Earthworks before, but here's a primer. It's a 5-year project, started in the summer of 2020, so we're almost 4 years in now. CSU is the lead, NCAR is a key collaborator, and so we're working with 3 different NCAR laboratories, as well as the CSU effort. And the goal is to develop a global convection permitting and ocean eddy permitting coupled model based on CESM. Earthworks is supported by NSF SISE, which is the Computer Information Science and Engineering section of NSF, but with some funding from GEO through SISE. The CSU NCAR split in the funding is 60-40. So Earthworks is also partnering, as I'll explain here in a minute, with the Department of Energy through our use of the MPAS Ocean, which is the ocean model used by E3SM, and also interactions with Andrew Gettleman, who used to be here at NCAR, but now is at PNNL, and the ocean modeling scientist at Los Alamos. So this is a team effort, and this has been emphasized already, but here's a list of names, and I hope I haven't missed anybody, especially I hope I haven't missed anybody who's in the room. But the list of organizations is down here. I can get this thing to work. You can see there are 8 altogether, including some participation by NVIDIA. We're not paying them, but they're helping us. And NCAR software engineers, including Brian Dobbins, who was just up here a minute ago, have been absolutely key to our progress. And a couple of the slides that I'm going to show were created by Rich Loft and Sherry Vols. So the vision of the project, that's the place to start, is we're using CESM as a base, and we're creating a coupled model with a 3.75 kilometer geodesic grid. There's a picture of a very coarse geodesic grid at the bottom of the slide. Same grid used by atmosphere, ocean, and land surface. And this strategy is central to the Earthworks vision. We are working to develop improved parameterizations that can work well with both 3.75 and 120 kilometer grids and everything in between, and use the model to study both weather and climate. That's quite important. So timescales ranging from days to years. So the components of the model are the MPAS atmosphere, which you've heard about already, the MPAS ocean model, which I mentioned briefly, almost the same dynamical core. Obviously, there are some differences because water isn't air, but close. MPAS sea ice model, which is based on CICE, the CLM, and the CMEPS, which is the mediator or coupler used by CESM. And we plan to use CCPP when it is available to us. So the scientific goals are, of course, to replace the deep convection and gravity wave drag parameterizations with direct simulation, to demonstrate the resolution-dependent advantages and disadvantages of using the same grid for all components by comparisons, use the model to study the interactions of mesoscale weather systems with larger spatial scales, so upscale, as we heard earlier, on timescales from days to years. Use lower resolution versions of the model to study century scale climate change. Of course, you can still do that. And perform deterministic forecasts. This is the weather mode, days to S2S, with a higher resolution version of the same model that is used for climate change experiments. So this is a strategy that can make shareholders more comfortable with the model as it is applied to climate change. Use the model to understand deficiencies of lower resolution versions of the same model and perhaps to create training data sets for machine learning. So, computational goals. Those were the science goals. I added a new bullet at the top of this, and I'll say more about it on the following slide, but find and fix issues with CESM infrastructure, things like I/O and so on, that prevent CESM from being used with very high resolution. So we're working through this, and you've already heard some of that from Brian. Provide CPU compatibility for use at low resolution, let's say 100 kilometers, and for short tests with ultra high resolution. And I've got a typo here somewhere. Provide GPU, it should say, right there. There we go. For ultra-high resolution simulations. And the goal is 1 simulated year per day on the 3.75 kilometer grid on a DOE leadership class machine, or perhaps at TAC, we'll see. So, issues encountered and fixed. And this is some of the same stuff that Brian mentioned, because the issues that we've encountered are the same issues that SEMA has encountered using MPAS-A. So, initialization, very, very slow. Trace to an issue in ESMF, a library that CESM uses. And so a fix was found, a patch, and the impact was a major speed up and a reduction in memory use. Initialization, MPI communication traced to another issue in ESMF framework and another workaround. Large slowdown in history I/O bandwidth, traced to a problem in BNet CDF, and expected performance restored. Run after restart errors. So at one point we couldn't even write a restart, and then restarts took a ridiculously long time to write. And then we got to the point where we could write them successfully, but we couldn't restart from them, which means they're not terribly useful. So this has also been fixed and works as it should now. And I/O performance issues of various kinds, and this has been worked. So I'm showing one slide here with a few results from a simulation being analyzed by a graduate student of mine at CSU. And this is with a 30-kilometer grid, so this is not 3.75. So we have observations on the bottom. You're looking at tropical cyclone tracks. I hope you can see the colors. Yeah, you can see them. And the upper panel is a 10-year simulation. This is atmosphere only, not coupled, for the years 1990 to 99. And so the comparison is apparent. So reasonably good agreement between the observations and the simulation. And student also has a simulation with warmer future temperatures from the end of the century, and one like that with SAI. And so that's the project. So we have released several versions of the code now, and very recently, on June 3rd, we released version 2.2. The GitHub address is there, so if you want to go there, get your camera out and click. We have now multi-platform support. We're working at TAC, the Texas Advanced Computing Center in Austin. They are in the process of installing a Grace Hopper system. Some of you will know what that is. It's NVIDIA. The Grace parts are CPUs, and the Hopper parts are fast GPUs. And the memory communication between them is done in a relatively quick and clever way. So we're in the early days of testing on that. So the new release also has a multi-component GPU offload. That means we're able to run various components of the model, including microphysics, radiation, club, and the dynamical cores of both the atmosphere and ocean on GPUs. The GPU performance is not optimized yet, but it is running. The new release allows relatively straightforward out-of-the-box configurations, just like CESM, and more straightforward ways to do testing, and a developer's guide with some documentation. So currently what we're doing is running very short, ultra-high resolution, 3.75 kilometer simulations to identify issues and work our way through them. Testing the atmospheric model with GPUs, that's a sort of separate activity. Maintaining the repository to make sure that it stays in sync with CESM, which is changing all the time, and developing workflows for data visualization and analysis. And some of the things that Aaron mentioned yesterday or earlier today are also on our radar. So next steps, we need to optimize the radiation and club, continue to improve performance on both GPUs and CPUs, and identify and fix the I/O performance issues, and study the performance of the fully GPU-ported model on Grace Hopper. So looking ahead, the CESM Scientific Steering Committee have agreed to designate the model as CESM-E, E for Earthworks. Support of the model is divided between NCAR and CSU. CSU is taking on support of the ocean component of the model, and of course we'll be working with DOE on that. And CSU and NCAR are currently working on a follow-on proposal, which if successful would have a start date of next year. So that's it. Thank you.
Questions for Dave? Question, when you had talked about optimizing RTM GP and club, do you mean for GPUs or for CG?
Yes,
okay.
for GPUs.
Gotcha.
Yeah. Oh, there's a question.
Really interesting talk. I mean, it was interesting that you talked about all the synergies with CESM, and how your project can benefit the general CSM community. And I'm here thinking about the NOAA perspective. As you know, we are now doing several experiments with MPAS, standalone, and in the future in the unified forecast system. And lots of the things you mentioned are also of interest to NOAA. In particular, RTMGP, we've been wanting to get that going for the UFS, but it runs too slow.
And ESMF too, I believe, right?
ESMF, and also something that was interesting to me was your workflows for visualization on the native grid, because we're actually also working on that right now. So I think there is another overlap there that we can start exploring.
Yes, that's a good thing. Thank you for pointing that out.
Okay, I think we should move on to our next speaker. We're running a few minutes late, but I think it's okay. So Gökhan and Christian Jabanowski are going to give a talk about...
Two talks.
I guess these are back-to-back talks about whatever Gökhan's going to talk about, and the non-hydrostatic SC effort that Christian is talking about.
Right, well, thank you. And I wanted to thank Christian in particular, because this was like a last-minute insertion into the agenda. So I just wanted to provide you a brief update on our new, relatively new project. That's MESACLIP. It stands for Understanding the Role of Mesoscale Atmosphere-Ocean Interactions in Seasonal to Decadal Climate Predictions. It is a joint effort. It's a highly collaborative effort between NSF NCAR and Texas A&M University, and all the list of characters are they are given here. You previously heard about IHASP, and this is in a sense continuation of the IHASP project that was terminated back in early 2022, and NSF stepped in and we wrote a proposal to fund some of our continuation simulations. So this is an expanded list that was shown by Dave yesterday. We are using in this project an older version of CESM 1.3 that was originally created by Frank Bryan and Justin Small. And it uses 10th of a degree ocean and sea ice models coupled to quarter-degree atmosphere and land models. We have what I would call an unprecedented set of simulations. Quite a few of them have been already completed, and some of them are available to the community. Some of them are just recently completed, and decadal prediction simulations in particular, they are still ongoing. I wanted to highlight that we have already completed a 10-member ensemble of transient RCP 8.5 simulations, another 10 members available for RCP 6.0, 1 member each for RCP 4.5 and 2.6. We are also looking into ozone withholding experiments to understand some of the changes in the climate associated with ozone. We have 3-member high-res 1950-2014 AMIP simulations. We participated in high-res MIP, and we have the full set of high and low-res equivalents. We have 5 cycles of OMIP, that's ocean model forced. 1 cycle includes biochemistry. We are expanding the decadal prediction simulations. We are adding every other year. It was every other year initialized in November. We are adding the missing years. With November, we are also adding May initialization for all those prediction simulations. They are 62 months each. The last, in parentheses, is not related to MESA clip, but Betty requested that I include that simulation as well. It's using the similar high-res version. They have 60-year high and low CO2 past periods using the same set of simulations. We are making these simulations available to the community following the CESM guidelines. We severely underestimated the storage needs. With added fields and higher frequency fields, particularly coming from atmospheric side, we now hit 6.8 petabytes. It is well, it's estimated to be 6.8 petabytes because we are still completing the simulations, and we are trying to figure out a way how to serve them efficiently to the community as soon as possible. And our target date is starting in September and probably through December of this year to make these available, full set available to the community. So I don't know whether you are familiar with it or not, but in April 2023, presidents, this is US president, not the UCAR president, President's Council of Advisors on Science and Technology issued a report on extreme weather risks in a changing climate, and they recommended the following, two things. A focused federal effort to provide estimates of the risk that a weather event of a given severity will occur in any location and year between now and mid-century. And they also suggested that United States create a multi-model ensemble, ideally more than 100 members, of climate simulations at 10 to 25 kilometer resolution, spanning the 20th century and extending through 2050, consisting of simulations from various modeling centers. So in response to this, NSF-NCAR actually provided a memo to the White House. So we are now in collaboration with MCube and CGD and Texas A&M University, we are providing select data sets from our 6-hourly output of key variables for use of insurance and financial sector of the United States. There's supposed to be an ICANN, okay, it's working actually. So this is supposed to show some atmospheric rivers and induced precipitation in CSM high-res. And I wanted to thank CESL folks essentially for helping us create these visualizations. Just a few things, highlights here. This is showing the 1981-22 wintertime extreme daily precipitation over the United States. These two plots are from observations, NOAA and PRISM. Low resolution, as expected, nothing major. And this is high resolution simulation. So we were quite pleased that we are actually matching the extreme winter precipitation in the southeast United States. For comparison, this is WRF, 4-kilometer resolution. I suspect this is suffering from same issues that Andreas talked about. It is actually higher in magnitude, but you can essentially provide a more quantitative analysis of this comparison. These are showing the probability density distributions as a function of precipitation rate. The lower line is low res. The observations are actually two black lines. They are truly black. And then the high-res simulation is actually shown by sort of now showing up as grayish line there. So it's right on top of observations. The upper curve, which is pink actually, but it's showing up blue, is WRF. So it's overestimating the extreme precipitation at 4-kilometer resolution. So that probably needs more work, as Andreas was actually mentioning. Tropical cyclones, this is not a new plot. We actually showed this thing in Ping's paper in 2020. Observations are on the left side, high res is in the middle, low res is on the right side. And we are actually, well, you can't see the color coding, unfortunately. We are doing a lot better, obviously, compared to low res. We are overcooking the spatial extent or latitudinal extent of the tropical cyclones, and we are somewhat weaker than actually observed strengths of the tropical cyclones. What we can do now is essentially, with all the ensemble members that we have, we can look at other questions, like what are the changes in tropical cyclone occurrence, say between 2070 and 2100 compared to sort of 1950 to 1980 period. This is a new plot, and it is essentially showing that These are number per year, so it's actually estimating a decrease in the frequency in certain regions in the Atlantic and the Indian Ocean and South Pacific, whereas there's an increase in the occurrence in the Northern Pacific. We can also take a look at, for example, trends of annual mean, tropical cyclone induced rainfall. You can see some increase in the Southeast United States. And this is the plot this is my last plot. Dave's version was a lot better because it was showing the true colors, and I shuffled the panels here. These are sea surface temperature linear trends for the 1980 to 2020 period in each ensemble member from 8.5 simulation that we have. Low resolution is shown at the top left. It doesn't matter whether you look at a single member or ensemble member, and this is pretty much the case across CMIP5 and CMIP6 simulations. The observations are here as SSC is shown here, and they're at least showing up as blue. I put the the 10th member of our ensemble right there, and you can see that there is actually pretty good agreement in the Southern Ocean. I point this out, this is rather important, because what we are finding is that getting the right trends in the Southern Ocean seems to be impacting the equatorial Pacific, and in turn it's actually changing or increasing the decadal skill or prediction skill that we have in our simulations. And I think this is associated with the representation of mesoscalities or their incorrect representation perhaps in the low resolution models. So we are looking at in more detail, but this would actually advocate for use of really 10th of a degree ocean model in this kind of, in these studies. So I'll stop and pass it on to Christian. I'll take the questions later. Yeah.
So my talk is actually an advertisement, so I'm not really showing you science results because we don't have them yet, but I want to just get the word out what we are up to and hope next year here at the CSM meeting we have actual results to show. This is a new project funded by NSF. We call it Storm Speed, and the idea is that we will include a non-hydrostatic spectral element dicore from the DOE into the CSM framework. And you see the collaborators here. This is a team from University of Michigan, NCAR, and TAMU, and also we have collaborators, Mark Taylor from the DOE and also the Earthworks team. So yeah, maybe I'll keep this really brief, but you know the status quo. We have seen the IHASP and also the MESACLIP results. These are good-looking high-resolution simulations, but let's face it, these are model versions from back 10 years ago. We are looking here at CSM 1.3, and we don't really have a lot of progress on the newer versions of CSM at the high resolution, and that is really the contribution that we are making with the kind of the state-of-the-art CSM configurations here, CSM 7. So we are claiming we are missing opportunities that we are not able currently because of, for example, a missing non-hydrostatic dicore. MPAS is coming online, yes, but it's not currently the default for CSM. So we are basically now adding a non-hydrostatic capability to CSM to kind of change the picture. The goal is, yeah, to turn CSM into a kilometer scale or ready model to enable the community to do kilometer scale simulations and contribute to, yeah, the global community of kilometer scale modelers. The global community, you might have seen this, is a diamond project. A quick look here, we have about 10 models in the community, international community, that can do kilometer scale modeling between 3 and 9 kilometers here. This is one project called Diamond, and you see just a snapshot of satellite image. One is circled, that's actually an observation. Don't dive into the results here, just another kind of snapshot from the literature. If we look even further, there are even models in the community that are now run at like 1.4 kilometers. Here are two from the IFS, the ECMWF model, and also ICON, the German Weather Service MPI model. So this is actually the horizon. Yeah, we are now shooting, and this is really what we are up to, like a 3-kilometer mesh, and we are using Scream. You saw that actually here from Aaron. This is his standstill image, and this is now the animation of it. This is now a one-day animation of the outgoing long-wave radiation from Scream, and this is basically now the vehicle to get to high resolution, ultra high resolution with CSM. So, okay, what are we doing? We have 3 things in mind. We do it quickly, meaning we are not doing it from scratch. We are now borrowing basically from DOE the existing non-hydrostatic capabilities of SCREAM and also the Fortran version, and we put this into the CSM framework rather quickly, especially the Fortran version, meaning this year. With this, we will have basically a workhorse for some exemplars, scientific exemplars, which will focus on mesoscale convective systems, as also Dave Randall pointed out, and some like ERC interactions with tropical cyclones and precipitation. These will be the flagship exemplars. We also bring in a second step the COCOS version that we heard about from SCREAM, and this will now enable GPU capabilities in CSM in the future. And we will then test and demonstrate, actually, as I mentioned in my last bullet point, the capabilities in a scientific setting. Okay, I only have one more minute, I believe. What we really push is, the GPU readiness with this. Again, this comes in as a second step for us, but as we heard from Aaron, they are approaching this problem with an MPI COCOS implementation in C++. This is one of my, let me kind of see whether my bullet point. This is exactly what will come in as a second step, like a year and a half probably from now. And the advantage, I just kind of give you, and then I close, advantages. As we heard from Aaron, this is even a newer diagram. This was published by Mark Taylor and co-authors last year when they won the Golden Bell Prize, like a real prestigious prize for high-performance computing. And we see, I guess, this is a measure. Oops, let me see whether not certain here. We see these are numbers, simulated days per day, per wall clock day, and with this, this is the COCOS version of SCREAM, and here's a full model. This is the atmosphere only, so we see impressive numbers that we can use with SCREAM to get really high-performance computations through. All right, my last slide. Oops. Scientific drivers, I mentioned the mesoscale storm systems and also the ERC interactions, but let me close, and you will hear about it next year. Let me just close with some benefits for the community. So it's an ability then that we will enable the community to do this, basically simulations at the weather-climate interface. We will provide exemplars, meaning code and data for everybody to use. And it's of broader impacts when you kind of look at the big landscape, enabling, yes, kilometer scale simulations, but also bringing together several labs at NCAR, CGD, M-Cubed, and CISL, building really strong relationships with the Earthworks projects and Brian Dobbins, and all the legwork that they have done will benefit us great time. So I don't think we could have really done this project without their initial work. So we are building on top of that, and we want to train the future generation of scientists. And I close with an advertisement. So for the young scientists and students here in this community, we will have a workshop next year. We call it DC MIP. We have done it a couple of times. You see some of the figures here. It will be a week before the CSM workshop next year here at NCAR at the Mesa Lab, and we will put out information soon, but put it on your radar screen a week before CSM. And we have basically it's a summer school and a workshop and a model intercomparison project teaching young students and scientists about non-hydrostatic modeling. Thank you.
To Lin Cheng Li, who's going to give us a talk on high-resolution land surface data sets, I believe. Can you hear us okay?
Yeah, I can hear you. Can you see my screen?
I can see your screen. I think I can hear you.
Okay, good.
All right, go ahead.
Yeah, okay, thanks. Hello, everyone. My name is Lin Cheng Li. I'm an earth scientist from the Pacific Northwest National Lab. So today I'm talking about the development and applications of global 1 kilometer land surface parameters. Hopefully it could help to further enhance the kilometer scale Earth system modeling as we see many presentations this afternoon. So currently, we are towards kilometer scales. We see a lot presented today, at high resolutions at the kilometer scale, we can resolve the specific physical process that can the code resolution cannot resolve. For example, you can see here, you can see the structure of the clouds, and also in the ocean modeling, you can see more detail of the currents. And also in the land surface modeling, we have the ultra even high resolutions of the land surface simulations. For example, here is the soil moisture simulation of the corners at 30 meters, and also we have the digital twin Earth. We have a high resolution using AI technologies. For example, here recently the NVIDIA to launch the Earth 2 digital twin Earth, which can simulate the kilometer scale climate change modeling. When we look at the land surface, in this picture you can see a lot of detailed heterogeneities. Like we have different land scale land types with mountain, with snow, forest, and agriculture. Also have different topography in the valley and the mountains, and also could have this different soil moisture structures. But even we can see this high spatial heterogeneity in the realities, but in the company in the global Earth system models, its land surface parameters has limitations for the kilometer scale simulations. There are several limitations. Like they have usually it have coarse resolutions. Most of the data set like parameters are at 0.5 degree, and some is more than 10 kilometers. And also most of the data set is auto-dated. This default like CLM parameters are prepared about 10 years ago, and also it is temporally static. It's prepared either at a given year or only have 12 months for vegetation properties. So with these limitations, we developed the global, we will go to the globally at 1 kilometer spatial resolutions, and we will use the most up-to-date and well-validated data to process this, to prepare the data set. And we also prepared about recent 20 years, and we continue extending. And so we have the annual land-use land cover and also monthly leaf vegetation properties for use. And all of this data is processed with the Google Earth Engine. And here I'll show you a list of the how many parameters we have. So we have about 4 types. One is the land-use land cover. It includes the plant function types, and also the lake, glacier, urban distributions. And we also have the vegetation properties, includes the leaf area index, stem area index, and the canopy height, and canopy bottom height. And also have the soil properties and topographic factors like slope, aspect, and the scale view factor, all these parameters and the kilometer scales. And now I will show you some the view of these parameters looks like. So here is the land-use land cover of the 2010. So you can spatial patterns. You cannot see the details, but it's at globally at 1 kilometer resolutions. And also here I show you the leaf area index to show the vegetation, and with the sub-panel for subplot here to show you that how the topography will affect the leaf area index in the mountain versus in the valley. And this is show you details about the deforestation, how it changes the leaf area index in this deforestation area. And for this part here to show you that the irrigation will increase crop leaf area index of the desert in the Middle East, and also how the urbanizations impact all these leaf area index spatial patterns. All these kind of details can be seen in the kilometer scale data set. And here is show you some other parameters for the vegetation canopy height, the percentage of the clay, and also the topographic factors of the elevation and the slope. Then after developing this data set, I will show you some briefly comparison between this new 1 kilometer data set versus the default. Currently, we currently have 2 default data sets. One is from the CLM5 or CESM data repository, and one is from CUR 2012, this data set. I will show some example comparison for some parameters. So here to show you the plant functional type comparison. So for the bare soils, you can see in the green color is from the CRM5 default, and for the blue color is the new data set. You can see there's large, like about 10% of the difference in this bare soil landcaps. And also there's some difference in the broad evergreen tropical forest, and also some other difference in the other types of plant functional types. And here it shows you the comparison between the leaf area index. So here is the difference comparison. So this figure here is the difference between the new parameter versus the CRM default. You can see that new parameter is relative small leaf area index in the northern hemisphere, but the relative has larger leaf area index of the tropical regions. And here to show you the comparison with soil properties. So this is the new parameter. You can see it's more like spatially smoothing compared to the default CRM parameter is more patching. And this is their difference. You can see that for the percentage of sand, the new soil property has larger sand percentage over the north hemisphere here, and also should but have smaller values in many locations. So here is show you the difference between the percentage of clay and organic matters. Especially when you look at organic matter difference, you can see that new parameters, new data set has lower organic matters over the northern hemisphere, but has larger organic matters of the other locations compared to the default CRM5 dataset. And this is for the topographic index. So generally, like the new parameters have larger slopes than the CRM5 default slope parameters. Then with this dataset, I will show you two examples how we should demonstrate the capability of this new global 1 kilometer dataset. So firstly, the example is we conducted the 1 kilometer corner simulations, and we simulated the water, energy, variables. And if you look at the soil moistures, you can see these high details, but you can still see some mosaic here, coarse resolution. This is because of the Forsen dataset is at still coarse resolution at 0.5 degree, but you can see the high resolution patterns in other locations. Then I will show you how to do some spatial scaling analysis to show the high resolution, high heterogeneity simulations under this new dataset. So when we look at the 1.5 by 0.5 degree, this is the original 1 kilometer simulations. When we upscale this data to coarse resolutions, and we calculate the standard deviation in each case, and then we compare the standard deviation decreases, then we got the information loss. So information loss is the spatial variability decrease when upscale the simulation from 1 kilometer to coarse resolutions. And you go to 6 kilometers, the information will continue loss, and go to the 12 kilometers, it will more information loss. And so here is the show you example from the location 1. You really have larger information decrease when you upscale from 1 kilometer to 12 kilometer. This is another example to show you the relative small information loss when you upscale from 1 kilometer to 12 kilometer. And I will show you the spatial patterns of this sigma, of this spatial variability of the corners, and also the information loss of the corners. So here is the spatial variability of the soil moisture at 0.5 degree of the corners. You can see relatively large values in the eastern Texas and also North US and the Northeast US. And we also calculated the drivers to contribute these spatial patterns. And we find that the soil texture, the high resolution soil texture, is the main driver for this spatial variability of the corners. And here is the map of the information loss. And it's about 30% of the information loss across the corners if you upscale the 1 kilometer simulation to 12 kilometer simulations. And we find that the soil moisture, soil properties are the major factors to drive this information loss. So the second example is I will show you that because we have the 1 kilometer data set, but the 1 kilometer data set cannot guarantee you have a beta result, beta simulations of the high resolutions. So still we need some like calibrations. So we did some tests to calibrate the water table depth of the corners. So here is the calibration parameters. Right? In the models, there is one parameter called FGNH, the default value 2.5, and which can affect the groundwater table depth a lot. So when we calibrate this data, this parameter to match the benchmark water table depth. So here it shows you this how the calibration parameter looks like after the calibrations. It's relatively like have a large value of the shallow water depth location and a very high small value of the western US with deeper water table depths. So here is a comparison with the after the calibrations. So this is the benchmark water table depth from FAN 2013 dataset, and this is the default. From the default, you can see the difference is very large between the default simulated water table depth and the benchmark. And after the calibration, we can capture all the spatial patterns water table depth, and the bells is largely decreased, and the R square increase from like 0.3 to 0.8 or 0.9 after calibrations. So this dataset has a lot of broad applications. In many cases, we applied this for many different calibrations studies, like in the mid-Arctic simulations in northeastern US, and also we applied this for global land-ocean coupling because it has better soil property and the topography can better resolve the land-ocean interactions. And also we apply this for the lateral flow development and simulations of the small water basin and also of the upper Colorado River basin. And we also apply this 1 kilometer data of the using EM power flow phase simulations of the entire Amazon basins at 1 kilometer resolutions. We have more and more application going on. I will not go to the details. So this data set has like, before it is published, it has received many like interest from our communities. So this is one of the preprint is one of the, is the most read preprint from the PNL, and also this data set now is available in ESSD. You can refer this paper for more details. And as we are going to 1 kilometer resolutions, we developed this like land surface parameters, and then all other like 1 kilometer data set. For example, the EFAN trend, she presented yesterday about the global urban data set. With this kilometer data set and also other more future 1 kilometer data set, all these kind of 1 kilometer data set could further enhance the kilometer scale assessment modeling, as we see a lot in this afternoon's presentations. So here is the summaries. So briefly, like we developed the global 1 kilometer method parameters, and we demonstrated this like capability simulation of the corners, and we hope these kind of parameters can enhance the Earth's model and the kilometer scale simulations, and that's all. Thank you.
Thank you, Ling Cheng. Does anyone have any questions for Ling Cheng? Suppose not. I will say that, you know, this is actually pretty exciting from my point of view. I am aware that a lot of our input data sets for the CLM land model are based on resolutions much coarser than 1 kilometer.
Yeah.
So, anyways, thank you again. So that concludes our session for today. I'm wondering if we can all just give a round of applause for all the speakers. And let's adjourn. Have a good one. Sanitas. It's just this slim down.
the bear